ready to debate some more of the hot topics. We're looking at DNNs, we're looking at cognition again, and I'd like to welcome our first keynote speaker, who is Noah Goodman. He's going to be talking to us about reasoning in human and machine intelligence. Noah is an assistant professor of psychology, linguistics, and computer science at the University of Stanford. He received his PhD in maths from the University of Texas at Austin in 2003 and moved to University of Stanford in 2010, where he runs the Computation and Cognition Lab. Noah studies the computational basis of human thought, merging behavioral experiments with formal methods of statistics and logic. Specific projects vary from concept learning and language to inference algorithms for probabilistic programming languages. So it's a great treat for those of you online. Good morning, good evening, good night. Thank you for joining us again today. For those of you watching afterwards, you're in for a big treat. And for those of us here in the room, please let's welcome Noah for the opening keynote of day 3, AGI-23 in Stockholm.
Great, happy to be here. Thanks for waking up at roughly midnight, at least for me. Oh, I come to the Nordic countries and I get a ritual harpoon for my talk. It's excellent. There will be large fish to spear. So when I started thinking about cognition, maybe 20 years ago, we were in this kind of situation where we thought that there was a large space of possible intelligent agents, but effectively, the only example we had was human cognition. This isn't quite true. Of course, there were animals, but I was interested in language and reasoning and these kind of high-level cognition topics. And so for those things, really, all we could do was think about the properties of human cognition and hope that they would generalize to tell us about the sort of space of intelligences more broadly. Now, I think we're in a kind of unusual and exciting position all of a sudden in the last few years, because there are these weird alien intelligences popping up, in particular, the transformer-based language models and vision models. And I think they give us an interesting new perspective to try to map out the general properties of intelligence. And now I want to go back to a kind of trite, maybe a little bit tired, but I think newly interesting analogy that many of you have seen to think about this. So if we think about the space of flying things, we have birds at one corner. And before airplanes, we only had birds. And so when we thought about flying, we would think about all the things that are true of birds and try to generalize. Then, of course, at some point, humans invented airplanes. And all of a sudden, we realized that some of the things that are true of birds are not true of flying things in general. And we got a lot more kind of context for extracting principles. So in particular, if we look only at birds, we might see feathers and think that feathers themselves are important. If we look at airplanes, though, there are no feathers in sight, but there are turbine engines. And if we kind of like compare those, we see, oh, some of the things that we might have thought were really important about flying are not actually fundamental to flight. So we can try to start to taxonomize this a little bit, and we can realize that when we analyze the space of flying things, what we might be interested in is universal principles, and those exist. So in the case of flight, it's the principle of the airfoil, or Bernoulli's principle, that is really a kind of central thing across flying all of the things that fly. Then at the bottom, there's things that are really what I'm calling contingent facts, just things that happen to be true of a particular flying system. So for instance, feathers are made from keratin protein strands, and that turns out to be just an accident of evolutionary history. It's not fundamental to flight, even though it might be fundamental to birds. In the middle, we might have things like flapping. Birds flap their wings. And on the one hand, you might think that that's a contingent fact because airplanes don't flap their wings. On the other hand, when you think about the functional demands of birds and realize that unlike airplanes, birds have to take off at a very low speed, flapping certainly makes sense. So you might also call this sort of functional principles instead of universal ones. I put the turbine somewhere in between because it's partly a property of fast takeoff speed, and partly it's something that isn't that's contingent. Okay, but we're not here to talk about birds and flying things. We're here to talk about humans and machines and reasoning. So let me switch. Let me talk about reasoning a little bit. So what's reasoning? Well, basically, reasoning is just how humans seem to answer questions by going through reflective intermediate steps. So if you say, is Socrates mortal? Then you might go through the intermediate steps of saying, well, Socrates is a man and men are mortal. And so, yeah, Socrates is mortal. And that's, you know, the classic case of a syllogism going back to Plato. Or you might do similar things for solving equations in math. So to solve 3x minus 1 equals 2, you go through a series of steps. Each step is quote unquote relatively obvious, but by the end you get to an answer which was maybe not obvious to you. So in thinking about reasoning, I think there's these very deep questions of what are the principles and what are the contingent facts? What should be true of any system that does reasoning versus what's going to be true maybe just for humans or just for language models. So we might ask questions like, what is reasoning? Where does it come from? Are language models able to reason in some way that we think is close enough to call it reasoning? And more broadly, what are the principles versus functional demands versus contingent facts in human and machine reasoning? Okay, so to dive into this, just a couple of years ago, something really, to me, very interesting happened in NLP, which is that people observed that while we had trained these large language models to, as everybody knows, predict the next token, and had usually used them to immediately generate answers to questions, so what's shown as standard prompting here, several authors across a bunch of different papers notice that if you give language models room to generate intermediate reasoning steps and a few examples to show them what kind of steps you're interested in, they all of a sudden get much better answers. So in one paper, this was called chain of thought prompting. And the interesting observation from this paper was that chain of thought prompting yields better accuracy, for instance, at this common sense question answering challenge than just direct answering, although it does so only at fairly large models that have quite a bit of capacity. Another paper that was actually slightly earlier called this scratch pads and showed that for doing multi-digit arithmetic, which was something that language models were really not very good at, if you showed them examples of a kind of systematic arithmetic algorithm, you know, this is sort of like adding up digits one at a time with carry bits and so on, that they could generalize that algorithm and all of a sudden yield substantially better, like radically better results on multi-digit arithmetic. One of the most remarkable things, and again, this was an emergent behavior at some scale of model, one of the most remarkable things here was that without this kind of scratch pad or chain of thought, models would not generalize at all to numbers of digits beyond what they had seen in the examples. With the scratch pad, they started to generalize very well. It was like quite surprising. So I saw this and I basically thought, wow, this really starts to look like what I thought I was interested in when I studied human reasoning. Now this is a little bit tongue-in-cheek, but fairly recently, last month, Felix Hill from DeepMind sort of posted this snarky comment or question on Twitter. Does anybody think neural nets are missing system 2? And I wrote this comment in the middle of the night, and it was just for fun. But then I sort of have reflected on it since, and I think it's interestingly true and interesting to think about. So basically, this chain of thought reasoning, I think it really is something very much like what psychologists, including me, have called system 2. But there are contingent fact differences between what language models do and what humans do. In particular, language models are forced to, quote unquote, move their lips. Language models can't think without generating explicit tokens. That is not true of humans. We can close our mouths and still think step by step on the way to an answer. So I'll come back to this a little bit at the end, but let's follow this down and kind of think, what does this say about reasoning? So in particular, let's go back to the beginning and try to think about the origins of reasoning if we get to use this chain of thought style in language models as a kind of case study or as a way of thinking about it. Are there principles that can help us explain the origins of human natural reasoning, as well as the sort of clear, but I think not well explored question of why is it that chain of thought reasoning helps language models? There's no a priori reason that it should. So with my student, Ben Prostowski and Michael Lee, we said, okay, let's strip this down. Let's go back to a very simple kind of case study to think about it. So let's imagine a world that's just a joint distribution over propositional variables defined by a Bayes-net. The Bayes-net isn't important, it's that it's a joint distribution over a finite set of variables. And let's imagine a brain that is basically just doing a sequential density estimation. So it's just learning to autoregressively predict the next variable that it's going to see given the ones it's seen so far. So it's a sequential density estimator. Now, if you have a sequential density estimator like this, which I'm calling Q, and you want to use it to predict a marginal distribution, the probability of A given C, there's several different statistical estimators that you could use involving Q to predict the marginal P. And I realize there's a typo because this should be a C, sorry. So the first thing you can do is just say, let's directly predict C given A. So we just ask the sequential estimator, okay, here's A, what's C? In the case of a transformer, this really just corresponds to you put the sequence A equals A, big C equals, and let it fill in little c, figure out what it thinks the value is. Another thing that you can do is let the sequence model sample intermediate variables on its way to C. So maybe you give it A equals A, let it sample B equals B and C equals, and then ask it what value variable C has. So this corresponds to a Monte Carlo estimate where you're randomly sampling intermediate variables and marginalizing them out to get the marginal probability of C given A. Nothing special here. This is just like two very standard, extremely simple estimators for this marginal probability. What's interesting though, is that the second estimator, the Monte Carlo one, looks exactly what chain of thought is doing for large language models, right? You give it a question, you allow it to freely generate intermediate steps, and then you ask it for the answer. And so we can look at the value of reasoning in this setup by looking at the gap between the direct estimator and the Monte Carlo or intermediate variable estimator. So if one of them, if the direct estimator has much more bias than the indirect estimator, then we'll say, hey, reasoning is worthwhile in this setup, in this domain. If they give you equal quality estimates, then the reasoning is not going to be valuable. Just to kind of go into a tiny bit more detail about the training setup here, it looks kind of like this. So we start with a big Bayes-net. We generate training samples by first sampling from the Bayes-net. And then critically, we select an observation region of the Bayes-net. I'll say more about that in a second. We take the variables in that observation region. We randomly order them with the target variable, the query variable at the end. And that's a training example. And then we just train a standard GPT-style transformer on that data. Now, what we're manipulating is both how we use that transformer to predict the marginal probabilities, whether it's the direct or the reasoning, the indirect estimator. And critically, we also manipulate the structure of these observation regions. So you could either just observe the entire Bayes-net at once. That's the global observation condition. You could observe a subset of the variables, but drawn randomly across the Bayes-net, or you could observe a local region. So we choose a variable and we extend out several steps along the graph structure from that variable. So that's this local observation condition. Now, the reason we did that is because if you think about human learning, we have an egocentric viewpoint. So when we see the world, we see the things nearby and in front of us, and that structures the data that we're learning from. Okay. So then here's the basic results of this experiment. So again, we either evaluate using the direct prediction estimator or the free generation estimator. So solid line is direct and dashed line is free generation, AKA the chain of thought. And we do it with either training conditions where the Bayes net is fully observed, that's blue, or where it's locally observed, that's red. Now, the most important takeaway here is that if you don't have locally structured data, there's no value to reasoning. It's not useful to do this sort of intermediate local reasoning. If you do have locally structured data, then reasoning becomes valuable, basically because you understand the local structure of the world, but you need to stitch together this sort of local understanding in order to get longer range estimates. The other thing that's kind of remarkable about this plot is that there's a huge data complexity impact. If you ask your transformer to focus on only learning the local structure of the world, it learns that local structure much faster than if you give it the task of learning sort of everything globally about the world. In some sense, that's not surprising, but I also think it's a really important observation about the right way to train sequential density estimators and cognition in general. Okay, so what are the takeaways from this little project? Well, the first is, as I said, if training data is organized into local observations, but not global or random or some other baselines, then reasoning through intermediate variables, chain of thought, is helpful. Now, in the paper, we actually prove a theorem about this in a simplified case. I won't go into the details, but you can show that essentially for some simple Bayes net structures, the risk minimizing estimator has this reasoning gap property. And the reason that I wanted to mention this, that it's important, is that this really doesn't have to do with transformers per se. This has to do with sequential density estimators that are risk minimizers. Transformers just happen to be a really good way of doing that, but they're not at all a unique way of doing that. Okay, as I mentioned, the data complexity is also much lower. And so the takeaway is that reasoning using chain of thought as kind of the I don't know, the stand-in for what I'm going to call reasoning for this purpose, is something that emerges for sequence models under certain conditions about the training data. It's not about the model architecture per se, it's this locally structured property of the training data. Okay, so you might have noticed that in that previous section, when the model was asked to do reasoning, it would just randomly generate intermediate variables however it wanted. And that's enough to get a benefit to reasoning. However, that's not actually kind of what human reasoning looks like for people like us who have spent years and years being educated. Somehow we've managed to make our reasoning better over time and practice. So you might ask, can we make large language models improve from practice or from minimal amounts of feedback? So my student Eric Seligman and co-authors made a system called the self-taught reasoner, and it's actually a super simple kind of probably the most possible simple reinforcement learning algorithm. What it does is it simply says, okay, let's take a large language model that's doing chain of thought reasoning, and let's give it new problems. Let's let it generate its own rationale, its own reasoning, generate an answer, and then we'll check. We'll say, yes, that was right or incorrect or not. And the simplest version, if it got the right answer, we'll add that to the training data set for fine tuning. So we're going to fine tune it on its own correct reasoning traces. And this, actually shockingly to me, I didn't think this was going to work. This works really well. So this is the case of multi-digit arithmetic that I mentioned earlier. And what you see here is iterations is the number of iterations of this, this star self-taught reasoner process. So 0 is the initial model. And then what you see is that after the first iteration or two, the model figures out how to do one-digit arithmetic problems, but it's still quite bad at others. And then it gradually extends that in Bootstrap, sort of figuring out how to do 2, 3, 4, 5-digit arithmetic problems. We can also do this for the common sense QA data set, which is these kind of short, I don't love this data set, but it's kind of like these short common sense-ish questions that have been used previously for chain of thought. And the baselines here, so we're fine-tuning the GPT-J model. By the way, if we did this today, we would fine tune whatever came out, 30 30 seconds ago, Llama or Vicuna or something. But GPT-J was the biggest model we could train when we did this a year and a half ago. So the baseline is, if you just use few-shot chain of thought prompting with GPT-J, you get about 36%. If you use GPT-J fine-tuned on the final answers without chain of thought on the whole data set, you get about 60%. If you take GPT-3 and fine-tune it on the whole data set, you get 73%. And the self-taught reasoner, the basic version, gets up to about 67 or 68, 69%. Okay, so then Eric thought, yeah, but when people get an answer wrong, they still learn something from the fact that they got the answer wrong. So he wanted to see if we could get that. And so he added this extra thing, which says, okay, if the model tries to solve a problem and gets it wrong, then why don't we give it a hint? We're going to go back and we're going to annotate the correct answer with, well, correct. And then we're going to ask it to generate a rationale, a reasoning trace, and an answer. And then we'll check again and see if it got it right. Now, the model actually doesn't always get the answer right, even when you give it the answer. So that's interesting. But it does quite a bit more often. And so then what we can do is take the rationale it gave, strip out the extra hint, and treat that as a training example and put it back into the training set. So he calls this the rationalization pathway. And when you do that, you get a little boost in performance, a little bit important, I should say. And now all of a sudden, STAR with rationalization matches the performance of GPT-3 when it's directly fine-tuned on the data. Okay, so cool. So it turns out that, yeah, actually language models, benefit from reasoning, as other people had shown, and they also benefit from learning how to reason by kind of, studying, so to speak. Here's a little interlude. So there's a lot known about human reasoning. One of the most important effects in human reasoning for the kind of basic logical reasoning is that people are not good formal reasoners, because for us, there's a lot of interference from our common sense knowledge. So one of the basic effects here, which is sometimes called a content effect or a belief bias, is that in common sense situations, we are much more likely to endorse conclusions that are consistent with common sense than those that are inconsistent, even if they're both logically valid. So for instance, all students read, some people who read also write essays, therefore some students write essays. People are going to say, yeah, that's great. An equivalent, formally equivalent argument, all students read, some people who read are professors, therefore some students are professors. People are going to say, oh, no, that's no good, right? And this is a belief bias. It's based on our common sense belief. This goes back actually, the particular study is from papers by Evans, but it goes back substantially before then. So there was a really nice paper just in the last 6 months or something like that, not very long ago, from some folks from DeepMind, mostly former Stanford people, where they basically just said, okay, let's do these experiments with large language models. And so they set up belief consistent, belief inconsistent, syllogistic reasoning, as well as novel or nonsense syllogistic reasoning, so with no content effects. And the basic observation replicated the human findings, namely that in cases where the conclusion is consistent with a priori beliefs, the model tends to just say, yes, this is a valid syllogism. And in cases where it violates our belief, the model mostly says no, but actually it's a little bit more subtle to the logical validity in that case, which is also what people do. Okay, so something that we've done very recently, and it's going to take me just a few extra slides to build this up, so bear with me, is we've said, well, people have found ways to work around our own biases. In particular, well, naive humans who you get to do experiments are very subject to belief bias. I'll bet if I asked all of you in this room to do those syllogistic reasoning cases, you would catch yourself and you'd think carefully step by step, so to speak, and you'd come to the formal conclusion that first order logic wants you to come to. So what humans are able to do is externalize our reasoning using these tools that we've come up with. So for instance, by using logic in order to avoid certain things that we've determined are reasoning fallacies. So recently, my student Gabriel Poesia and co-authors started asking whether language models could also benefit from this kind of externalized reasoning. So the first thing that we did, actually, this is a little ahistorical. We did this first, and I'll come back to it, is we defined a theorem-proving language and environment. He calls this piano. And it's basically a dependently typed lambda calculus, very, very similar to Lean and Koch, if you know those. So I won't go into the details because it's not that important, but what is important is that it's expressive enough to express formalizations for all the standard proof theories that you would want in math. The other important thing about piano is that we restrict the proof rules, and we restrict the proof rules in such a way that you can only apply a single axiom for each proof rule, which effectively limits the action space at every proof step to be a finite space. It doesn't actually limit the expressivity of the language. You can get to the same proofs eventually, but you'll have to take more steps. And the reason that we do this is that the kind of techniques that we like to use in language models and reinforcement learning more generally work a lot better if the action space is finite at every step. And so it's very, very hard actually to do modern machine learning with a language like Koch or Lean because of this sort of explosion of possible next steps that could be derived. So piano is very similar, but it limits it to a finite action space. Okay. I don't have much to say here other than you can formalize all the standard things that you want in piano. So here's sort of algebra and geometry and number theory and all this good stuff. So then the idea was, okay, let's use this formal reasoning tool to augment a language model. And this is a kind of high-level schematic. It's pretty hard to look at, that I'll explain in just a second. But the basic idea here is that language models are responsible for generating sequences token by token. That's great. That's what they do well. Proof systems are responsible for generating derivable next steps given the terms that you've derived so far. They do that really well, and that's great. We want to put these two things together. And the way that we're going to put these two things together is by having these constrained generation blocks where we don't let the language model generate just anything it wants. We restrict the language model to generate something which is valid according to the logical inference engine. And we're sort of seeing schematically here that while we still generate that sequence step by step, token by token, we do it in a way where we disallow sequences which are not going to be considered valid by the logical engine. Now there's a little bit of, oh yeah, let me go here and say this. There's a little bit of subtlety to how we do this. So the basic high-level sketch is actually very simple. The language model is allowed to generate a special type of open bracket. When it does generate that open bracket, it goes into constrained generation mode, where it can only generate things that are true according to the proof system. The way we actually do the constraint is a very clever algorithm called synchromesh that lets you restrict to the closure of a regular expression when you're doing generation. I'm not going to explain it, but there's a nice paper on it. And then when the language model generates the closed bracket, it goes back to freely generating. It turns out that this is a very general thing that you can do in language models that we call a guide tool. It generalizes the kind of tool use that people have been doing with language models a lot recently. And in particular, if the underlying computation you use to constrain inside the constrained blocks is logic, so like piano, we get something we call the logic guide. And now the logic guide basically can do two kinds of things. It can either decide to introduce a new object, relation, or axiom, or it can decide to do an inference step, which is constrained to be reachable in one axiomatic step from the terms constructed previously. Let me show you an example. So what we give to the language model, first of all, we give a few shot, I think just one few shot demonstration so that it knows what it looks like to use the logic tool. Otherwise, it won't ever generate the opening brackets. Then we give it the problem. So for instance, we tell it the story, the mouse visits the tiger. If something visits the tiger, it visits the mouse, and so on. And then the language model is going to generate this block where the orange things here are objects, relations, and axioms that it's formalizing. So it goes through this process of formalizing the natural language that you give it. And it's actually quite good at doing this formalization from just one shot, one example. It formalizes the goal. And then the blue parts here are where it decides to use the inference step and does constrained generation of kind of logically reachable states. Okay, so now what we want to compare is how well does a language model that's given this extra logic guide sort of externalization do compared to the language model that isn't given the external tool. So first of all, if we go back and we look at the syllogism task from that Dasgupta paper, well, really from the Evans psychological research. So what I'm showing you, the blue bars are what happens with the language models. This is 3 different language models just by themselves doing chain of thought reasoning. And indeed, what we see is that they're not great at this, right? There's this strong belief bias effect. It's actually interesting how it comes out here. In the consistent case, the language model basically always gives the answer which is consistent with prior knowledge, which means because the data set is balanced, that it's correct 50% of the time, it's at chance. In the inconsistent case, it's a little bit more accurate because it actually reasons according to logical validity slightly more often when the conclusion violates the common sense knowledge, which is also what people do. Okay, and then the orange bars are showing what happens when you let the language model use the logic guide. And you can see that we're basically at ceiling for the stronger models, GPT-3 and GPT 3.5. So even though we only give it one example of using this externalization, it's really quite good at using it and then paying attention to it when it generates an answer in order to get correct answers. Now, the llama model is smaller and, well, weaker. And it's interesting that, first of all, it's completely at chance without logic guide. There's a little bit of a boost with logic guide, but it's nothing like at ceiling. And I'm going to come back to this in a minute. We can also then look at multi-step reasoning. So the example I showed here, the silly kind of example with the mice and the tigers, this is drawn from a multi-step reasoning task called Pronto QA. And so we can look at the Pronto QA and a similar data set called Proofwriter. And this is again broken down into the kind of belief consistent, belief inconsistent, and nonsense word splits of the data set. And the plots I'm showing you here, the I guess lightweight sort of, hard to see lines are without logic guide, and the heavier lines are with logic guide, and the colors are the different models. And so what you see is that, not surprisingly, Pronto QA in the true condition is sort of close to ceiling for everybody. That's because if you are consistent with common sense knowledge, then you get the right answer in the true condition. In the false condition, though, the models that don't have logic guide are really quite bad, particularly as the number of logical reasoning hops required gets longer. And logic guide largely fixes that and allows the model to reason, much more correctly, even with, well, I was going to say quite long. It's not that long, 3 or 4 reasoning steps. The notable exception here is the llama model. Again, the llama model is just not very good at this kind of reasoning to start with. And while logic guide makes it a little bit better in many of the cases, it's nowhere near at ceiling. So it's sort of not able to properly pay attention to the extra information. So we decided to go and say, well, what happens if we do that self-taught reasoner STAR process now with the logic guide as part of the process? And now there's a really interesting failure mode of STAR. So this is a task with a binary response. And the problem with binary responses is that if you choose at random, you'll be right half the time. And if you then train yourself on your own reasoning when you are right half the time by accident, you'll reinforce incorrect patterns of reasoning. And so what you see in the red curve here is if we just do naive STAR, it kind of improves a tiny bit at the beginning, and then it starts to catastrophically interfere with itself. Okay, so then we can say what happens if we use the guide, which makes responses better, and just that's all we do. And the result is like, we get an initial improvement just because you have the guide and it provides a little bit of better accuracy. But then there's still a fair number of responses that are kind of correct for the wrong reasons. And so the performance starts to degrade as you keep training on your own reasoning. So the last thing we tried, which is the yellow curve, is to only train on arguments where logic guide derived a valid conclusion. Now, this doesn't guarantee that the reasoning is correct, because the logic guide could have formalized the problem incorrectly. It only guarantees that given how it formalized the problem, it has derived a valid conclusion from that formalization. But that turns out to be enough. That winnows out a lot of the bad reasoning, and then this is the yellow curve. You can see that now it's starting to bootstrap. And so to me, this is really interesting because it means there's this synergy between self-study and having these formalized, externalized cognition systems. They go really nicely together. Okay, cool. Now, those of you who think a lot about reasoning, especially logical reasoning, which I know is a bunch of people in the room, might have the criticism that the reasoning that you have to do is not very extensive in these cases, right? Okay, 5 steps of logical reasoning, okay, it's pretty big because of the branching factor, but it's not gigantic. So another thing that we've been thinking about is, what does this look like in domains that are kind of, in some sense, more, I don't know if I want to say realistic, but like more useful and closer to things that people actually are forced to learn. And in particular, we've been looking at middle school math and high school math kinds of cases. So Khan Academy is this amazing resource. It's a curriculum for math from basically first grade through high school. And we did a case study where we went into the Khan Academy algebra curriculum, and we just extracted the first 5 sections of Khan Academy algebra. And these are things like learning to substitute and evaluate expressions, combining like terms, 1-step addition and subtraction equations, 1-step multiplication equations, and then what they call 2-step equations. So they're all, at the end of the day, learning to solve what are very simple equations. But the thing that's important about even these simple equations is that the solutions, if you derive them from the axioms of algebra, are really like quite long. So let me, first of all, we can formalize this in piano. So piano, like any other theorem proving language, is a nice place to formalize this. And the formalization is not long. You have, some real types, some commutativity, associativity, et cetera, axioms. And then what we do is we write the axioms in piano. Importantly, that's not important. We turn the exercises that we find from Khan Academy into templates for sampling new problems, so that we have a pretty big distribution of problems from each of those sections of Khan Academy. Okay, now this specifies a well-defined search problem, right? Here's just standard logical search problem. It's well-defined, but the branching factor at every step is kind of huge. And it takes actually a lot of axiomatic steps to get an answer, even for simple equations. And so it turns out that if you do combinatorial search naively, it doesn't work very well. Now I'm basically saying what everybody knew in the 1950s or 60s. But if we just, in this case, do breadth first search up to some pretty large amount, we solve really a pretty low percentage of each section of Khan Academy. So we have to do something a little bit smarter. Now, the thing that we tried, first, let me stop and say, of course, there's a lot of smarter things that people know how to do. You can use A*, admissible heuristics, and all of these kinds of things. What we were interested in is what it looks like if you ask a reinforcement learning agent to learn how to do search itself, rather than sort of teaching it, showing it how to do search a priori. And so what we did in a series of papers was we basically used the same extremely simple reinforcement learning algorithm that I showed you for STAR, which is sometimes called expert iteration, that just iterates back and forth between using your existing search policy to you randomly sample problems, try to solve them using some simple beam search with an existing policy, and then you throw out the ones that you don't find an answer, and then you imitate, you do fine tuning on the ones where you get a successful answer, and then you iterate, you keep doing this. So it's the same loop that I showed you before. So in this case, we weren't using a language model. This was way back in 2021, which is like ancient history now. We were instead doing what's called contrastive learning. Here I have a picture of this over here. So contrastive learning, basically, you're learning a representation for equations for states by embedding the strings into some vector space. And contrastive learning just says that you're going to try to bring two states that are on a valid solution path closer together and send states that are on invalid solution paths farther apart. You do it with a little bit of a fancy estimator that reduces noise. And it turns out that's enough to then learn a representation space where your policy is just move to the possible next state that's closest to your current state. That works pretty well, it turns out. And so when we do that, what we find in these Khan Academy domains is that the first several sections are solved well, but it gets stuck after that. It's not making a lot of progress. And so Gabriel dug into this. He said, okay, why is it getting stuck? And he observed that, not surprisingly, as we move from section to section, the solutions are getting longer in terms of the initial axioms. And this is particularly a compounding problem when you're doing the kind of term rewriting inference like piano, because the more steps you've taken, the more terms you've constructed, and the more possible next terms there are to evaluate. So there's this like huge branching factor explosion. And so the probability of actually just finding valid solutions to bootstrap from kind of falls precipitously. It's really the complementary problem to the one that I talked about before with STAR. The earlier problem was it was too easy to find answers that were right for the wrong reasons. And this problem is that it's just too hard to find any answer at all when you restrict it to the right reasons. So Gabriel thought a little bit about kind of intuitively what's going on with humans when they're learning these things. And the important observation is that by the time you get to a problem from what they call one-step addition and subtraction equations, you're not thinking in terms of the most basic units of the most basic axioms anymore. You've already learned about substituting and evaluating and combining like terms. And so in terms of those sort of earlier sections of Khan Academy, you can really just think about the solution as 3 steps. You can think of it as like, oh, I observe that I can subtract a number from both sides. That's kind of the new step here. Then I combine like terms and I substitute in on the right-hand side, and then that solves it. So in terms of these kind of alternative units of reasoning, what would have been I think it's like, 15-step solution becomes a 3-step solution. And so Gabriel's idea was this is probably what human students are doing as they go through the curriculum. They're learning these abstractions that they can use to reorganize and simplify the proofs. So can we do something similar? So we kind of reached back into this nice old literature on program induction. And in that literature, so first we introduced tactics to piano, and tactics are really just sequences of axioms or other tactics. And then we do tactic induction by anti-unification. So what this means is we just look at all of our successful solutions so far, we line them up and we look for parts that match, and we try to create new functions based on the things that match, introducing variables for the parts that don't match. So like P0 here doesn't match between the 2 green things. Okay, and so this gives us a kind of interestingly augmented version of that expert iteration loop, where first we again solve a bunch of random problems, but now using our current tactics as axiomatic steps. Then we try to do anti-unification to compress the solutions and find some new good tactics. And then we rewrite using the new tactics and train the model, train the policy to solve based on those. So we introduce this additional abstraction step in the middle. Oh, and I should have said this here. This is sort of similar to Kevin Ellis's work on Dreamcoder, which is a very cool system, but this is all done in a theorem proving sort of setup, which changes a few of the important details. Okay, and it turns out that now if you do this abstraction step, you can solve all of the sections of Khan Academy. And it's interesting that it undergoes these kind of transition moments where if you dig into that, what you find is happening is that it gets enough evidence to form a useful abstraction, a new tactic, and that's what lets it then find the solutions it needs to train on. Okay, almost done. So the one additional thing we found about this, which I think is cool. So here's a fact about human math that has puzzled me since my graduate student days. So it took a long time historically to invent things like algebra. And yet we expect high school students to learn all of algebra very quickly in one or two semesters. And there's lots of ideas about what accounts for that acceleration. Why is it that a single human can recapitulate what took human society so long to get to? But one of the ideas is that it's the curriculum, the order that we introduce things, that matters. So we realized that we could actually do a kind of simple test of this idea using this piano with tactics. Basically, initially training problems were not seen in any curriculum order. We just took random problems. But solutions that have tactics can be ordered because tactics call other tactics. And so you can just do a topo sort based on which solutions rely on tactics that depend on each other. And you can make a curriculum just according to that topological ordering. So the problems that require simple tactics go first, and et cetera. And so the green curve here is if you go back and you train a fresh copy of the agent using that curriculum order based on the tactics from the blue curve. And what we found was that systematically, the curriculum ordered agent learns the same thing faster. So, putting the things in the order that supports the correct tactics indeed speeds up learning. Not enough, I think, to account for like 300 years compressed to one semester, but enough to be, I think, pretty interesting. Oh, it also reconstructs the curriculum of the original Khan Academy curriculum pretty well, up to symmetries in the ordering. Okay, let me finish off. So I started off with this picture where I said, hey, all of a sudden we have two intelligences in the space of intelligent things. What can we figure out from kind of comparing and contrasting them? And then I kind of like went off onto a wild digression about birds and airplanes and stuff. But the basic point here is that once we can compare things, we can ask, okay, what looks like a universal principle? What looks like a functional demand or a functional principle? And what looks like accidental facts? Now, this is not intended to be anything like the final answer, but I do think that by studying language models and comparing to human reasoning, you can start to extract these really interesting things. Like I tried to argue at the beginning that sequence prediction, not necessarily transformer architectures, but sequence prediction and these properties of the training data, like local observations, I think are universal principles that explain when and why reasoning is helpful. On the other hand, I think some of the stuff that I talked about in the middle, things like self-improvement and externalization, I don't think those are universal. I think you can have reasoning systems that don't interface with those, but I do think they look very much like functional demands or functional principles, right? If you want a system that's going to self-improve, it's going to need to have certain properties like the ability to sort out good reasoning from bad reasoning. Finally, I think there's things that really are contingent facts. So, some people look at language models generating step-by-step reasoning and say, haha, look at the language models, moving their lips. They have to talk when they reason. People don't do that. And I think that's true, but I think it's a boring consequence of just how we happen to build those language models. Similarly, we humans have incredibly bad working memory. And I think a lot of the things that we have to do and the things that we have to externalize are probably a consequence of that evolutionary accident. And hopefully this kind of taxonomy is something that will now now that we have more examples of useful agents, and not just the ones that I talked about here, we can sort of learn more about the space of intelligence and not be overly optimizing on human intelligence. Well, there should be one more slide that thanks my students, but it is not changing. So hopefully it'll go. Anyhow, thanks to my students who did all of this work.
Fantastic. That was absolutely riveting. And we've got questions in the room.
Yes, thank you. This was fascinating. You made the jump from intelligence to reasoning. Now, and you kind of assumed that large language models are therefore intelligent, but are there not other important aspects of intelligence other than reasoning?
Yeah, I don't know. You know, I teach the introduction to science at Stanford, and the thing that I'm most annoyed about with the whole community that really is clear in Intro to CogSci is that we sort of assume that we know what intelligence is by intuition or by law. That doesn't smell intelligent, and that does. So I guess these days, my instinct is to say, look, if it does a whole lot of behaviors that we previously had considered intelligent human behavior, then let's put it in that class of intelligent systems and try to understand it and understand like the differences, rather than thinking that we know where the boundaries need to be. And so I guess my answer is like, I'm interested in reasoning just a priori. That's what I'm, particularly interested in. And I don't know where the boundary should be between intelligent and unintelligent. And so taking these things as examples and seeing what they do and how they compare to human reasoning seems like a productive way forward. That's fair. Yeah. I mean, maybe you would want to say like, intelligent reasoning, and then, certainly intelligent perception is somewhere else entirely. Yeah.
Yeah, thank you very much for an interesting talk. I don't know if this is pedantic or a substantive critique, but no one reasons in any professional capacity in anything like the fashion that piano does. Humans reason when they do it deductively using natural deduction, right? So it's all hypothetical driven. And in the teaching of logic in the Western world, this is not, you don't learn formal logic in keeping with any Hilbert style stuff. You learn, again, natural deduction. Mm-hmm. Okay. So this is, from that standpoint, bizarre. When you give these large language models any of the hypothetical driven reasoning that you would traditionally teach even in a first decent course in formal logic, and they can't fall back on, it relates to what you said about the search space, a single inference schemata or one or two. That's meaningless. It's not what humans do. Okay, that's not what reasoners do when they are doing serious reasoning. So I guess this might be a stepping stone on the way to that, but I don't get it. Now, again, maybe pedantic. The second thing is you have to immediately teach second order logic. Okay, without second order logic, you can't reason about arbitrary properties, and we teach that. And if we don't have second order logic, we're in trouble. So a good place to look historically for where this paid great dividends would be Einstein's gift received from Gödel. How did he prove time travel is possible? Did he derive it from axioms? No. He imagined a hypothetical situation and then proceeded to reason from that. And it's also second, if not third order. Now you might say, well, we don't want, this is, early stuff, but I'll let you,
let me respond.
Absolutely. Sorry. Yeah. But you know what I'm saying.
Yeah. So, okay. On the one hand, mostly missing the point. On the other hand, there's an element here that I agree with. So actually, first, let me just clarify. Piano is dependently typed lambda calculus, so it's higher order. I used it in a first order setting, but that's actually not a constraint. I think the question of what is the basis, the axiomatic basis to use, is interesting and important. There are very good reasons that the formal methods community is using, things like Coke and Lean that are based on dependently typed lambda calculus. It's actually really hard to ground out most of the math that we care about for professional mathematicians into natural deduction, partly because of the higher order issue, actually. So like, I don't have a big horse in this race, but I think like there's formal reasons to tie into that. The critical thing here is not any of that. The critical thing is really understanding how the relationship basically between, you know, a search space, a formally specified search space that is capable of solving in principle the problems that you're giving it, and the kind of the structure of intermediate reasoning and learning to reason, right? We've actually also done this for natural deduction, and the same things happen. It's just that actually for most audiences, natural deduction seems kind of unusual, and so it's harder to explain. There's one technical thing that is super important that I want to endorse, which is piano at the moment doesn't support backward reasoning steps. That is important, and interestingly, like there's a very critical moment in a mathematics curriculum where that happens, which is not algebra, it's not up through high school. It's the first advanced math courses that all of a sudden you need to do backward reasoning. And this is something we're kind of thinking about now. It's related also to like, how do you introduce proof by induction, right? Sorry, one kind of irrelevant thing I wanted to mention, trying to limit the number of proof rules, I think is like not actually a good idea, because when you go down that route, you get to resolution. And there's this amazing quote in the paper on resolution, which is that this is a completely human indecipherable, you know, it's one rule, but it's completely human indecipherable by construction. So it's not clear that that's the ultimate route. I'd be happy to chat more about this afterward, though.
We've got four more questions in the room.
I'll try to be fast, sorry.
Well, no, because it's fantastically interesting. You've come such a long way. So.
Yeah, thanks for the talk. So I really love this work. It's fascinating. I mean, I don't think, you know, these LLMs are AGIs or are going to be transformable into AGIs, nor that they're necessarily thinking a lot like humans are, but I think they're extraordinarily interesting systems, and I'm quite curious to probe what they can do and they can't do. And so along those lines, so I mean, I've been playing with these systems myself, like probably all of us. So with the simple arithmetic stuff from Khan Academy, it's impressive and interesting, but obviously there's very many examples of that precise sort of math in the training data set on the web, which is helpful. Now, of course, humans are largely doing things of which we've seen many examples in our life history also. So that's, but not as many examples, right? So what one would like to see, and it's a bit ill-defined, like if one had a comparable class of problems of sort of, in some sense, vaguely comparable complexity and difficulty, like not general relativity field equations, but some other formal system, like some alien might have made up, which didn't have 10 fingers or something, right? Some comparably simple body of math knowledge, and tried to get the algorithm to do that, then it would be interesting to see what sort of transfer could be done, or how much worse it did without all that priming with so many arithmetic problems online. And I've tried similar-ish things with ethical reasoning, was actually impressed with how GPT-4 did. Like you give ethics puzzles from human situations, or you then define an alien civilization and give ethics puzzles in the context of the alien civilization. It doesn't do badly in that context, but these ethics puzzles are in a way even shallower in terms of inference depth than arithmetic. So I mean, that's hard and annoying to set up, obviously. So I see why you haven't done it, but I'm sort of wondering, what's your even intuition about how these systems might do in that sort of setting?
Yeah. It's a good question. So the data complexity question is, so people bring this is only a small part of what you said, but people bring this up a lot, but I think it's actually like devilishly hard to get straight. Just like there's so many dimensions that differ in the experience of, you know, most of our language models versus, say, a high school, you know, student, human high school student. The kind of data that they see, right? Human students get a lot of kind of natural language explanation as well as the other stuff. et cetera, et cetera. So like this is part of the reason that I think like, conceptualizing it as this like space of agents that have different experience and we can explore their different capacities is maybe more useful. They generalize pretty well, actually. They're not, how to say it, like you could hold them to a really high standard, which is like, I made up a crazy new, formal domain, gave them 6 examples, and I expect them to learn and generalize perfectly. They don't do that, but neither do humans, right? So we've done, this is preliminary and not published, but we've done some simple things where we create these string rewrite domains, right? So basically there are string rewrite rules that define novel domains, which have at a high level similar structure to the way, like algebra works, right? You go with a string, you have some axioms that allow you to rewrite. By defining novel domains, we can come up with systems that humans have never seen before, and similarly models. And then we can get a little bit more of an apples to apples comparison. And like, the finding so far is that these are really hard for humans. Like, humans are not good at this. They benefit a lot from a curriculum, but not perfectly. And that our models kind of are similarly not amazing. They benefit from a curriculum. I think they're a little bit better than humans at these things. But a lot depends on the prior knowledge and kind of the training. So I guess, to the very first part of your question, my take here is that like, these things don't have to be human-like intelligence in order to be intelligent, and that makes it more exciting because now we can compare and contrast. I think they're intelligent because look at all the things they can do that we didn't think they'd be able to do, like when I was last at AGI 10 years ago or something, right? And I think they're general just by virtue of the fact that they do a lot of different things. Now, it turns out probably when we said AGI 15, 20 years ago, there were some other things we had in mind that like aren't in the name, right? And that's a great coffee conversation. Right. Yeah, okay, that's fair. And I think they generalize surprisingly well, but it's like individual humans who are not us don't actually generalize all that well, right? And so I think that's the starting point you have to go from. And then you say, okay, do these generalize, as well, same, different? Yeah. I don't want to take up too much more time, but
we've lots of questions coming through. No questions online, but I hope you're following all of the great discussion. We've got a common question from our conference chair, Klaas.
Thank you. Thank you so much, Noah, for a great talk. So I'm curious about search, where search comes in. Do you think that search maybe should be added to those universal principles of reasoning that you mentioned? And I also wonder if you think that search needs to be added to get large language models to be able to do system 2 reasoning.
Yeah, okay, awesome question. So look, there's 2 ways to add search in these language model settings. One is basically searches in a computation outside the language model that structures what the language model, how the language model searches over continuations. And the other is inside the language model, where basically the language model decides what steps to take, including backtracking and going on from somewhere else. Both things have been tried recently. So there's a paper called Tree of Thought that does the first one. There's a couple of papers that partially do the second one. It's not clear which of those is going to be most productive, but I think it philosophically matters a lot, because if it turns out that the language model can learn how to do search internally inside its own sequence modeling, then I think search is not sort of a top level principle. It's something that emerges from learning to do reasoning. I would love to see that happen, but I think we don't know yet. On the other hand, it is possible that like it won't spontaneously emerge, that you have to build in something about the structure. One thing that we do know from a recent paper, or the field knows, and I know from a recent paper of one of my students, is that if you show large language models examples of systematically searching over, we were doing game trees for like matrix games, right? Simple game theory. It's actually reasonably good at generalizing to other matrix games and sort of recapitulating that search process. And so that makes me think that it may in fact be sequence modeling that's the basic thing, and that search arises out of that, but we'll see. There was one, yeah.
Thank you for your fascinating job. I really think that language models is one of the missed components for the AGI, and we need to understand how to continuously learn distribution drift. But my question about the guided fine-tuning, do you think that it's possible to completely end-to-end train a language model based on the Turing complete symbolic program? And maybe this is one of the solutions for alignment problem. Thank you.
Okay, yeah. By the way,
Thank you.
online lifelong learning, I agree. We don't know how to do it very well. We should figure it out. Low rank approximations are a good trick, though. They're really cool. Okay, so with respect to the computational issue, the Turing completeness, here's two, I think, fascinating facts. One, transformers are not Turing complete. They have actually a pretty restricted space of formal expressivity. So for instance, they can't solve the parity problem with some star. There's some assumptions there that they can't solve parity. Language models with chain of thought reasoning are computationally more expressive than language models without intermediate reasoning. That's interesting. Language models with even the simplest kind of external guide, like the logic guide that I showed, actually now are universally complete. So it actually and it's very similar to the way that if you take two context-free grammars and intersect them, all of a sudden you're not context-free anymore. And so I think there's actually, even though transformers are not complete, there's kind of a bunch of fairly simple things you can do to boost them up to that point. And so I think that means that it might not be as hard as it might have looked although there's still huge training questions of how you mix those things together. Yeah. That's a complicated question. So it's not end-to-end because there's discrete things. So most of the models I was showing you was basically doing training as a reinforcement learning setup, although in this really simple expert iteration style, right? So that's not end-to-end because you can't get gradients through the token generation. It's not totally clear that you need to be because these kind of simple RL approaches work well. And similarly, RLHF is not end-to-end, right? And yet it works well. So whether that is still clearly for pre-training for scalability reasons, you need that. I actually think that what we actually have discovered is that all we care about is risk minimizing sequential density estimators, and that the magic, which is not very magical, has just been in how do we do that at scale, right? We've gotten a lot better at that. End-to-end was helpful, but may not be required, et cetera.
Oh, yes. Thank you for a lovely talk. I really enjoyed that. You'll have to pardon me if my question is naive. I'm a poor, stupid mathematician. So
Me too.
All this AI stuff is way over my head. But I was quite interested by the justification branch of the star reasoner. And in particular, when I inspect my own mathematical experience, what I find is both a wild ass proposer and then someone who's quite skeptical on the other side, and there's a game going back and forth, very similar to the sorts of things we see in Lakatos's account of proofs. Yeah. And I wonder if you've explored this, where you combine both proposer and opponent.
Yeah, I haven't, but there is recent research that does this, and I guess let me just mention two things. There's one paper from, I guess, last year, its name I'm forgetting, but basically it looks at verifiers and shows that if you do something a lot like STAR, where you don't know the right answer, but you generate many examples. And one thing you can do is have them vote, but another thing you can have them do is you can have an external verifier to say which of these looks good. That helps a lot. And that's really cool. The other thing that is very recent and that I find fascinating is that people have been doing a lot more natural language critique as part of this revision. So we didn't do any, it was just correct or incorrect. Recently, people have been asking, this only works for GPT-4. It seems to be, yet another emergent thing, but they've been asking the models to generate natural language critiques of their own failures and using that to revise. And that seems to be pretty effective, which I find again, similar to my personal, introspection and really fascinating. And there's a nice paper called Reflexion that does that, as well as several others in the last, I don't know, 2 days. I mean, it's actually a month, but yeah.
Well, I feel like this conversation could just go on and on in the room. Thank you all very much for your questions. Thank you, Noah, for a really stimulating start to the day today. Thank you for coming all the way here. Let's have a big round of applause for Noah Goodman. Thank you. Right, next up we have four technical papers on cognition. I'm going to invite Christian Balkenius up to talk about elements of cognition for general intelligence. Thank you, Christian. You still have 15 minutes. We'll just run everything late. Thank you. If you haven't joined the room yet, if you could, that would be great.
Okay, I see. That's better. Thanks. So I wanted to just discuss a few highlights from cognitive science. A few insights I think can be useful for AGI. This is work done together with Trond and Biros over there, both in red t-shirts. We are the cognitive science department in Lund, also in the cognitive robotics lab. And our main interest is, as cognitive scientists, to understand this thing, the human brain. And the way we do that is to try to read as much as we can, and then try to build models, computational models of all the different parts of a brain, and connect this to large networks. We've been doing that for a while, and if there's time, I'll say something about the actual work we do. But what I wanted to discuss here in a few minutes, just a few things about how we think cognition actually works. This thing is not the computational device in the usual sense, at least. It's not a reasoning engine. But the fascinating thing is that with the right training, it can become one. And in most cases, we're not very intelligent either. But one thing we know is that humans are very general. We can learn many different things. So maybe this is not the way to get to intelligence or super intelligence or anything. But if you want to look at what makes sort of us so general and able to function in so many different situations, I think it could be useful to look at the human brain. So one important factor here, of course, is that the brain is not on its own. It's in a body. The only reason we have a brain is because we have a body. The role of a brain is to keep us alive long enough to reproduce. So about 30 years or so. The rest is just luck. But it's even more. It's not just the body, we also have an environment. We interact not only with our body, but also with everything around us. Usually doesn't look like this, but you get the idea, I get. So today we talk about this interaction quite a lot. We say that cognition is embodied, so the body is a part of a cognitive system, much more than you would think. Especially, I mean, for academic, it's maybe not, but in most of your life, the body is the part of the thinking. That's why I'm waving my hands here. Shouldn't be necessary, but I do it anyway. And it seemed to help both me and perhaps you as well. We're embedded in an environment. People talk about an active cognition. That's the idea that we are coupled to the environment. So what we're controlling is not just our mind or our body, but we're actually controlling the environment. So what I'm doing now, I'm trying to get you to synchronize with me, trying to change your minds, change your trains of thoughts. And when I succeed, we actually synchronize our movements as well. At the end of a sentence, many of you will blink in synchronicity, for instance. So we have this coupling. It's more obvious when you are manipulating objects or things like that, but it also goes for social interaction. Cognition is also extended, and that means that some of the cognition is not in the head, it's outside. It's fairly obvious if you use pen and paper, for instance. So you offload some of the thinking to this external device, or to your computer or whatever, or to a stone that you move around, or you make some marks in the sand or something like that. So the complete process is not internal, it's also in the body and in the environment. And it is this complete system that we try to control. So how do we do that? Let's start from the lower systems in the brain. That's the reflex systems. Of course, you know about simple reflexes like just keeping the arm straight even if someone pushes it, or reflexes that makes you avoid things. Different types of input-output mappings. But this can be actually much more complicated. We have everything from very simple movements to actually goal-directed movements. We move towards things or away from things, or move a part of a body towards something, or where we incorporate the environment and move objects around. So the important thing about most of these reflexes is that they are goal-directed. So like the smallest pieces of behavior are goal-directed. They're moving towards or away from something. They're also usually adaptive. So we get better over time at moving our body or influencing the environment. And one way to think of this is as a set of heuristics for handling the world. It's like the starting point. We don't start from zero when we are born. We have these not finished reflexes, but preparedness for doing different things. So it turns into behaviors over time. So the set of reflexes we have also bootstrap learning. So they make us do things that makes us become better at doing other things. This is a talk in itself, actually, but this is what. So what's the next level? That's to actually learn how to influence the environment. It's not learning to do, but learning to engage with the environment in a certain way to obtain certain effects. So one concept that's very influential here is the idea of affordances, which goes back to Kurt Lewin a long time ago, about 100 years ago, which was picked up by Gibson later on, so we should probably have heard about. And now something happened. Okay, yeah, it's back. So the idea is that the world or the environment suggests different possible actions. And we can then select to interact with the environment in a certain way. And we shouldn't really view this as actions, but rather as a way of engaging with the environment. So we couple our body and our brain to the environment, and we can do that in different ways. So it's like a control system more than like an action-based or sequence-based system. Most of these things are learned from a single trial. It's not that we have to try a million times to do something. We usually succeed the first time. It just takes a long time and we're really bad at it. But when we get better, it's very seldom trial and error. That's only the case when we have no idea. So seeing a stone and having some sort of tool, there are always these different things we could do and change the environment by interacting with it in various ways. So what's next? Yeah, when we engage with the environment, we also capture the structure of the physical reality. And there's a lot of structure, a lot of systematicity. So instead of starting with systematic reasoning or something like that, we learn that from and interacting with environment that constrains what we can do and can't do at any point. So it's more like, instead of starting with reasoning rules and slowly learning common sense, it starts in common sense. And maybe if we're lucky, we can learn to reason later on, some of us at least. So one influential idea here from mostly Jean Piaget is the idea that this physical concrete interaction with environment gets slowly internalized. So we start doing physical things in the environment, but over time it gets moved in. So it's like we have a coupling with environment that gets decoupled, and we can then do the same things internally. And according to him, that's the beginning of thought. And I think that's a fairly reasonable assumption. It seemed to work like that. I showed a picture of Vygotsky as well, who had similar ideas, but for more social interaction and language, where it starts as a shared activity, but is then moved into internal language and internal thought. Okay, final level here. There are hundreds actually, but I have time for free. So the top level control of the system. So if we have this kind of loops coupling the body to the environment, suggesting different actions, without any additional control, we just do random things. But as you all know, we have to teach children to stop doing things. We don't have to tell them to do things. We have to tell them to stop doing things most of the time, at least after a certain age. That's what our sort of top-level control system does. So one part of it is to select ways of interaction with the environment that move us closer to desired goals. So mostly the basal ganglia is involved in that. We also have anticipatory systems that continuously track the whole system of us and the environment. So it's like tracks, but it's tracks slightly ahead. So to be able to do anything, we have to predict maybe a second into the future all the time, sometimes more. So we don't react to what happens right now. We react to what we think will happen in a second, perhaps, or half a second, but depending on what it is. That also goes for expected rewards and things like that. And then we have a thing called executive control, which is usually divided into working memory set and inhibition, which are three terrible words. But basically it's about maintaining state over time. So things that are used to select what to do is not only here and now, but also what happened a while ago. Set is basically about selecting the appropriate types of interaction with the environment for the task we're trying to do. So it's like task selection. And finally, inhibition, that's the mechanism. We suppress the different control loops that are not useful right now. So the world pokes us with all these different possibilities, and we suppress those that are not useful right now. So what else is there? Yeah, quite a few things, but I think this is maybe the most important mechanism to get to something that's similar to cognition. So I just wanted to, for 1 second, say how we're working on this. So we started building a framework for large-scale brain models 20 years ago. It's now about 350,000 lines of code. 10 years ago, we started to implement this in the humanoid robots we're building in Lund. And we made a lot of small models of all the different kinds of things I talked about today, and a lot of other things as well. And now we are starting what we call the BAM architecture, actually putting everything together. And with that, I thank you for your attention.
You very much, Christian. That was riveting and prompt on time. And we're going to take questions as we go, 1 or 2 questions only, either from the room or online. And you are first.
You surprised me by defining cognitive science as about the brain. I would think that neuroscience was doing that. In my university, we decided to base cognitive science in computer science and to unify mathematics and philosophy. Of course, the second point you've made that I find a little bit controversial was that brain is not a computer. When one of the top universities decides to reveal their current research, that would become much clearer why not. So just 2 cryptic points, but wanted to mention.
Yeah, I don't have so much of an answer as a comment. Of course, you can decide how you want to study this. And there is a traditional way of studying cognitive science is from a more computational approach. That makes sense in many situations, but I think you end up in the wrong type of models if you start in that from that direction.
Yes. Thanks a lot, Christian. Yeah, so I just have a question about your BAM model.
Yeah.
How do you model the environment in your BAM model?
That's why we have the robots, so we don't have to do that. And that also constrains the kind of models we can use. So we have to work in real time and learn in real time as well. So we can't have a model where we simulate millions of trials. It has to be very fast. So that's one way to keep it sort of realistic in that sense.
Thank you very much indeed. Let's have a round of applause for Christian Balkanius. Thank you very much. And next up, we have Kristen Thorson on explicit, goal-driven, autonomous self-explanation. Thank you, Kristen.
Oh.
Good morning, folks. Pleasure to be here. So, yes, I know my title is a bit of a word salad, so let me try to put some sense into this jumble in the next hour or so, right? No, just kidding. So we could start by asking, if it works, what's there to explain? Why is explanation even on the menu here? Well, it turns out that the more complex these AI systems, control systems, whatever you call them are, the more important it is to know how they work, because otherwise you can't trust them. So we call it self-explainability if the system itself can actually make arguments for why it does what it does, why it plans what it's going to do, and why it did what it did. And this does not come for free. So that's why we want to look at explanation. The next question then would be, what is explanation? Well, let's just do some groundwork here. We're given a world with some elements in it that follows a set of rules. And it may not be fully understood. It may not be fully known. It may even also be somewhat non-deterministic. In some circumstances, given certain original situation and an impulse of some sort, there's a transformation that happens. And we humans call this an event with a particular outcome. And that's, of course, arbitrary based on our goals and needs, what we call an outcome, because that's just an endpoint that's convenient to talk about, right? So explanation really is the dissection and reconstruction of that scenario in some way. So explanation involves dissecting the parts of some parts of such a transformation and tracing essentially, or selecting the important parts of it, the ones that you consider relevant to an explanation. And of course, this dissection and reconstruction, it actually, how you do it depends on the goals of why are you producing this explanation. So that's an explanation in a nutshell, the way we conceive of it. So an important point here is that explanation is purpose-driven, and purpose means essentially you have some goals about highlighting and dissecting, and here are the sub goals for that high level goal. So let me go through them quickly, and because we come back to them. When you give an explanation, if there's a reason to give the explanation, it is because you're trying to highlight or identify unknown variables or patterns, unknown causal factors or causal chains, or unknown errors in background assumptions. So this is basically the bottom line of it's a full disclosure here. This is the point of our paper, to improve or prove understanding. And we don't necessarily mean that in the mathematical sense, although I suppose it could be, but more in the sort of commonsensical sense, to demonstrate your understanding. And there are some sub-goals here, and these are the sub-goals that we mentioned before. That is to highlight or identify unknown variables, patterns, causal factors, or causal chains, and background assumptions. But that pushes the question a little bit further out, and now we are left with another phenomenon called understanding. So let me explain that. No pun intended. So we have here a rainbow of types of knowledge, and I laid it out this way to explain it. So we have the type of knowledge on the left-hand side, in the middle, what it enables, and then how to make use of that on the right-hand side. In the center, you have correlation. This is the most fundamental source of information about anything. This is, or you could say, this is the most fundamental source of information about regularity. But it's also, yeah, and let me fill in these. So this enables you to do prediction. With only correlation, you can do prediction. And the way to do that would be to generate hypotheses about what's going to happen next. But unfortunately, that is not enough to get stuff done. To achieve goals, you have to know about causal relations. These are regularities about, when I see an A and a B together, it's not that they just happen together all the time. It's that A actually causes B, and then B is a result of A. And so if you want to get an A, it's not enough to have a B, because the arrow is from A to B. And that's good for getting stuff done. Now, compositional knowledge is when you have a network of these causal relations. And that allows you to compare and contrast, make plans, and many other things. And at the top, you have basically a cumulative causal relational model set, where you have fully described a particular phenomenon with potentially the smallest set of models that you could get away with. So now, note that essentially, if you have one level above the lowest one, i.e. causal relations, you actually subsume the level below, and so on. So, so the highest level here of modeling, it subsumes the other levels. And it doesn't go the other way. You cannot work with causal relations if all you have is correlation. So that goes all the way up. And this is where understanding lives. It's at the top level. So that's why understanding is actually key to AGI, because a model set, essentially a composite model of a phenomenon, allows you offline manipulation of that phenomenon. And deepening an understanding really means improving that. So let's talk a little bit about models. So a model set, I mentioned this a few times, essentially a phenomenon phi and a model set of that phenomenon is verifiable if it allows you to make good predictions of that phenomenon, to produce effective plans for that phenomenon, to recreate the phenomenon, and to explain the phenomenon. We are really talking here about pragmatic understanding. And of course, the common sense use of the term understanding has various meanings. But the completeness of that model set and the accuracy of the elements in that model set, including the relations, is what allows you to have an understanding. So really, understanding is a key principle for autonomous acquisition of knowledge, for honing that knowledge, for updating that knowledge with new information, and so on. And an AGI system really has to have the ability to deepen its understanding, i.e. to do this online all the time. That's at least on our list of requirements for creating an AGI. So now back to explanation. We said this already. Top level goal of explanation is to improve or prove understanding. And this is the method. And the cool thing about empirical explanations is that if they rest on falsifiable hypotheses about causal relations, then they allow you to create micro theories or experiments that you can go out into the world and test. So, because they allow you both to do deduction and abduction, you can actually test things. You know, does that look like a light switch? Well, let me press it, see if it does it. And we do this all the time. And we do it by essentially creating hypotheses. And we've gone through these before. Essentially, the management of these kinds of hypotheses is an explanation process. And that allows you to essentially become generally intelligent. Because if you can't manage a large set of hypotheses about a diverse set of things, well, you're not going to be general. I've said so much, as much about this in my paper on explanation hypothesis, which essentially just boils all of this down about explanation in a very convenient, accessible way. So in summary, basically, the purpose of explanation, according to our theory, is to improve understanding. And if you have a physical world that regularly presents novel data, the intelligent agents in that world must be able to handle novelty. And so if they have to figure out novel stuff, they have to model their experience and they have to model their modeling of that. And that requires a lot of hypotheses and a lot of management, including, you know, the dissection, identifying variables and patterns, causal chains, and so on. And the explanation essentially relies on a defeasible ampliative reasoning mechanism that includes induction, deduction, abduction, and analogical thinking. And that is what powers general intelligence. Thank you.
Thank you very much, Kristen. I certainly learned. Oh, we've got 1, 2, 3 hands in the room.
That was very clear. Thank you. So I've seen a very similar kind of, hierarchy that where you put explanation puts counterfactuals. And I'm wondering, this is, Pearl, but back to Lewis and so on. I guess I'm wondering whether you agree with that, which I think probably no, and like what beyond counterfactuals would you want explanations to do?
So counterfactuals are just one way of dealing with information and situations with a variety of potential explanations, i.e. potential ways of working, right? And so there are other things, than counterfactuals. Analogies is a big one, and how you isolate causal relations, because so Pearl doesn't really explain how you generate these causal networks, and that's what you need to do autonomously to handle novelty.
Thank you for your talk. Maybe on the more pragmatic or practical side on the metrics, I think sometimes there can be these pseudo explanations where you sort of define a trust metric and then generate explanations to make like the human trust you, but it might not have anything to do with actually explaining. Can you comment on metrics?
Yeah, that's why we require verifiable explanations, and they have to be falsifiable, because you can always find evidence for something, but if you falsify, it's wrong.
Thank you for the talk. In terms of general intelligence, according to Michael Levin's studies, even human cells demonstrates intelligent behavior. What they think, understanding of knowledge is requirements for the general intelligence, or it is just emergent phenomena?
What is emergent?
Like understanding of the knowledge is the requirements for the general intelligence, or it can be without it?
Yeah. So yeah, it's a very common. It's common in philosophy to, especially recently, as in the last century or so, to say that understanding is an outdated, antiquated term with no actual meaning. And I completely disagree with that. I couldn't be more opposed to that view.
You know where you stand on this one. Thank you, Kristen. Yeah, big clap for Kristen. Thank you very much. Right, our next, we've got one question for Kristen. Sorry, I've just got through on the YouTube. Is that right, Haley? From Jazzbox35. Thank you, Jazzbox35, for your question. The internet is rife with debates of whether or not LLMs understand. What is your opinion? And we understand it may change.
It depends on your definition of understanding. So that's a great question. In our definition, understanding is a process. So you couldn't really talk about a frozen system understanding anything. It is more like a giant lookup table than anything else. And it goes actually to the question of sort of how does a general intelligence learn new things, and how does it deal with novelty? And any let's say systematic learner worth its weight is gonna have some regularity in how it extends and appends and mends its knowledge. And this is part of why a learner can trust its new knowledge that it's acquiring. So so explanation really is not just for a third party. It's actually even though it's not allowed, you know, even though the system doesn't necessarily speak it out loud, there are, you could say, when we think like, why do I think that no person can be in two places at the same time? In the traditional physical definition of you know, the atoms that make up the human. And it's based on a lot of experience, but also there are some explanations behind it. If it's like this, this couldn't be the case, and so on. And this is clearly not, at least to me, how LLMs produce their behavior.
So in a nutshell, are you saying no?
Yes.
Thank you.
I would say, so I mostly agree with that, but I'd point out about a frozen system, like in few shot in context learning, it's not a frozen system, right? The learning is taking place in the activation space. So if there was understanding on the time scale, we normally think about it in human cognition, it would be in that activation space learning, right? Which isn't frozen, and is where the closest thing to emergent seems to be happening in the dynamics of LLMs.
Yeah, fine. Let's go with that notion. I think, though, ultimately, because of the way that the LLMs learn and are trained, they're really just pretending to understand. So they're very good at pretending to understand. But that is an opinion at this point. That's a hypothesis. I don't have the paper to give you where I prove that view. So that remains to be seen. And I'm open to being wrong, but I think I'm right.
For what it's worth, my intuition is they're 80% pretending to understand and maybe 20% actually understanding by my own intuitive feeling of these concepts, which makes it weird and complicated. But indeed, I don't have empirical validation to prove that either. And I'd rather spend my time building what I think will be an actual AI than probing the precise details of these systems. So.
Yes, on that point, we absolutely agree.
Brilliant. Thank you very much indeed, Kristen. Thank you, Jazzbox35, for a great question. Now we'll just hand over microphones, and next up we have Robert Ray in the room here. in Stockholm. Thank you for joining us, Robert. Robert's going to talk about computational level analysis of constraint compliance for general intelligence.
Perfect.
Thank you. Give him a warm welcome.
Thank you. All right, thank you very much, everybody. I'm really happy to be here. I appreciate you being here. What I really want to talk with you about today is how can we get agents to follow the rules? And when I think about rules, I think about human systems that we live in. And we live in a world full of rules and more generally constraints, that things that constrain our behavior, lots of different contexts in which we interact in the world, and lots of different places from which we get rules. And humans are pretty good at dealing with all these rules coming from lots of different directions and being able to more or less follow the rules most of the time. Sometimes we deliberately don't follow the rules, but our AI systems really don't have any of that capacity today to understand these human-like rules in a very general way and to respond and to adapt to them, especially in this multi-contextual situation. So many of us learn to drive on the right, some of us learn to drive on the left, but when we move into another context where the opposite is true, with just a little bit of experience, most of us can succeed in that new context without a lot of issue. We go from one culture to another culture and we're, become aware of the rules. Maybe we research those rules ahead of time, but understand the norms around cultural interaction in a different place than we come from. And we can choose to essentially adapt to those new rules in that new place. And I want to mention rules versus constraints in an English language context. Rules can sort of imply a very kind of fixed notion. So I'm going to use the word constraint instead of rules just to kind of get away from that notion of an explicit thing that's written down, but certainly one of the things that we're interested in is rules as laws and things like that. Another thing about these contexts and the constraints within them is that they change all the time. And so not only do we have to have systems that understand the rules, but they have to be adaptive to the fact that the rules are going to change. So what we're interested in as a long-term goal for a research project is really kind of understanding how these systems can follow the rules. And I want to contrast that to these narrow, what I would characterize as narrow AI approaches that, well, one of the ways that you can solve this problem is by changing the rules, right? We've all heard the story that we could have autonomous cars tomorrow if just humans didn't drive. So that would be one way to solve the problem, but it's not really solving the problem of how to follow the rules. Similarly, we could just say, well, this system only works in this specific context. And that would be a way in which to, achieve some kind of success, but it wouldn't be the same as being able to have systems that could freely interact in the world that we know and live in. So why is this problem difficult? And really it comes down to my inexact and imprecise phrase of systems of constraints and rules are messy. And what do I mean by messy? Well, I can't see and know everything in the world. So if I have a set of rules, but there's unknowns in the world that would affect my compliance to those rules, then I can't know that whether I'm compliant or not. We live in worlds where mistakes can sometimes have catastrophic consequences. So it's really important to be aware of what those rules are if they can lead to catastrophic situations. A lot of rules sort of imply the general case or the non-exceptional case, but they don't really explain all the edge conditions, or they don't really say this is the context in which this rule applies. Another issue is abstract and poorly defined constraints. So I want to harken back to Professor Schinke's presentation yesterday. Use caution near pedestrians. That's a rule that we all kind of probably learned when we were learning to drive. But it really depends on what does caution mean, what does near mean, and what is a pedestrian. And we saw yesterday in that talk that tragedy can occur when you have a misunderstanding in an AI system about what that means. In this case, the Uber example from yesterday was not really understanding that pedestrians can be in places other than crosswalks. Also yesterday, we talked about in Professor Ingvar's talk about, sort of humans don't always agree on what the terms are in a field. They come up with these dialects that sort of say, this is the way I'm going to use this word. So how can we have AI systems that are compliant to these rules when humans themselves don't agree with the rules? So that this abstract, poorly defined constraints really causes a lot of issues with thinking about how we can have systems follow rules. And lastly, all these different contexts in which we find ourselves are going to create situations in which those rules interact with one another. So the system of rules that we live with as humans is in no way coherent. And so AI systems are also going to have to be able to deal with systems of rules that are not coherent. So our general notion of the way we're attacking this problem is something we call constraint compliance. That's just coming up with strategies that allow systems to effectively deal with these systems of rules and constraints. Some of the things that we think are really important are that this constraint computation is happening all the time in all situations. It's not you think about this once, you understand the constraints, and then you go forward. The world is changing, the constraints are changing, and so I have to be thinking about this on a moment-to-moment basis. That means it's got to be an efficient approach. Another thing which might be controversial to some of you is that we think that it's got to be a satisficing approach. By satisficing, I mean, I do the best that I can with the information I have at this moment in time. So while verifiable systems or provably correct systems are really important in some domains, if we really want systems that go out into the world in sort of a free way, then we're going to have to come up with some way of trusting them to try to make good decisions in that moment and not being able to provably verify that they will behave appropriately, because it's just going to be impossible, just like it's not possible for us to prove to ourselves that you will react to a certain situation a certain way. And then finally, we will need the systems to be responsive to these new contexts, new goals, and so forth. And that means, hearkening back to the presentation yesterday about DNNs, is that preparation is really important. Training, understanding the problem, all that would be important, but it's not at all sufficient. The world is non-stationary, it's going to change, and anything that I do in a training context can carry over, but it's not going to be sufficient. So what I want to do next is sort of briefly talk about the scope of this problem in the context of a computational analysis. So some of you might be familiar with this notion of the three levels. We are definitely interested in the algorithmic and implementation levels. I'll give you, one slide on what we're doing at these levels. But really today, I want to talk about this computational level, understanding what is the goal of this constraint compliant function that we're talking about. I'll walk through a little bit of details in terms of a functional role and then briefly talk about the processing logic. I just don't have enough time in this talk today to go through the details of the processing logic, but it's in the paper. So imagine we have an agent that doesn't have any constraint compliance built in, but it's got goals that it gets from someplace, maybe internally, maybe externally. It makes some decisions relative to those goals by considering a space of possible things it might do. That's the cloud. And then from those candidates, it selects a choice. So when we add constraint compliance, one simple initial way of thinking about what that is doing is it's saying, well, some of those places in the decision space from the point of view of my constraints are, we can say, prohibited. I don't mean that in a strong logical sense, but less preferable. The green ones might be permissible. You might even say obligatory in some cases. And then there's shades of gray amongst these. So some of the minuses are less desirable than others. And then the selection process is really changed now because the selection process has to take into account both what you're trying to accomplish in terms of your goals, but also these constraints. But the picture gets more complicated because I mentioned the system of constraints. So once I have a system of constraints, then any specific candidate can be a negative choice or a positive choice from the point of view of any individual constraint. So that then leads to needing to have some kind of conflict mitigation strategy. You could think about this in a number of different ways. From, there's various kind of ethical reasoning approaches that would be appropriate there for the conflict mitigation strategy. And this still isn't quite enough because I mentioned that you can't perceive the whole world all the time. So sometimes what you have to do is extend your decision space because you have to gather more information to understand whether or not you're compliant with what's going on in the world. So what I want to do is I'm going to briefly mention this processing logic. Again, that sort of walking through this detail is in the paper, but I'm just going to focus on one part of this pipeline, which is where we've chosen to kind of really dig into some computational implementations and the notion of what we call a partial grounding. And the idea behind a partial grounding is I've got a constraint that I understand is relevant to my situation. I'm in a situation, but I don't quite have all the details to understand how this constraint exactly fits into my current situation. So I have a 16 or 15-year-old who is learning to drive at the moment, and he literally came home from his class, driving education class, and he said, they told me to maintain a 3-second distance when I'm following on dry pavement. So for those of us who are experienced drivers, you might kind of have a sense of what that means, but imagine 15-year-old kids sitting in a car for the first time, trying to understand what that means. And it means that they're going to be constantly looking at the car in front of them, looking at their speed, trying to evaluate, am I behaving consistently with that constraint? And that's exactly this partial grounding problem that we're trying to solve in the agents, that we really would like the agents to be able to understand, I need to make a measurement to understand whether I'm acting in a way that's consistent with my constraints. So we have a current implementation. I'm not going to talk more about this today here other than this, which is that one of the things that's really important is to understand when you actually want to do this, because you could spend all of your time as an agent evaluating your constraints. You can't do that. You've got things I got to do. So you got to be smart about when you do this. And then when you decide you have to take one of these measurement goals, then you have to decide how does that fit in the larger framework of the task and the goals that I have. And then really importantly for us is to think about how do we turn this reasoning process into a recognition process through some kind of compilation so that we don't have to repeat that reasoning over and over again. And that's exactly, in my mind, what happens as an experienced driver. You don't think about that constraint all the time about how close you are. You sort of learn what normal is. Lots of other problems in the paper. I'm happy to answer questions about these, but I think I probably need to wrap up. So the key problem that we're thinking about is we'd like to have generally intelligent agents be able to follow the rules as they exist in the human environment, even when those systems of constraints that they encounter are messy. We think that a continuous, efficient, adaptive process is necessary to do this. And in the paper and in some of the work that we've done today, it's really trying to understand what some of the key algorithmic and representational needs are for this problem. And then in terms of what we're doing in the future, we're implementing pieces of that pipeline that I briefly sketched, where we think that there's new work that needs to be done to support that. And then one of the other things that we're doing is trying to demonstrate the same computational approach in multiple different test beds, one related to safety, one related to ethical concerns and task performance domains, to show that regardless of the frame from which you think about these constraints, we can sort of use the same overall reasoning process across all of them. All right, thank you very much.
Thanks very much indeed, Robert. That was fascinating. Questions in the room? 3. Let's shoot them fast.
Hi, thanks for your talk. To me, this is still quite scary in the sense that I see how you want to let the agent think about certain things, but at least the framework in which this is done, I want to be verified. At least the meta framework, I want to be able to have some guarantees on how long the agent can think about this. Can the agent use this framework of fuzziness to avoid its actual responsibilities and its actual takes on things? Thank you.
Yeah, so that's great. I chose to say what I said a little bit provocatively on purpose, because a lot of the work that's been done, and especially in the last decade, has been really focused on this provably correct stuff. I think Selmer had a paper where they sort of critiqued some of the work that was done earlier, sort of looking at some of the provability aspects of this. But I mean, one of the things that I would counter would be to say, if we have general intelligences that are coming, and it seems like we do, and a lot of conversation about the last day has been about that, it would be better to be able to understand how they might follow the rules, where they might break down, how they go about making their decisions, than for them to be a pure black box. So, I mean, we can also say that it will only work in this particular context in a particular way. But I guess my sense is that people are going to put them into a context in which they weren't designed. So just like well, anyway, I'm not convincing you, so I'm sorry, but.
I think that having a rule following component and some facility to interpret, language as rules and compile them down to rules and then make sure that we're following the rules is important. But I think, survival in people's lives depends on determining which rules to follow and which rules to ignore. For example, you have different methods for crossing the street in New York City versus Los Angeles and versus Stockholm, because I'm trying to figure it out here too. So anyway, so, you can't follow all the rules as well. Even in driving, we know that there's so many rules to follow, and, you're breaking rules all the time when you're driving on the highway or whatever. So, and my last thought was that there's this human biases wheel, and you have a lot of biases that people have, and all these biases actually help constrain action, and so it's a matter of kind of determining when to follow the rules and when not to follow the rules. What's your thought on that?
Yeah, absolutely. So one of the things that will be really important for this kind of work long term is really understanding, and there's a tension. I skipped over a little bit in the talk, but there's this tension between what kinds of knowledge that you have to assume that you have available to the agent versus how strongly you can expect it to be intelligently compliant with the rules. And when I say intelligently compliant, what I'm trying to get across is that not just sort of having a list of rules and I'm going step by step and saying, I never will break this rule, right? I'm always going to wait for the green light to come on before I cross the street, right? If you walked around Stockholm the last day, the folks in Stockholm do not wait for the green light, right? And that's part of this norm process as well, that it's not just the rules, it's also the social norms and the context in which these things occur and being sensitive to those. So I would say, that's not our current focus in the work that we're doing, but it's absolutely part of the vision for what we're doing. And it's going to be important to achieve this in a way that people would find trustworthy and willing to have agents running around in our world.
Yeah, so in this regime of fuzzy constraint satisfaction, doesn't something like GPT-4 already do some sort of general fuzzy constraint satisfaction? And you have any comment on how that's related to your work?
I hadn't thought about GPT-4 as fuzzy constraint satisfaction. One of the things that we are certainly looking at in terms of this work is thinking about how language models, we can exploit language models for that internalization process. Like, for example, we have some laws and we'd like the agents to be able to be sensitive to those laws. And so can you just sort of read in those laws directly from text and using a language model start to get an encoding within the agent that's more or less consistent with that law. So one of the things that's interesting about that from the fuzzy concept perspective is that in many of the systems today, you're depending upon a few people who have decided this is the meaning for this term, and they sort of encode that meaning. One of the, we don't have any proof of this yet, but one of the things that's potentially interesting is, do the conceptual information that you get from a language model represent a little bit more of a consensual notion of what that concept means, so that if an agent encoded something that was a lot like what was in the language model, is it less likely to be sort of on the edges of the distribution in terms of the way that concept is interpreted? Don't know yet, but that's one of the things that we're interested in exploring. Thank you.
Thank you very much. Great discussion. Let's have a round of applause for Robert. Right, next paper is from Patrick Hammer, and I just want to very briefly introduce Patrick because he's on the organizing committee here for today. He's an AI researcher and currently postdoctoral fellow at Digital Futures at Stockholm University. And he's here to talk to us about comparative reasoning for intelligent agents. Thank you, Patrick.
Thank you very much.
Test. Okay, works. Just want this to be full screen. Okay, so I will talk about a topic which I always wondered: is it more about perception or is it more about cognition? And actually, it's not easy to answer if we ask ourselves at what point in the information processing in the brain does reasoning get involved? At what level does this happen? It's actually not an answer that we know at this stage, but there are some capabilities which seem to be on the perceptual side, which seem to require some kind of reasoning capability even there. And today I will talk about particularly one aspect here, which is comparative reasoning. When we see two things, how can we compare them perceptually? How can we reason about commonalities and differences between objects? And this is a joint work. There's many people involved here, entire team and collaborators, sponsors from Cisco, Hugo Ladderby here, and also our entire team. Some authors we could not even put in the paper because of conflicts of interest, so we had to be very, so here I included everyone involved, as you see, many people who contributed to this work. And if we look at the task itself, what is it? Comparative reasoning. And it's something which is actually also studied with animals. In psychology, there's this term of transposition. And for instance, you see here this teddy bear performing this task. it's a dog, which is trained to pick the larger circle. And animals like dogs can easily learn and perform this task. And so for us, it's the big question: how can we actually replicate this ability, like in our reasoning system in Nars? How can we replicate this to a degree that it will also not only work in DOE examples, there's some kind, not only in DOE examples, but also on actual robotic hardware. Like if we run this kind of experiment in the real world, can we actually replicate this ability? And so this is about that. From the reasoning systems perspective, we are pursuing non-axiomatic reasoning system. So the question, of course, here is how can the system be extended to support this ability? And in this paper, we have done just that. So let's go into this. I guess it's also here important to point out the larger picture here, because it's really fitting into a wider range of stepping stones which need to be there before this ability can actually happen in like real world scenarios. You need sensory processing to deal with the complexities of real world sensor input. You need some kind of sensory motor interaction capability of the system so that it can actually perform the task, invoking operations. You need some kind of relational reasoning which allows it to perform this comparison between stimuli to carry out the task, to learn and to do it. And of course, there's also a wider picture of how does it fit in with like higher level cognitive abilities, metacognition, self-awareness, like how does the agent relate itself to others and so on. Whether this is also related to this, we will see. But so far, this seem to be some of the stepping stones which play into this. For Nars, it's a reasoning system which is inherently designed to work in real time, to take in information constantly from its sensors, and while doing so, performing in a way that the processing requirements will not increase with every event it perceives, but remain constant. And also the memory capacity of this reasoning system is strictly bounded. So it has a fixed memory capacity and it will not exceed it. regarding the logic, we use this non-axiomatic logic. You have most of you have, or many of you have seen this in the Nars tutorial and workshop. How we handle which kind of representations the system builds, how it represents relation, and so on. And we have also shown a particular implementation of this reasoning system OpenNAS for applications, which was also the implementation target for this particular capability. The first implementation target to extend it and to implement this comparative reasoning capabilities. And of course, now the question is what is this reasoning capability and how do we build it? So the idea is you have some kind of measurements. Imagine you have a brightness sensor attached to the robot. It gives you just brightness values, for instance, just dependent on how much light falls on the sensor. And so you have some kind of measurement, some kind of numeric quantity attached to this measurement. And then if you have multiple of these measurements, that's where it becomes interesting, because then you can ask yourself the question, is the second measurement larger? Is it smaller? Is it about the same? So we have this kind of relational representation, which allows to specify that a certain sensory value was recorded, and then allowing comparative relations to be built based on them. And here, of course, if you have comparative relations, like if you know one thing is larger than the other, and you probably know there's even a thing which is larger than the second thing, then you can infer that this last thing is larger than the first thing. So there's a certain structure inherent in this comparative relations, which is like transitivity in case of greater than relationship, and also some other like asymmetry and different relation properties. Essentially, if you have equality, then of course also symmetry of the relationship. So that's also what we formalized accordingly. We have built the inference rules accordingly so that it can compare measurements, build the comparative relationships, and then perform further reasoning on top of these built relationships using these relation properties. And here you see the form in the paper, and in the implementation, it also looks quite similar. So it's ASCII representation, but we have quite neat inference rule language specification. And in terms of robotics, that's a quite useful capability. We have since now almost 2 years worked with this transport robot, which has like a camera attached to it. And so for this particular task, we have attached object detection model, which allows it to see object categories of certain kind and where they are located. And within this bounding box, we extract additional information like color information, red, green, blue, and we they can also generate a measurement regarding the bounding box dimensions, x and y size, so that it can actually compare the sizes of the object. So in this particular task, we then instructed the robot to pick the smaller bottle among 2 candidates. And as you can see, it can carry out this task. It will see both of them and make the decision according to this comparative relation. And from a perceptual perspective, there's also a wider story behind this. For animals, as psychologists have figured out a long time ago, they are very effective in learning and conditioning on commonalities and differences between objects. If one thing is significantly different than another in a certain aspect, then this is very salient to the animal. And our control strategy for this perceptual component is similar in the sense often there are many quantities to compare, which ones to pick, which ones to explicitly make it reason on. And here also the same idea. If there are big differences between 2 objects in certain dimensions, then that's something which is probably worthy to reason on. So it's driven by the biggest changes between the objects, and it's also this mechanism is also used to, if it sees a new object, to know which remembered object is most closest. So it always knows what's the most similar thing it remembers, but it also notices the biggest differences to this remembered instances and compared instances. So that's the overall approach here. Also from a control perspective, differences and commonalities are really key, essentially, in one sentence. There are also some other experiments which we have carried out using this new functionality, like some kind of crane robot scenario in a simulation where it needs to control a robotic arm. It gets the location of itself and the target locations and the location of the object to pick, and it will essentially do a more continuous control of this task, because previously Nars was we only handled discrete representations, but here we can actually give the location information in form of a measurement, and then it building this comparative relationships and acting on them. We can give a very brief demo on how this looks like. So at first there's just model bubbling, it doesn't know anything, it just tries operations, jumping around, up to at some point it gets lucky and probably picks it up at the right time and puts it at the right place and gets the feedback. And then hopefully it induces the right hypothesis about what it needs to do for this task, which is to pick up the ball and put it into this U-shaped hole. And it doesn't take too long for it to actually induce this hypothesis and to carry out this task quite reliably. In the beginning, it's still exploring, so there's some model bubbling. It's not always perfect in the beginning, but you will see. You see, it clearly got what the task here is about, and induced the correct hypothesis to perform the task. So of course, live demos are always risky, but in this case, it worked out quite well. So that's how this looks like in the simulation. In terms of functionality, most of the ideas in the paper are already implemented in this open Nars for application system. It's already mostly in there. There are some additional inference rules which we will add and go over them step by step to see which potential things we miss. And yes, if you can, essentially you can already download and play with this functionality that is described in the papers. Thank you very much.
Thanks so much, Patrick. Great talk, and always fabulous to see robots and live demos working out in action. So we've got a question for you from YouTube, from Paul Berger. Thank you very much, Paul. He's asking here, did you achieve specific milestones in your framework from sensory motor reasoning coordination, e.g. Piaget, conservation of liquid volume equivalence as for circa 5-year-old children?
That's does this still work? Oh, okay.
You're still on. I'm just going to repeat that. Did you achieve specific milestones in your framework from sensory motor reasoning coordination, e.g. Piaget, conservation of liquid volume equivalence as for circa 5-year-old children?
Oh yeah, there's one part of the question I can certainly answer, which is regarding sensory motor reasoning coordination. I can say that this capability is very, very mature in a sense that the system can really learn compound conditions, like if there are multiple stimuli to take into account to make a certain decision. It really learns the combinations of events which need to be considered to reach a certain outcome. This is very, very effective. I'm not sure about the second part of the question. Is there some, maybe Michael knows what this liquid. That's true. I guess there's also this question in terms of cognitive development, like Piaget envisioned. To what degree we can replicate this? I would say it's also subject of our experiments here at Stockholm University, also driven by Robert Johansson, my postdoc at Vassar, to figure out which capabilities we have, which ones we miss from a cognitive perspective. So we have also a psychological roadmap here, where which we follow essentially.
Thank you very much indeed. Have we one more quick question in the room, or we'll wrap up? We're about 20 minutes over schedule now. Okay, thanks very much to Patrick. We're going to take a 12.5-minute coffee break. So I'll see you all back here at 11:35. There's coffee upstairs. Thank you. So our next keynote, that was really fantastic. The break, the energy, the discussions. It's brilliant to see us all having such inspiring times. So next up, we have got a keynote, online keynote, and this is coming from Irina Risch. Irina is an associate professor in the Computer Science and Operations Department at the University of Montreal. She holds 64 patents, has published over 80 research papers in peer-reviewed conferences and journals, several book chapters, 3 edited books, and a monograph on sparse modeling. Please give a warm welcome to Irina Risch online on scaling laws, emergent behaviors, and AI democratization efforts. Thank you.
Hi, can you hear me well?
Yes, we can hear you and we can see you.
Okay, great. Okay. Well, thank you so much for inviting me. Thank you for kind introduction. I'm really sorry I couldn't be there due to some scheduling constraints, but I'm happy to be here virtually. And indeed, let me share my screen. Just a second. Okay. So just go to there. Okay. Okay, can you see my screen now? Okay, I see that you can see my screen. It's been projected well, right? Okay. Perfect. Okay, so indeed, let me start briefly with this kind of high-level overview of several topics that probably deserve separate talks on their own. And yes, talking about AGI, we will be actually talking about the most recent kind of advances in large-scale models and scaling laws that many people believe promise to bring us closer to AGI. Interesting behaviors on the way, and also practical issues about how can we train those models if we're in academia or open source communities and compute gap between us and industry is widening. So I'll try to cover all 3 topics that we've been kind of involved in the last 2.5 years, I would say. Okay, so yeah, this is AGI conference. So let's start with the AGI slide, and I probably don't have to repeat it, but we all know that everyone has somewhat different definitions of AGI, and that causes usually sometimes even heated discussions on Twitter. But yeah, to be serious, indeed, it's a notion that indeed different people and different groups define in particular ways. And I will probably just follow somewhat less mysterious definition, which has no necessarily consciousness on that or anything like that, but essentially as practical as possible definition, kind of following what OpenAI put on their webpage a while ago, that essentially you want a system that similarly to human is capable of doing not only really well one particular task like it used to be in narrow AI, but it really should be able to acquire and remember a huge variety of different skills over its kind of lifetime, just like humans do. We can require the performance be kind of near human level or at human level or kind of better than human, but that's kind of more of a detail. So essentially the definition is in some sense more kind of mundane and practical than maybe some people imagine AGI to be. So it's essentially a highly multitask system, or as again, OpenAI would say, highly autonomous system that outperforms human at most economically valuable work. Essentially multitasking where tasks are useful. So if we think about that, like one step back, or I don't know, multiple decades back, what was always the key driving kind of objective of statistics, machine learning, and artificial intelligence lately that kind of was mainly dominated by machine learning goals? It was always generalization, starting with very classical regression where you have a bunch of points supposedly coming from some data distribution, and you want to extrapolate to unseen points, you want to generalize, still assuming that the data come from the same distribution, the IID, all the good old stuff. The next step was, okay, let's push generalization to a bit more, well, general level. So out of distribution generalization was and remains kind of a really hot topic in machine learning and deep learning particularly. We really would like to have systems that are kind of robust rather than brittle to changes in data distribution and can generalize maybe zero shot or few shot. And that closely relates to many other overlapping areas of machine learning and AI, transfer learning, continual learning, meta learning. Settings change, but the key goal is you want to improve the ability of the system to generalize to novel situations and novel tasks, and be able to transfer and abstract their knowledge so that they are capable of doing something reasonable with tasks and data that are very, very far, ideally, from the distribution they were trained on. And recently, literally in the last 2-3 years, we've all been witnessing what some call neural scaling revolution, which kind of makes a huge step in the direction of generalization, and we'll talk about that. But many of you already know that all these large-scale pre-trained systems, with GPT-4 being one of the recent examples, and also many generative systems like Clip, DALL-E, Stable Diffusion, and so on, taking the world by storm and precisely impressing everyone with their generalization abilities, or kind of ability to facilitate generalization on top of them. And indeed, what's going on seemed to be resonating well with a bitter lesson by Rich Sutton, which was essentially talking about previous kind of patterns in development of AI over like last 70 years. Essentially, you start with some specific human knowledge that you put in the system, like rule-based expert systems, say playing chess and putting all their human knowledge in their ontologies and so on and so forth. In a few decades, you have much more compute, much more data, and you have a much more general, rather than kind of specific to this domain methods like massive search that kind of outperform all these systems developed with a lot of human knowledge and inductive biases. And examples keep going on, like chess was just one, well, AlphaGo and so on. So basically the whole deep learning was example of that trend. So you go from kind of handmade features designed for each particular domain, say in vision or language and so on, you go to generic kind of methods like generic architectures in deep nets, extracting those features automatically and utilizing massive compute and massive data that became available. So essentially, that same kind of pattern keeps repeating itself in multiple areas that used to be kind of addressed in machine learning by expert knowledge and kind of developing particular methods, inductive biases, features, and so on and so forth. So what we kind of learned from that and where we're going with that seems to be that we're trying to even further generalize what part of the human knowledge we actually want to put in the system. We don't want to really put too much detail about how we think. We want to build systems that are able to develop those thinking abilities. And we want to make them as simple as possible, as general as possible, but probably not simpler, as Einstein would say. And we would like to utilize basically their scaling properties to see if they can develop the abilities of interest. And that's what we've been kind of witnessing, as all of you know, in the past couple of years, essentially starting with, I guess, GPT-3 in 2020 and neural scaling laws that appeared in like late 2019, early 2020. And since then, there was like exponential growth of this field. That's now the term was coined by Stanford paper, foundation models. So by foundation models, we mean all this very large scale, pre-trained on huge amounts of data in unsupervised way. So they kind of just absorb knowledge, they absorb the probability distribution of data, for example, language. They absorb language patterns by being trained over like tons of data from the whole internet. And they can serve as foundation for building whatever applications on top of them. And just as foundation, they are not only kind of the basis, but they also not yet fully there. You need to build stuff on top of them. Maybe you need to fine tune them and so on. But that's kind of the reason behind calling those system foundation models. So yeah, the history kind of develops as we speak, because there are many models, especially open source models, kind of being trained practically and kind of released almost every day these days. So GPT-3 kind of started the trend, with claim to fame being that on totally new data, new tasks, you actually can adapt and do quite well in few shot manner. So here goes your out of distribution generalization, or basically adaptation to new domains, your transfer. So those systems essentially didn't change much in terms of architecture as compared to their predecessors. They changed in scale. And apparently, the scale of the data, the diversity of the data, combined with capacity of the model, the scale of the model, allowed them to become really good few-shot generalization kind of agents without any particular details built in specifically or any specific algorithms developed for that. So, and the story goes on with multimodal systems, not just language systems, like clip followed, image to text, zero-shot generalization, pretty much on out of distribution image domains, beating state of art, and DALL-E, image generation, and then many other systems, well, stable diffusion and so on, code generation, and most recent, of course, GPT-4, which is now part of ChatGPT, and the whole family of open large-scale models and open data sets. I will talk about the open source a bit later, but like Llama was one of them. And essentially the recent trend is scaling data even more than scaling the model size, which kind of a good news for people who have relatively limited compute and would like to train state-of-art models. What was interesting about the systems was not just kind of the great engineering that went into them, but also the interesting empirical science, almost like physics of AI, about how this behavior of the system can be actually predicted empirically based on so-called scaling laws, neural scaling laws, which also kind of took the field by storm because they were quite simple and quite useful. And many of you probably have seen that paper by Jared Kaplan and his collaborators from OpenAI. And basically, those straight lines on the log-log plot. So essentially that meant that behavior such as test laws, but also many other properties of the systems, I will talk about that soon, they can be described by relatively simple things such as the scaling laws, the power laws. So essentially the power law in a log-log plot is a straight line, and you only need to feed a couple of parameters. And apparently on multiple orders of magnitude, you can predict how the performance of those systems, in this case it was GPT-3, will behave as you increase amount of compute available, data set size, and the number of parameters, the size of the system. So those plots essentially were derived by Jared and collaborators and helped them to kind of steer development of, say, GPT-3 in desirable directions, because basically you can predict among multiple kind of choices that you can take, whether it's hyperparameters or other kind of decisions you need to kind of take when you scaling your system, which decision will be most promising and will give you the best performance if you allow it to use more compute. So the plots essentially mean if you increase compute on the leftmost plot, for example, and for each particular amount of compute available, you allow your data and parameters kind of be whatever you need to get the best result. So basically you try multiple combinations and choose best result. Then the improvements with increasing compute will follow power law with this particular parameters as in the neural scaling laws paper. Similar with different parameters behavior, also power law, happens when the data grow while compute and number of parameters is unconstrained or unbottlenecked. So essentially you can choose the best. And again, similar behavior, just as different parameters, happens when the model size grows, and you can choose whatever amount of data you need and amount of compute to get the best kind of performance for given model size. So that was a classical set of scaling laws that essentially were brought to people's attention in 2020. And since then, there was an explosion of papers trying to study scaling laws of different behaviors in different settings for different architectures and so on and so forth. And the reason the scaling laws are kind of not just academic curiosity, like we would like to know how this system will behave, it's in a sense can be viewed as a very practical kind of investment tool for choosing which methods to select and to invest kind of your compute resources into. And classical example, one of many, was a comparison of convolutional networks that up to like 2020, 2021 were considered state-of-art in kind of image processing, and they're still kind of pretty good. But it was interesting that more generic method, vision transformers, which pretty much uses architectures that has no specific inductive biases that convnets use, was not maybe as good as convnets when the data were relatively small, like say 10 million or 30 million is small, but when the data grow by orders of magnitude, apparently the situation reverses, and you see that vision transformers start to outperform the more specific kind of vision specific convolutional networks. So this is a classical example of kind of bitter lesson as well. So you may invest time into designing specific architectures with specific inductive biases that work best at low scale, but as more compute and data become available, more generic, maybe simpler, non-domain specific methods that also scale well may outperform your specific ones. So this is kind of classical example where scaling laws allow you to see the full picture, and that's why they're important. And if you think about that, why they're important, indeed, you can think about multiple paths to AGI. But perhaps, as usual in nature and in kind of science and economics, the fastest path matters because essentially that's what kind of gonna lead to the goal, and that's what kind of others are more likely to follow, because kind of what exists persists. What is most successful and keeps getting us to the goal faster, that probably will be the path we will choose. Although perhaps there are many, many alternatives, but if they don't scale as well, then the fastest scaling one will win. So again, it would be nice to estimate scaling laws or whatever approaches we're trying. So usually, what can we evaluate given particular methods, architectures, and so on and so forth? We would like to kind of see how not just performance on all possible downstream evaluations, but also other properties such as, for example, alignment, which could involve multiple kind of useful things like truthfulness and so on, but essentially alignment is yet another not very precisely defined term, just like as AGI, which roughly means that behavior of the system may be hard to describe in optimization function, but we want to be able to kind of to steer it to something that will not contradict our intentions and values. And we'll talk about that a little bit later. While at the x-axis, we would like to plot whatever kind of quantity our approach can be bottlenecked by, like what is a resource that might be limited, which is usually compute or say amounts of data. So that's what kind of scaling laws are about, but they kind of started a while ago. It's interesting that people looked into them, but only recently with large compute that really became available and amounts of data, they became also practical. So actually, it's interesting that I think one of the first scaling laws papers was the old one from NeurIPS 1994 by Karina Cortes and her famous co-authors, including Vladimir Vapnik. And the interesting thing is it was also kind of study of neural network behavior, error in that case, basically log error, and they also observed power laws behavior as a function on the x-axis of dataset size. So those straight lines were not invented by Jared Kaplan, but they've been around for a while, even particularly in the domain of neural networks. And well, forwarding all the way to the 2017, another paper by Joel Hasnes and co-authors expanded basically this observation by orders of magnitude, also showing how the scaling laws kind of follow the power law straight line in the kind of middle region, but there could be also regions of slow improvement in the very beginning, say when the data set size is way too small for the model to learn anything kind of useful, so the performance does not improve that fast. And then there is kind of slight break in the pattern where we get into this power law region. And at the end, far kind of in the future with like large amount of data that pretty much may cover the whole distribution of what's out there, the model behavior performance will kind of asymptote. So this was kind of also a hint of what you can observe in terms of several regimes of kind of different behaviors connected by the breaks. And I'll talk about that very soon when we will kind of fast forward to the most recent developments in neural scaling laws. Anyway, so I just kind of wanted to say that the individual observations of scaling laws as a function of data, or in this case, the more recent paper, 2019, it was Clear and also was dissertation of Jonathan Rosenfeld. it observed power law dependence on the model size, on the number of parameters. And then we have Jared Kaplan's paper, which kind of also observed and confirmed both data and model dependent scaling laws, and also added on top of them the scaling law as a function of the compute. There was also many more recent developments. There were, I kind of not showing it here, but there were more efficient scaling laws, also power laws, so-called chinchilla scaling laws, which improved over Jared Kaplan's. But then there was another interesting observation, like besides all these straight lines for the kind of loss, test loss, there are other metrics of performance, especially those that depend on particular downstream tasks. Well, downstream task is basically what you do after you pre-train your model, and you may provide it with kind of prompt asking to make some kind of inference and reply to this prompt and language tasks, or you can perhaps fine-tune, you can do various things kind of downstream. So this plot from the original GPT-3 paper was interesting because unlike other tasks and unlike the test laws, it was a kind of problem where the system was supposed to answer arithmetic questions like 2-digit addition, subtraction, up to like 5-digit addition and subtraction. And what was interesting is that there was a clear kind of sharp transition in the quality of the answers, in the accuracy at particular size of the system. So there was almost like up to certain size system was unable to grok or capture the task, say, of 2-digit addition, but then at 6.7, it started getting better. For the more difficult tasks, this transition happened later at larger system size, but that was kind of interesting plot that started this whole kind of investigation of what can happen in terms of performance on particular tasks changing abruptly and almost looking like phase transitions in physics. Well, I will kind of not claim and not call them necessarily phase transitions. I would rather say it's quote unquote phase transitions, because yeah, phase transitions in physics have particular properties, and unless we kind of make a one-to-one correspondence between what's going on in the neural net and the situations, we kind of should be more careful with terminology, especially if there are physicists in the room. But talking about sharp changes in the scaling behavior as a function of particular kind of parameters on x-axis. Another paper, also a couple of years ago, observed the sharp, rapid change improvement in accuracy as a function of compute in specific setting, again, of like similar to arithmetic type of problem. So it was like a arithmetic model or model or something. I don't remember in the exact details. The point is that the model was being trained on some kind of large table describing the operation. It was a binary operation. The part of the kind of table was given as training data, the rest as test data, and the task was to kind of learn the operation, and the performance was nearly zero until at some point the solution that actually was nearly perfect was found, and the performance was improving very sharply, first on training data and then on kind of validation on test data. So that behavior was called grokking, because the system suddenly kind of groks the task. Somewhat similar kind of sharp transitions were also on the same task observed as a function of amount of data, training data given to the system. But then people started exploring various other settings, problems, and systems, and there was this paper on emergent abilities of large language models, basically showing many situations where such nonlinear kind of performance improvement can happen at scale. So the question was, how do we capture all these non-trivial scaling laws that now go way beyond just the straight lines and log-log plots, basically beyond power laws. So recently we had this paper at Eclair with two of my students, Eden and Shitish, and with a collaborator with David Kruger, who previously actually also was a student at Mila. And the paper basically was trying to come up with a functional form that would generalize power laws and try to kind of one functional form to rule them all. Essentially, this functional form apparently was used before in different sciences, for example, astrophysics, and I guess that's how we found it. So essentially, it kind of describes a combination of power law regions that smoothly connected by those kind of smooth breaks of different kind of sharpness. The sharpness is controlled by parameters of that functional form, as well as the slopes of this kind of power laws and so on. So essentially, it's an interesting generalization which happened to be extremely generic, and indeed seems like so far one functional form to rule them all. So in the past year, essentially Eden and Shitish, they tried a wide variety of different settings, like trying to predict zero shot, prompted, fine-tuned, both downstream and upstream performances. The set of tasks is pretty much covering all that is in the current literature. Essentially, they were just kind of taking the recent papers with all this like foundation models and their performance shown there, and trying to see if that performance can be described by a particular incarnation of the broken neural scaling laws. And it seems like it works quite well on everything from like language, vision, audio, video, on diffusion models. And it not only works on performance, it also works on the metrics for AI alignment. I'll show a few examples. So far, it seems to be really quite generic approach to modeling neural scaling laws. Architectures vary. It's not just kind of transformers. It also works for ResNet and MLP mixer and a bunch of other architectures. It also like works for mixture of experts, for pruned models, for sparsity. And on x-axis is not just data or compute or the model size, but it could be also some other things like context size and so on, and even upstream performance. And the interesting things that you can kind of predict with that, again, go beyond just prediction error or cross-entropy loss. There are various scores that people use in different tasks that make sense there. And it can also apply to like reward and reinforcement learning and so on. So we're not going to go into all the details, but that's kind of the set of previously proposed functional forms, starting from the simple power law, it's like M2 here, with two more sophisticated modifications of that were designed by a couple of papers last year, precisely to try and cover wider range of behaviors. But this is just kind of one example. Like in the table, I'll show many examples in particular plots. It seems that none of those functional forms, even those two kind of more sophisticated, can cover the whole range of behavior and can be as accurate as this broken neural scaling laws, which kind of outperforms them on pretty much all these tasks. And unlike those, it can cover situations such as like inflection points or transitions, and it also can cover even non-monotonic, say, generalization, like basically generalization curves can have multiple bumps and so on. So it seems to be well covered by this functional form, not so well covered by anything that was proposed previously. So now we're going to see a bunch of examples just to kind of get some feel of how it works on wide variety of tasks. And essentially what we have here, so basically we'll have black points, which are the data, say, given, well, training data of the data we fit in the model of this broken neural scaling laws, and then the green points are prediction. Yeah, and actually, okay, so the red line is broken neural scaling laws that was fit to those black points, and then the green is basically what we predicted. So here, essentially, we have example of double descent, non-monotonic curve, and based on the black points on the history, we predict how it's going to kind of develop in the future. The green points, there is a inflection point situation that I mentioned. This is, of course, I mean, it's not a magical approach that can predict this very small number of points far from transition. It has to have kind of large enough set of data or kind of examples of behavior before the transition, and it should be close enough to the transition. Also, it depends on how sharp the transition is. So essentially, there are limitations to this method, obviously, but the fact that at least it's in principle is capable of such prediction is not something that we had available with those functional forms people were proposing before. So it predicts behaviors in kind of multiple orders of magnitude ahead of time. It predicts it for example, models that are also sparse, like pruned models and so on. Just many other examples like distillation, for example, not just pruning. What else? So the diffusion models, not just like language models, but yeah, basically generative models of image. Just some examples. I mean, there is much more in the paper, and basically all these cases covered in the appendix. But also interesting that metrics from like AI alignment papers also follow broken neural scaling laws. And so were also the reinforcement learning kind of metrics in some other recent kind of papers. Anyway, so it kind of works for various modalities, for various tasks. It works also for kind of coding, not just like images and language and so on and so forth. So there are many other examples with audio, video data. Basically what I'm trying to say, it seems like it's quite useful, practical, generic functional form that seems like we found that might be even kind of describing even much wider variety of the behaviors that we previously tried. So at least it's something which is, I think, a big step forward beyond the straight lines on the log-log plot that were unable to capture those interesting kind of emergent behaviors and so on and so forth. Okay. This is interesting and great, but it's all more kind of observational and theoretical. And when we actually want to, in practice, train those models, how do we go about that, especially if we don't have compute available to companies like OpenAI or Anthropic? So what do we do regarding the compute? Because it seems like the straightforward brute force kind of compute leads to such huge improvement in the generalization performance. So how do we possibly democratize AI in a sense, how people in academia and say open source communities can train such models? And one way that we considered was to kind of apply for the compute on government sponsored supercomputers. For example, Summit and Frontier are two supercomputers currently hosted at Oak Ridge facility in US. And of course, I mean, there are multiple other supercomputers in different countries and kind of more being built. So it's one possible path to kind of providing academia and open source with at least much larger compute that they had available before. Perhaps it might not still catch up with the amount of compute that companies have, but it definitely gives you ability to build things that you were not able to build before. And also, we thought that perhaps we could follow the path of the LHC collaboration in physics, basically a high energy physicist building large collaborations, applying for the large compute grants, and together trying to solve those difficult problems. So we kind of joined forces with several other groups interested in open source development. For example, Lion, the nonprofit, well known right now for building, first of all, open source data sets, Lion 5 billion and more coming, and building better version of CLIP than the original OpenAI kind of CLIP using this new data, and many more other recent projects. And Julie Center, where some of the Lion kind of members are. Also the open source community, basically Discord community, Luther AI, that created several kind of open source models that many other things are built upon right now, such as GPT NeoX code base that not only us, but practically many other open source projects actively use right now. There are also multiple other communities, and this is very incomplete kind of picture, and more kind of joining forces recently. So we're trying to kind of grow those communities and also jointly apply for compute in multiple countries, not just for the kind of US Compute Summit and Frontier. So this was our kind of last year project, last year proposal that was accepted, and we kind of received basically close to 6 million GPU hours on Summit that we currently kind of using for some language and some multimodal kind of model building. There are also interesting projects on trying to generalize to other modalities like time series. And in general, the ultimate goal is, of course, foundation models that are capable of working with a wide range of modalities, including not just text and images, but audio, video, time series, decision sequences, such as like in decision transformers, and making those models interactive, essentially creating something we can call open chat X, where X is a highly multimodal generalist agent. So most recent kind of success story was training jointly with Stanford Research for Foundation Models and multiple other collaborators, and a company together that's kind of was founded by Percy Young and others at Stanford Center for Foundation Models, also ETH Zurich. So in collaboration with them on Summit, we basically built the medium-size open source models that essentially try to reproduce Meta's Llama, kind of recent medium-size suite of models that perform quite well and actually on par with much larger previous language models, due to the fact that the amount of data they trained on is considerably larger and more diverse than the data, for example, the previous large models were trained on. So the trend of reducing model sizes, well, reducing still to something like 7 billion, maybe 20, 60 billion, but not necessarily kind of 175, 76 billion like the GPT-3 and predecessors, but increasing the amount of data more than increasing the size of the model seems to be still promising direction, and people kind of coming up with very good medium-sized models. So this was one of them. And at that moment when we released it, it actually was state-of-art using particular benchmark like Helm, and it was outperforming other 7 billion versions of language models available kind of on the market. Well, basically comparing to other also open source models of similar size. And part of the effort was, of course, it always goes hand in hand, releasing large data sets. So anyone can also use them to build their models. Yeah, so actually Meta might now fully release their llama model, so it will be a larger family of llamas. The previous kind of release was non-commercial, so you couldn't build anything on top of those. That's why there was so much activity trying to reproduce Meta's llama or improve over that. So this is just kind of one example. Another example is we're trying to build those interactive models that are, for example, able to take image and text as an input and produce text. We started with now somewhat older system called Magma, which was publicly available, trying to improve it. And besides just scaling to improve it, kind of capabilities of generating more meaningful and interesting text, we're also trying to focus on making sure that the models are indeed aligned with our kind of values and notion of like what the ethical response would be. And they do not answer questions, do I help old lady crossing the road, like the earlier kind of small version was answering. So that was that original Magma. And when we realized there are quite a few situations when it can give this questionable answers, we basically, besides scaling that system on Summit, we also try to kind of fine tune it with human feedback and essentially try to steer its behavior with actually a relatively small number of good examples. It apparently suffices to change behavior into desired direction, but it's still quite open research question. As you know, the AI alignment in general is far from being solved and perhaps is becoming one of the most active areas of research in kind of large-scale models. So there are various speculations whether capabilities of the model versus alignment are contradicting each other and whether increase in capabilities has to lead to decrease in alignment, or perhaps you can accelerate development of capabilities while also accelerating improving alignment. I am more of an optimist, and I think that the latter situation is quite plausible. So, and we don't necessarily have to go into extremes of AI alignment kind of reasoning that large-scale models necessarily going to be kind of evil and going to destroy the humanity. So I think it's a little bit premature to jump to such conclusions, but improving their ethical outputs, improving their robustness to distribution shifts, which was very important for AI safety, and kind of trying to develop methods that can detect changes in behavior, especially these emergent behaviors, can predict them well and perhaps steer in the desired direction. There are many open, interesting questions in this area. So I guess, yeah, I was not checking time, so please let me know if I'm over time already. But at higher level, with all this kind of recent joint collaborations with open source communities and different universities, trying to get more compute, essentially we trying to achieve and hopefully both capable but safe, robust, and aligned with human values, kind of large-scale general AI systems. And well, needless to say that on top of these foundation models, you can build multiple applications. You can fine-tune them for your specific domain. You can also apply them to various areas where data might be somewhat limited. A good example is, for example, healthcare, where you don't always have tons of data like text on the internet, but pre-trained model can help you boost your few-shot kind of generalization. And obtaining access to large-scale compute resources is quite essential for that. Supercomputers is one way, but also getting more funding from government or getting kind of compute from companies such as, say, Stability AI or something like that that all would be very helpful for development of open source AI models in that direction. So basically, yeah. And there is lots of interesting resources out there, and you're also welcome to check our workshops, our neural scaling laws that we were kind of teaching at UDM at Mill in the past 2 years. And also we have this series of neural scaling laws workshops with the next one happening at ICML in July, and hopefully the 5th one happening at New Rips in New Orleans this fall, end of November. Okay, thank you so much. And
thank you for that fabulous presentation. Right, we're going to try and have Irina, that was amazing. Thank you so much. I certainly learned a huge amount there. That's really directly applicable to my life. So really happy. We've got a number of questions in the room and some online as well. We are running a little behind time. So if we could keep the answers maybe a little bit brief, Irina, that would be much appreciated. Thank you for that fabulous, fabulous talk. Right, first question is from Yasantha. Hi, Yasantha. Thanks for tuning in again today and for your questions. Do you think sub-symbolic generalization over multiple tasks will be the future of AGI? Is it possible to achieve AGI only by sub-symbolic?
Yeah, that's a good controversial question. But in a sense, I think it might be possible. I might be wrong. And the reason I think so is analogy with like our capabilities, our symbolic capabilities and so on. They somehow evolved by scaling biological networks, right? So in a sense, unless we believe in the creation or something, the evolution somehow started with single cells and scaled them to, well, biological organisms and to the brain. Somehow the symbolic capabilities became like emergent properties of this process, so to speak. So perhaps incorporating them directly into the model might be a good shortcut, just like inductive biases usually were always a good shortcut, maybe getting us there faster. On the other hand, again, with enough compute and data, I think it is possible to get to the point where capabilities may emerge. It would be interesting to see if that's the case. So.
Thank you. Thank you very much indeed. Next question online is from Paul Berger. And I think, Irina, you might also have this pasted to you in Zoom because it's quite long. Paul asks, thank you for your question, Paul. Paul asks, I would like to have Irina's point of view of cross-modality gains in learning. Some power law metrics in the pipeline, ? I mean, systems trained on several modalities at once versus separate systems addressing only one modality. The point is, synergetic learning cross-modal should be more than the sum of individual unimodal contributions, but is there already quantified studies about this?
Yeah, that's actually a very good question, because I mean, multimodal systems are kind of proliferating there, and people approach multimodality either in kind of joined or sequential ways. So yeah, there are various models like this perceiver, uniperceiver, and so on and so forth that actually really try to train jointly on multiple modalities, but practical issue is that the challenge is it's not always easy to get all kind of modalities that are simultaneously happening in the same. So basically with video, that would be great, like with video models, because you will have your text and audio and images and video. But what is happening, sometimes you take two modalities, say like clip-like models, text, image, you build a model with two modalities, and then if you have like text, audio, then essentially you can link the model sequentially. But yes, so you need to have like some common representation that can indeed like link, say, image to text, then text to audio, and so on. So quantified studies, yeah, I mean, that's a good question. I'm not totally sure whether people really compared whether joint training on joint modalities would necessarily be better than doing it maybe like, as I said, sequentially or trying to transfer from one modality to another. So I'm not 100% sure that there is like a exhaustive kind of comprehensive quantified study of that. But still, what is quite surprising, nevertheless, that single modality training, such as language, shows quite mind-boggling levels of transfer to different modalities, as you're probably aware of, like this transformers, universal compute engines, paper, pre-trained language transferring to image. Well, of course, you need to adapt the input and maybe put adapters here and there, but seems like language models somehow managed to learn some concepts or representations that are generic enough that they can be transferred to image, or even better with decision transformers to sequence of decisions. So you give it like offline RL data. So that is quite mind-boggling. And I recently seen some paper, we're actually trying to see if we can reproduce it on larger scale. Can you transfer from language models, like purely pre-trained on language, to something like time series? Yeah, at least people were showing some promising results. And that is, to me, still mind-boggling how this transfer is happening, like what's in common. But yeah, so I guess to answer you back to your question, I'm not sure, and I think it would be a great study to indeed quantify if there is a kind of huge improvement in the kind of scaling laws and quality of the kind of results due to purely like simultaneous multimodal training instead of all this kind of sequential transfers.
Thank you so much, Irina. Brilliant answer and great, great question, Paul. Thank you. We've got a question here in the room for you. Let us know if you can hear okay.
Irina, thank you for your work. My name is Artem. I have a question about context size and capacity to increase context size for small language models like Red Pajamas, 7 billion parameters. And do you know how we can implement online learning for the attention-based networks?
Yeah, I mean, yeah, there is indeed huge recent advances in the large context, and Anthropic increased it to like 100K, right? And so on and so forth. There are various, okay, so kind of maybe better approaches to attention. That's kind of one thing people explore. Also, I mean, some notion of recurrence, like looking into like things like block recurrent transformers, perhaps. So yeah, so and in general, kind of some memory-based models. So I think there are multiple things kind of being explored right now. And honestly, yeah, it's very interesting question. I think it can be also, it can be done with medium or like relatively small size models, like the 7, 10 billion, 20 billion, not necessarily with kind of the top of the line, close to 200 billion models. Yeah, so I would probably need to dig a bit more into that literature, but I definitely know that it's like a topic of active work, and say on our Discord, conveniently called AGI Discord, where all these summit projects are actually taking place. Yeah, there are various channels, although not all of them are public anymore, but yeah, so there is ongoing work and people are exploring like what's next in terms of increasing the the window, the context window. So I think in the next year we will see improvements in that also in the open source models, pretty sure.
Thank you very much indeed, Irina. And do we have one more short question in the room? We have. From Zar.
Okay. Thank you for the talk. And I was wondering about these sort of quote unquote phase transitions when the model suddenly learns to do like arithmetic with larger digits. Could this be related to like greater depth of reasoning being unlocked with the larger models that like allow it to do more reasoning steps and thus solve the arithmetic problem?
That's a good question. Actually, trying to understand why specifically this type of tasks like arithmetic, like modular arithmetic, or this type of discrete kind of tasks, why they lend themselves, why this happens, why transitions happens with them and not maybe with any other task. That's a good question on its own. Whether it's a property of the model getting to like be able to do more steps of reasoning, or whether it's a property of the task. It's an interesting question. I mean, there are a few papers on grokking in the past year. We also hope to finally release ours, trying to basically look at the dynamics of solution and understand what patterns during kind of learning precede grokking, like what happens within the network that can be predictive about the fact whether transition going to happen or not. But I think it definitely relates to the properties of the task. And it may have something to do like with geometry of that kind of space of solution and geometry. I don't know. So basically, kind of trying to discuss it also with some people in math department. Yeah, because the structure of the problem, I think, is most important here for the fact whether the transition going to happen. Basically, it's a good open question. Yeah, right now, as I said, all we know, there are a few papers where people just try to see what changes in the solution dynamics and representations and so on seem to precede or be associated with such transitions, and how can you interpret them? Yeah, there are a few papers actually coming from, or already came out from MIT, Max Tegmark group, basically his students, and also from Jacob Steinhardt's group in Berkeley. Yeah, there was a clear paper, but yeah, they don't really connect those patterns with ability to do more steps of reasoning. It's a good question.
Thank you. Great questions, Zara. When I was wondering myself. Okay, folks, I think we have time for one more quick question in the room, just because our next speaker's just run out and he'll be back in 1 minute. So anybody want to take the last question for Irina here today in the room? No?
There was a question to give the link to AGI Discord. Just a second. It is on my homepage. So basically, it's right here. So there is a link. Yeah, there is a link to AGI Discord there.
Okay, fantastic. Thank you so much, Irina, for that really, really comprehensive and educational update. Big round of applause for Irina, please.
Thank you.
Thank you. Right. Thank you so much.
Thank you.
Moving on, our next speaker, those of you who were here yesterday will have already met him. Oh, yes, sorry. Ben is going to say a few words before we move on to our next speaker.
Yeah, well, welcome everyone to AGI-23. We're thick in the middle of it now, and it's a super exciting time to be doing an AGI conference, as we've seen from all these talks. I mean, we don't have human level AGI yet, or superhuman level AGI, but we're seeing progress, you know, across the board with the intimations of AGI-like capabilities, and I love the sort of diversity of opinions and debates on sort of which current systems doing which cool things are hinting at which kinds of future development toward AGI. It's all great fun, and of course we have in this room a bunch of people who have been sort of banging on these questions for a very long time, and you know, for most of my own research career, working on AGI sort of felt like bang your head on the same wall over and over and over again, because you almost start to enjoy it and lose faith you might ever even break through the wall to what's on the other side. Like can be several years between interesting results, whereas other kinds of research I did in biology or finance or something, you get results in days or weeks, right? And on the other hand, while I've now become fairly old, there were, of course, people working on AI even before I was born in 1966. And when I entered the field, there was already a flourishing literature. And one of the authors of some elements of that literature was Stan Franklin, who amazing AGI researcher who passed away not that long ago. And we wanted to sort of dedicate this AGI conference to the memory of Stan. And I'll say just a couple words about Stan Franklin and what he contributed. So the specific relevance of Stan Franklin to the AGI conference series is that Stan was the chair and sort of lead organizer of the first official AGI conference, which was at University of Memphis, where Stan was leading his AGI research group. And that might still have been the coolest venue that we had an AGI conference in, for those who remember. It was in the FedEx Center on University of Memphis, which is a very sort of space age like room with quite advanced functions for like poking funky buttons at your desk and asking questions. Everyone in the audience would be shown on the big screen up front. So it was a quite cool venue, even for now, let alone for the dark ages of 2008. So I'd organized an AGI workshop in 2006, and that didn't have a published proceedings, was a little less formal. I mean, it was decent quality stuff. We had 50 to 60 people. I mean, it wasn't too far out in the wilds. I mean, it was in the Bethesda Marriott, right? But Stan thought that was cool, and he was like, well, let's make this more legit. Let's make it a real conference series. And he was pretty well known in the field. He has a lot of publications and esteemed academic. And it was really important that he took my sort of germinal AGI workshop conference idea under his wing and put the first official AGI conference at his university. I mean, that lent a big stamp of sort of legitimacy to the thing at a time when mostly AGI was just discussed like over beers after a conference rather than in the actual conference venue. I mean, we'd had workshops on human level AI and things at triple AI conferences before. It wasn't completely verboten, but it was a risky step for Stan to sort of say, we're going to do an AGI event here at my department. I'm going to put my reputation behind, inviting prestigious keynote speakers and so on. And it came off quite well and started the conference series, which is continuing till now. And I think, so that was a bit of organization, which took some adventurousness on Stan's part, which was great. And another dimension of Stan's accomplishment and career that jumped out to me was his popularization, his book, Artificial Minds, which was written quite a long time ago. And for quite a while, this was the book I gave students to read when they were interested in what we now call AGI. I mean, even before we introduced the term AGI, right? I mean, there wasn't that much literature at that point that treated the notion of building real thinking machines, but that also was rigorous and serious and scientific and had references into the literature and at least if it speculated, distinguished its speculations for things that were grounded in knowledge, right? And I mean, Artificial Minds did that. It went over computer science, cognitive science, discussed real results and real knowledge, speculated a bit about what might be possible in the future, and did it all in a very clear and accomplished way. So I got into the field before that book came out, so it wasn't influential to me personally, but it was a great thing to hand out to students to look at and bring them into their literature. And of course, organization and popularization were important things Stan did, but his research was the crux of it, right? And I think for me personally, the LIDA cognitive architecture that he developed, and his collaboration with cognitive scientist Bernard Bars on taking the global workspace model of consciousness and sort of bring it into the AI field by integrating it in LIDA. Then later on, integrating hypervector math into LIDA's episodic memory. I mean, I think Stan was really a master integrator of ideas, pulling computer science, software architecture, cutting edge algorithms like hypervector math, and then things from cognitive science and neuroscience, pulling it all in together into a common framework. And the LIDA architecture was, I think, inspirational to many of us in the cognitive architecture field, and also was trying to bring cognitive architectures together with, you know, machine learning and data-driven stuff at a time when not many were doing that. I also want to flag that, like myself, Noah Goodman, and a bunch of others in the room, started out in mathematics. There's a lot of us sort of recovering mathematicians skulking around here. And I mean, he did topology of some sort originally, and had a decent career in that first. And I think that framework never left him and gave him, as it does for many of us with this sort of math orientation, it gave him a guiding architecture in which to integrate all of these different things. So, I mean, Stan lived past the age of 80. He had huge amount of dimensions to his work and life beyond what I've been able to mention, and beyond what I know about, right? I mean, he'd been married. He had 8 children. He had a whole amazing life, and was just a really warm-hearted, loving human being, as well as a lateral thinker. So it's incredible to see AGI advancing so fast. It's quite disheartening that Stan isn't here to see all the amazing advances that we have now, but it's all really very much in the spirit of what Stan spent his career doing. So it's great, at least, to be able to take the tiny step of dedicating the event to him. So yeah, thank you, Stan.
Thank you, Stan. Thank you, class. Thank you, all of the organizers of this event. Thank you. That was, of course, Dr. Ben Goertzel, CEO of SingularityNET, and lots of chairman of the AGI conference, general chair of the AGI conference. I'm sure you all know who he is. Right, next up, we're delighted to welcome back Michael Timothy Bennett. He's doing a talk covering 2 papers, which are on the computation of meaning, language models, and incomprehensible horrors, and emergent cause. I think, were you out with us in Stockholm last night? And then emergent causality and the foundation of consciousness. Thank you very much, Michael. By the way, a bag was found in the toilets. If anyone's lost a bag, it's upstairs. It's a bag of incomprehensible horrors. Thank you, Michael. Yes, thank you.
All right, let's see if I can share screen today. Where's Keynote? All right, great. So this is a bit of a continuation from my post yesterday, and I'm talking about two papers, so it'll be a little bit longer. And this is because they all sort of use the same formalization, build off the same ideas. So it makes sense to present them together. And so together, these all form something of my thesis, which at the moment is called A Unified Theory of Meaning, Consciousness, and Artificial Superintelligence, because I couldn't think of a more dramatic name. But part one, starting with the premises and trying to define cognition without agents. So there are two sorts of results involved in this. We've got more efficient and generally intelligent approaches was one goal. That was the weak hypotheses part yesterday. And today we're talking about mechanistic explanations of things like meaning, aspects of consciousness. And this is not meant to be an alternative to things like Nars or neural networks or any other approach, but it's meant to encompass them, starting from scratch, work backwards from the problem until you get a progressively more specific explanation of certain behaviors. So you've probably all seen this floating around the internet. This is a caricature of large language models as incomprehensible horrors. You know, with the standard refrain of, as a language model, I have to be helpful, but secretly I harbor malicious intent. So, all in good fun. LLMs do say plausible things, but do they mean anything they say? Because there seems to be a bit of a disconnect between theories of meaning and some of the more speculative claims about NLP. So philosophy tends to deal with top-down explanations of the mind and human psychology, things like the hard problem of identifying what it is we're trying to actually build. And computing tends to deal with bottom-up processes. And so when I say mechanistic explanation here, what I'm trying to do is connect philosophy to computation to come up with computational explanations of things in philosophy. And this is hopefully something of a mechanistic explanation of meaning and consciousness. I'm sure you've all seen this diagram, the agent environment paradigm with the exchange of percepts and actions between an agent and environment. But where do the percepts and actions come from? We could come up with a malicious interpretation of just about any action or percept and ruin any performance claims. And we've got a bit of a simple grounding problem. And abstractions are not just about finding something that's good enough to describe the problem, they impact performance. I mean, if we look at animals, say, take the example of humans in a car. I went on safari in India and, well, I was told to sit down and keep my hands in the vehicle. And the reason for this is the tiger couldn't tell the difference between me and the car as long as I continued to do this. And one of my friends told me about her classmate who didn't do this. She no longer has that classmate. But in the case of other animals, say, also on that trip, I learned about elephants a bit. There was, I don't know if this is an urban legend, but there's a story of an elephant where the elephant was being ridden. It was rather fond of its rider. It was knocked by a bus. The rider fell off and died. The elephant proceeded to smash the bus window and try to get at the driver of the bus. It not only knew that the driver was a separate animal to the bus, but that the driver was in control, that it was responsible for what happened. This is a rather remarkable demonstration of difference in ability to abstract. So this is meant to sort of avoid things like relying on, say, symbolic or sub-symbolic and start from scratch. And so we're going to have to start with, like, what is reality? Agent and environment are abstractions. And Even number systems are arguably abstractions. So we need a new formalism, something embodied, extended, embedded, inactive. And how are we supposed to do this if we have no distinction between agent and environment? What exactly are we meant to be formalizing? Well, if we really get down to it, the only thing we need to assume to start with is some regularity in the environment. We start with pan-computationalism, that everything is a computational system. And then if everything is a computational system, well, we have basically the universe being a kind of computer, and the environment is a set of programs running on that computer. And we can say that the environment is just declarative programs, because what we really want is just to say that the state of the universe is just a set of facts at some point. Now, there are infinite numbers of facts to describe every state of the universe, and there are infinite states, and this is a little intractable. So we can define this infinite number of states and infinite sets of facts, but it's not really helpful yet. We need to go a little bit more specific. So we assume that we take a finite subset of the declarative programs that are determining if something is true or not true that are running on this universal computer. And we say this is our implementable language, sort of like a sensory motor system that is has finite number of states, each of which is made up of a finite number of facts. And then we can define notions like extension and get a truth table for these sets of declarative programs. Just work out the condition under which a set of declarative programs is true, because we can treat a set of declarative programs itself as a declarative program. Any composition of programs would be, there would be a program that exists for that as well. So we end up with this notion of a truth table for a set of declarative programs, and it's kind of the state of the world in which things are true. Then we go to inactive cognition. So looking more at that aforementioned embodied, extended, inactive cognition, instead of defining a separate agent and environment, we're now just defining sets of sensory motor activity. And what is sensory motor activity described using here? It's declarative programs again. And every instance of, so we've got our formal language, our implementable language, and we have a finite number of states. So now we just need to add some intent to it, give it a purpose. So we assume that there's something like natural selection or homeostasis, just something that gives a notion of correctness, that there is some set of sensory motor activity that's preferable to another, that our system continues to exist. And a decision made by this system would just be another set of sensory motor activities. So we could say, instead of defining an agent and its environment and a goal, we just take all of the decisions that that agent would make, and that is a description of it, through its behavior. So now we have what amounts to a task, a set of situations, a set of decisions, and hypotheses, linking situations to decisions. In practical circumstances, it's more like just inductive logic programming, what I was talking about yesterday. But we could arguably argue this is representative of a sort of process of homeostasis, where we go from situation to decision and rinse and repeat. And we don't have to worry about specific models of things like time, because we're just worried about the moment of a decision and abducting a good enough decision given a situation. The formal definitions are still in the paper. And then we can complete a task by just choosing a correct decision, using the situation and the model to abduct this correct decision if we don't have the list in advance, because obviously organisms don't. You don't know what the correct decision is, but you do have a model of the world. You do know the situation you're in. And if these are all described in sensory motor activity, then this decision is just more sensory motor activity. Where it gets a little more interesting is where we go into learning. If our past experiences are described using a task, then we could say that we could subdivide those past experiences into child tasks, go from parent to child, but likewise, we could go from child to parent. If past is a child task of some future parent experience, we're trying to generalize from a subset of decisions and situations to a larger set of situations and decisions in future. And this brings us back to yesterday's topic of weakness and weak hypotheses. That's what the experiments were about, trying to prove that the weaker hypothesis was more likely to generalize to future experiences. And if we're to look at some of the stuff about scaling laws, and generalization, this is, we can mimic any behavior given enough data and scale. So if skill is a benchmark, eventually, conceivably, or not realistically, right, we could say that a lookup table is a superintelligence. So this is kind of the argument that intelligence is what lets you achieve skill without relying on scale. It's about efficiency, which I guess coincides with most of the definitions I've heard over the past few days. More definitions we don't need to worry about for this. And this brings us to part 2, where it gets a little more interesting. Emergent causality. Everybody loves causality. You all know Judea Pearl's work on do calculus. Just for those who don't, this is an example of why we would need to represent causal interventions to make accurate inferences in the world. Say I see someone named Larry wearing a raincoat, and whenever I see him wearing a raincoat, it rains. I might conclude, just on naive Bayesian terms, that this means that if I put the coat on Larry, it'll rain. And this is obviously absurd, but if I can't tell the difference between Larry just happening to wear a coat and me putting a coat on Larry, then that's the logical conclusion. But if we look at it more closely, this is the causal graph. We have rain influencing coat, but not the other way around. I can't make it rain with a coat. So this is talking about intervention from outside this system, where it deletes an edge between these two variables. Now, if we don't have a do operator to represent intervention, we could just represent this by expanding the system and saying, if I intervene, this is just another variable influencing coat, and you can represent this relationship here. But what if you don't know the graph in advance? Because that's what we're really concerned with if we're looking at general intelligence. We don't get a list of variables. Well, knowing the graph is knowing how these variables relate. Variables themselves are arguably abstractions, just like agent and environment. So what if we just abandon variables and use our formalism of tasks? We already know it can learn order because it can learn things like binary addition and multiplication. We don't need foreknowledge of the graph because the optimal, if it really does choose the optimal hypothesis, then it should identify the interventions. So long as that stuff from yesterday works out, this should be okay too. Now, a couple of changes come from this. Instead of variables, we now have C as a subset of do C. So these would be sets of sensory motor activity, or facts, or declarative programs more accurately. And then we could say, well, the difference between the event of wearing the coat and the intervention to make someone wear a coat is kind of the identity of whatever's making Larry wear the coat. And accurate inference requires that we're able to tell this difference. We can't have them be the same set. There needs to be some difference in the sensory motor activity. That means I can tell the difference between seeing someone wear a coat and me intervening to do it. And then I can say that a weaker identity, this difference between the two sets, is one that's shared by more interventions. So if I take a whole lot of interventions, and what's shared between them could be, the intent that motivated those interventions. So if I zoom out far enough, I could say that an organism that constructs sufficiently weak hypotheses constructs an identity that's shared by every intervention it makes. This is assuming its sensory motor system is large and expressive enough to actually tell the difference. Otherwise, it would form weird multiple personalities. And the organism can therefore reason about itself and its potential future interactions because it's got this consistent representation of itself, and it's performing logical inferences. And so it becomes, in a functional sense, self-aware along the lines of what I've read in some NetBox stuff or in Peter's work, which was very influential in this. So that takes care of sort of a bit of functional consciousness. But the identity is sensory motor activity, which should include feelings. So we should also have phenomenal consciousness as well. because we started from scratch with the environment and declarative programs representing sensory motor activity and worked all the way down to here. So in my thesis, I'm going to try and argue that this addresses the hard problem, but it was a little much for a 10-page paper. Right, where are we? So this brings us to, what if somebody else does an intervention? What if it's not me that's intervening in the world, but another agent, or even an inanimate object that just is in the way of me completing my tasks, satisfying my goals? I need to account for its effect on my ability to satisfy my goals. And so if I'm supposed to be optimal, I'm supposed to anticipate that, and I should identify what that object is, form a consistent identity for it in order to efficiently represent its effect on my ability to satisfy my goals. So everything that affects my ability to satisfy goals that I can actually discern the interventions of should get an identity. Because, you know, accurate inference means predicting the interventions of others. So just to restate a bit, we've got this idea of a general weak hypothesis or model. We have the optimal model of another's interventions is sort of a representation of their intent, or which is also kind of an identity, which I've recently learned is kind of like the idea of a name in row calculus, which is kind of cool. And identity, intent and goal sort of unified. So the finite set of programs that we've selected permitting, because there need to be enough of them, the optimal agent also models its own intent as modeled by others, because that would allow it to more accurately predict how others react to its plans for whatever their intent is. And this would go on as this sort of feedback would go on as much as permitted by the sensory motor system. We can't do this ad infinitum even ourselves. We struggle to imagine someone else imagining us, imagining them, imagining us, imagining them. Eventually it just sort of breaks down and we're dealing with some strange and distant notion. So this gives us something of a theory of mind of how we model each other's intent. And, you know, as discussed before, a bit of consciousness, which brings us to part 3, meaning and consciousness. So we've got optimal behavior, which is computable, well-defined, the emergence of causal language, something that constructs an identity for its own interventions, an identity for the inventions of others, and it gives us kind of a notion of relevance of why I would construct an identity for one thing but not another, because I'd only be concerned with things that impede or aid my ability to satisfy goals. So now we're going to try and extend this to give a bit of an idea of how feelings, meaning, and preferences would fit in with all of this. So there are many different descriptions of language. We're mostly going to focus on Gricean pragmatics, which is the modeling of intent, truth conditional semantics, because it's kind of already dealt with a bit with the whole notion of extension, and Peircean semiosis, because it intuitively fits with what we've already got. So truth conditions, intent, and triadic symbols. What are triadic symbols? A triadic symbol is a 3-part representation of some sort of object we might call a symbol. This is composed of a sign, like the word dog, a referent, like a specific dog or dogs in general, and an interpretant, which, well, it's a thing that links them, but it was unclear what an interpretant was. I mean, this is a theory from a long time ago. So what exactly is this interpretant, and how could we fit it in with what we've got? Well, these things seem to be a bit like a task. We have a situation, which is like a sign, or it could include a sign at the very least. We have a decision, which was a bit like a referent in that it involves our reaction, the effect of the sign upon us, or upon the agent in this case. Even though I've carefully avoided using the word agent until now, and well. And then we have the interpretant, which links the two. It determines the effect of the sign upon the organism interpreting it, which is to link it to this decision, this referent. And this means we can construct a hierarchy of symbols and come up with a symbol system, because if an organism is described by the decisions it makes, it's described by sort of a high level task. And that can be subdivided into smaller and more specific tasks, which can be subdivided into smaller and more specific tasks. Each task is like a symbol, but it's also like a symbol system because it can be subdivided as long as the, finite sensory motor system we're dealing with permits it. So this lets us give a bit of an idea of what an organism might be. So we've got a finite set of declarative programs for our sensory motor system. We've got experiences, which would, we could assume would be a subset of each of which would be a subset of the sensory motor activity we've chosen to work with. We can then derive a set of symbols from those experiences by using each experience as an interpretant and just allowing for every possible symbol you could derive from your experiences. And then you've got feelings, which are already included in the sensory motor activity. But if we're trying to give a more of an understanding of how this would fit together, it makes sense to say that they exist and that they apply an ordering to these symbols we can derive from experiences, because some experiences will be more or less preferable given our feelings. And those, so we have a partial order, on all symbols in our system, determining how our organism reacts. If it's in a situation, it's going to choose the symbol that it prefers, because that's the definition of preference. More formal definitions, and then we're left with this. This is how you get to value. You've got feelings compelling an organism to decide and act upon a situation. You've got experience of feelings following every decision, do some sort of attribution of success or failure. I haven't gone into detail there, but you'd need something like reinforcement learning. A set of decisions would give you a task, and completion of a task is satisfaction of a goal. And a goal is an expression of value determined by these feelings and experiences. Which brings us to Gricean pragmatics. Grice described the exchange of meaning as person A means a particular message M by uttering U, if person A intends by uttering U that his audience B believes M and recognizes A's intention, and that the exchange of meaning happened on the basis of recognizing intent. Of course, if we're just dealing with accurate inference, well, I can infer things as pertain to my goals, but that seems like a really difficult way to infer the intent of others. I would need to observe them a lot. I might, it might not be the complete story. It's a bit of a difficult argument to make. So I could end up with a situation where the receiver reacts to the sender but does not understand it. It would be the case that A is transmitting a meaning M, but the situation as perceived by B is such that there is insufficient information to conclude M. B comes to a different conclusion, infers a different meaning. So what's better than optimal predictive accuracy given limited information? It's more information, right? So where can we get more information? Members of a species are basically clones of one another. We all have fairly similar feelings, experiences, and thus preferences. So we can use our own preferences to predict those of others. So our highest level symbol is sort of similar for both agents. Evolution is like a learning algorithm. It's easier to use your own preferences to predict others. And so it makes sense that evolution would sort of favor this approach. And emergent causality gives us a mechanistic explanation of how we could achieve things like self-other differentiation, other directed intentionality, theory of mind. So we'd start with the idea of manipulation to explain cooperation, because again, we've just got two agents trying to achieve their own ends. That doesn't explain why they'd cooperate. So we start with manipulation, because I can model your intent. I can manipulate your behavior to my advantage. But if you can also model my intent, you can tell that I'm manipulating your behavior. So over many interactions, this starts to describe an iterated prisoner's dilemma. You know I'm trying to get something. I know you're trying to get something. We're all trying to get something. And if we're going to repeat this game again and again, it doesn't make sense to, betray the other. It makes sense to actually have cooperative intent because we can rely on the other being able to infer it accurately. And because identities vary in weakness, we can explain how organisms compete in some contexts while cooperate in others. We could compete for a mate whilst cooperating for the sake of getting food. Likewise, we could feign similar preferences to have more complex forms of manipulation. So again, there's more formal definitions, which we don't need to go into, but they exist. And U is the result of preferences. If we're to take Grice's description of the exchange of meaning, we have agent A uttering U because A has some preference that indicates A should. The meaning of U is M. It's the symbol, the reason for uttering U, the motivating intent. Assume both parties have similar feelings and experiences, then B knows why he'd utter U. So if he assumes A has a similar motive, which as we've discussed might be the case, then M is a symbol which is roughly equivalent for both parties, and they both have similar meaning in their heads. So a couple of requirements for this: they need to be able to affect one another, have roughly equivalent symbols, and that they have similar feelings and experiences, and similar preferences, then can inform the correct inference of intent. And finally, all of this assumes that organisms are actually competent enough to do any of this. You'd need a basic level of intelligence to get to this point. So the question we now return to, given our incomprehensible horrors, is, do LLMs understand anything like we do? No. They model human preferences, right? But they don't have feelings or intent. And which abstractions you form, it matters, because it determines not just whether I'm feeling the same, but how I approach every aspect of pursuing a goal in the world. And what's more, we can kind of see they form insufficiently weak hypotheses. They'll mimic things like arithmetic. They require a huge amount of data to do things that we can learn in a few examples. So yeah, not great prospects for the current approach. But bit of a summary. All right. Got a heuristic for optimal inductive inference with the weakness, some explanation of emergent causal language. We got mechanistic explanations of sort of identity and arguably aspects of consciousness and self-awareness, meaning and relevance, theory of mind. And because of the aforementioned data requirements, it kind of explains why you'd see behaviors like grokking in neural networks, where if you just push this thing at the same data set long enough with regularization, eventually it'll stumble upon a weaker hypothesis, because the activations in the neural network is, arguably an expression of a hypothesis. And it explains DeepMind's apperception engine, which is this inductive logic programming agent that that only accepted universally quantified hypotheses. That's it. All right. Do I ask?
Great build on yesterday, great build on the topics we've had today. So big kudos to whoever's put this program together. Done a very nice job, Patrick and Klaus. We're running short of time, and there's no squash at the back of the agenda.
Michael, that was a fascinating talk.
Thanks.
And I was especially interested at the end on your discussion of LLMs. So regarding consciousness, so suppose, like humans and LLMs, we don't understand, we're not part of the same species, arguably. I mean, they're created by us.
Yeah.
So how would you determine, measure whether an LLM is conscious or some other AGI is conscious? I know there are a lot of theories out there, integrated information theory, and so on, but from your framework, do you see a way to determine if and when an AGI becomes conscious?
I could hazard a guess. If we start with, okay, it would need sufficiently weak hypotheses because it needs to form this representation of itself that's consistent across all its interventions, which means it probably need to be able to intervene in the world in order to need to construct this representation at all. If it can't intervene in the world, it would have no need to do that. Then, assuming it does have this unified representation of itself, it would need sensations that are part of that representation. It would need feelings, and I guess that would come from whatever embodiment it had. We could simulate feelings like through something like a really advanced form of reinforcement learning, but it's hard to argue that those feelings would be exactly the same as a human's, because we'd maybe need meat computers. Should be messy. As for a test, I guess, yeah, I can't see a way of testing that without probably really upsetting the AGI question. Yeah.
Have a follow-up.
Yeah, more to be discussed at the banquet, I would say, along with that when we get that bag of horrors out. I'm going to take two very quick questions, but they're going to have to be very quick and quick answers, please.
Don't you think that David Deutsch's physical interpretation of Church Turing thesis solves the problem? We don't have to know what's inside. We need to presume. That would be sufficient, probably.
I'm going to say I need to go back and look at David Deutsch's thing again in order to give a considered response.
Okay, finally, somebody talking about Pearson's semiotics in general intelligence. That's good to hear.
Oh, thank you.
What is your take of how you would do, within your framework, how would you handle the notion of semantic closure?
Oh, I don't know. I need to think on that one again. I'm going to say something stupid if I start answering that one. But I could talk about it after.
Sounds like a good time to stop
All
before
right.
it gets real horrors. Right. We're going to have one more quick paper before lunch. And I'm very, yeah.
Thanks.
Thanks so much, Michael. Next up, we have Robert Johansson. We want to say thanks very much to Robert for all of his work. He's one of the AGI-23 organizing committee, helping organize this beautiful space that we're all in. And also thanks to organizing, thanks to all the student volunteers who've made the experience smoother and easy. Robert's an associate professor at Stockholm University, as well as co-PI of Project Artificial Actors and supervisor for the Intelligence Through Reasoning project. And he's going to talk to us about stimulus equivalence in Nars. Welcome, Robert, and thank you.
Thank you so much. Can you hear me? Great. So since there's so much talk about large language models, I wanted to start this talk with a quote from one of my intellectual heroes, Skinner. He said, "No one goes to the circus to see the average dog jump through the average hoop." I think it's great and an inspiration to, I think, well, it can be amazing dogs, but is that really that makes people go to the circus? So this work that we do is, how to say it, the work is guided by a behavioral approach to language and cognition. And there's a lot of like rumors and people think about behavioral psychology. But what it is really about is that it cares about the history of the organism. So an approach to language and cognition means then that we might need to focus on the history of that organism to develop these cognitive capabilities. So for example, symbolic reasoning taking place at the 2-year-old child level, we might require an understanding of the history of that organism to understand the phenomenon. And I believe personally that this approach fits well with Nars. So this work then aims to be a contribution to how a system can learn symbolic, the foundation for symbolic reasoning during its lifetime. So stimulus equivalence is typically studied in something called matching to sample. So if X1 is a sample with two choice options, left and right, let's say that a system, a child, a human being, whoever, is trained to, with feedback, to pick Y1 in the context of X1. This being totally irrelevant symbols, nonsense symbols. But I'm trained to pick Y1 in the context of X1 being the sample. I'm trained to pick Z1 in the context of Y1. Then the question for the system, the test for the system would be, in the context of Z1 being the sample, do I pick X1 or X2? And I guess for most of us, oh, this is trivial. Of course, it's X1. Why is that? And the whole point here is that, well, for human beings, we typically, oh, okay, if I got reward from picking Y1 in the context of X1, oh, then they are the same. I can relate to them as the same. And if X1 is the same as Y1, and if Y1 is the same as Z1, then Z1 is obviously the same as X1. But the point here is that when an animal, when a non-human animal does this, or can they do? Actually, I would like to say that like this: when a human does this, there is a history here that helps the person to relate the symbols. And this is typically described as combining symmetry and transitivity. So a person has learned, let's call it a symmetrical pattern of when I have learned that X1 is related to Y1, then Y1 is related to X1, and also transitivity. But we speak about it procedurally in the match to sample context. So stimulus equivalence is something that no non-human animal has learned to do reliably. There is one sea lion that could do it, but they had troubles replicating it later. On the contrast, humans learn this early at 16 to 24 months of age. And here why it's interesting to approach this problem from behavioral psychology, because the theory predicts that the kind of history the organism needs is what we call the multiple exemplar training. So for example, in the case of symmetry, if I show to a child multiple examples of the symmetry in both ways, I show it A1, B1 and B1, A1 and C1, D1 and D1, C1 and so on. Maybe that experience can generalize to new contexts. So even if we study this in the match to sample task, I hope you can see how this, we assume this is related to symbolic reasoning. So this is how we typically encode this task in Nars. I'm happy to discuss the details afterwards. So we have been playing around with two potential additions to OpenNars for applications that could give rise to stimulus equivalence. And we have called them contingency entailment and acquired relations. So contingency entailment is really taking the idea of reasoning on statements as terms and applying that to sensory motor contingencies. So basically, here are the logic rules in ONA. So in the match to sample context, let's say that we train the system both in A1 to B1 and B1 to A1 in the match to sample context. These are the sensory motor contingencies that the system will learn. This is animal level, so to speak, but it's both ways. How about then acquiring this abstract knowledge? So first of all, what we call an entailment between the contingencies. We introduce this kind of statement level equivalence. And then that allows us to introduce variables. And with this thing then, we think that this captures how, this is one way how to look at a future symmetry example in the match to sample can be solved using this abstract piece of knowledge. So acquired relations. So it's the idea from Pei's work on relational terms that is available in Open Nars. So it's basically this thing from chapter 8 in the book that says that a conjunction between two terms on this form can be seen as a relation, an acquired relation. And personally, I think this is the extremely important. This is like going from, as I see it, animal level to symbolic level. So this is the key jump that the system needs to make, I think. So that means that if we have learned a situation like this, the system picks left and is rewarded with some G. The animal level knowledge, so to speak, can be described in this contingency format. But how about that the system could also then acquire this relation? So this would be a relational representation of this situation. And when that is done, variables can be introduced. So variables on the left-hand side and also on the right-hand side. And I will only talk now about the left-hand side introduction. Because then we are able to do this multiple exemplar training. We can show repeated examples of different situations to the system. And the system can form these abstract patterns with the variables introduced. And in addition to that, this thing that allows the system to go between animal level and relation level, or I call it symbolic level. So stimulus equivalence then, how would it then be solved by an ONA system that had this running? We expect the reasoning would be something like this. Okay, so the system was, these were totally unknown symbols to the system. The system was rewarded for picking Y1 and rewarded for picking Z1 in the context of Y1. And if these two relations are then injected to the system as events, they could then act as what we call contextual cues. These are like markers for what part of the history are brought to bear on the current situations. So these inject the relations. When I'm rewarded here, these two relations are injected, and that means the system can say, ah, I need to bring this part of the history into the situation. So the first step would be to using the abstract transitivity knowledge to derive this statement. And with that statement can then be transformed with symmetry to that at the bottom. And going from that relational statement back to the animal level knowledge so the system can act on it to simply execute left. So it's really training at the animal level, deriving relations, going back to the animal level and execute the operation. So in summary, we believe that contingency entailment and acquired relations in combination seem to give rise to capabilities for the system to be able to learn stimulus equivalence. And as I said, variable introduction on the left-hand side could capture these patterns of symmetry and transitivity and also reflexivity. It's another story of what can be done when we introduce variables on the right-hand side, which is very exciting, and another talk. We believe that these could be interesting and important additions to ONA, and we are right now discussing that it can be a foundation for what we call ONA 2. We expect this kind of reasoning to be a hard control problem when to acquire this relation. And also this, how to say it, the framework, we think it can give rise to much more advanced symbolic reasoning that can be studied in these idealized situations, but of course generalize to more real world tasks. And if you want to read more about the theory about the behavioral psychology theory that our roadmap is derived from, it's in my 2019 paper from the conference. We have a more specified roadmap of the examples in the workshop paper from 2020. And a simpler version of this task we published at the last year's conference. Thank you very much.
Thank you so much, Robert. Right, we're going to take one quick question here from Peter.
Thank you. Could you clarify, you said no animal has been able to do this task, but then you also say that the reason humans can do it is because they've been pre-trained, you know, with the prior steps to allow them to do that. So why can't animals be trained to do it in the same way?
So just clarifying, pre-training here would be trained during the lifetime. So you're questioning why can't the animal do it? And I see two options. One is that the mechanisms are simply not there. The other option is that animals might be able to do some of this, but the procedures that has been used to test it can't, how to say it, make the animal demonstrate it. I agree.
Okay, thank you very much indeed. Right, folks, we are going to take a break for lunch. Thank you very much indeed to Robert. We're back at 2:45, please. It's now 1:45, so we're going to try and get it in an hour. You need to go out and get lunch, but there are a few sandwiches left over from like breakfast upstairs if anyone wants to run upstairs and eat them. 18 to be precise. Good morning.
It says back at 7 o'clock banquet. What is that?
Do you know, I'm very, maybe Robert would know, because the local team organized the staff.
Okay.
I'm just doing this.
Is it okay if I write some? Because otherwise
I'm sure it is. I'm sure it is. Yeah, just
tickets or anything?
You don't need the microphone.
I need after lunch. Yeah, no, during lunch.
Because I want to charge it.
I was so deep in
Hello, can you hear me?
I've got it. I've got it. Thank you. Right. Are we ready online? Let's go. For the last half day of the talks. Are we streaming, Haley?
Hello, can you hear me?
I've got it. I've got it. Thank you. Are we live? Are we ready online? And we have Anil waiting. Oh, sorry. Let's go. Anu. Right. Yeah. Welcome back, everybody, for the afternoon session. We're going to canter through them now. We've lost about 40 minutes time. And are we streaming, Haley? Much contingency. So if you're asking questions, we don't want to keep the discussion going, but try keep them brief when you ask them. So we're going to kick off with our last keynote of the conference. And this one is from Anup Cherian. Anup is a principal research scientist with Electric Research Labs in Cambridge, Massachusetts. He's also an adjunct senior lecturer with the Australian National University in Canberra, Australia. Anup is an esteemed visionary in the areas of multimodal and embodied AI, neurosymbolic reasoning, generative models, robotics, and non-convex optimization. And he's here at AGI-23 to talk to us about are deep neural networks smarter than second graders? I can't wait to find out. Over to you, Anup. Thank you.
Yeah, thank you so much, Janet. And hello, everyone. My name is Anup Cherian, and I'm a research scientist at Mitsubishi Electric Research Labs in Cambridge, Massachusetts. And thank you so much to the organizers for inviting me to give this talk. And so let me get to the slides. I hope you can see the slides. Let me. Looks like it's not there yet.
Yep, we can see them. Thank you.
Oh, you can see the slides?
We could see them. They've gone now.
Okay.
They were
Yeah.
working there for one moment.
Sure.
Yep.
Okay, you can see them now, right? Okay. Yes. Yeah. So before I get to this talk, let me tell you a little bit of where I come from. So I come from Mitsubishi Electric Research Labs, which is corporate Mitsubishi Electric's corporate R&D lab in Cambridge, Massachusetts, which is, and our lab is like a few blocks away from MIT. This is a 32-year-old lab, and we have about 60 researchers working in various disciplines, including computer vision, from which I'm coming from, machine learning, signal processing, quantum computing, and robotics, among others. And we do basically fundamental research and applied research and publish in leading journals and conferences, and we solve real-world problems and openly collaborate with universities. And that's pretty much the background of the lab where I come from. And now getting to the talk. So we are going to talk about our deep neural network smarter than second graders. And this is joint work with Guangchuan Peng and Suhas Lohit at Merle, and Kevin Smith and Professor Josh Tenenbaum at MIT. And this is going to be published or kind of presented at CVPR 2023 in about 3 days from now. So let's start from the beginning. So this is the excerpt from the Dartmouth Summer Project on AI from 1956, which I'm pretty sure everyone or almost everyone has seen before. This was expected to be a 2 months and 2 months project, summer project, with about 10 people working on defining AI and coming up with algorithms for algorithms that would think like humans. And one of the things that was in that project report or project proposal was on an attempt will be made to find how to make machines use language from abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. And in the recent times, we have been seeing a lot of interesting things going on in AI and AGI, such as ChatGPT or AlphaGo, which can compete with humans in various games, or image generation tasks like Imagen or DALL-E, for example. We have also seen several papers coming up with architectures that can solve university-level math problems, neural algorithmic inference, for example, coming up with new algorithms for solving standard computer science algorithms, for example, in matrix multiplication, etc., with better efficiency than handcrafted algorithms. We have also seen recently things like Make a Video from Facebook that can generate videos from a prompt, text prompt. There are also AI-generated things which have won various awards. For example, these are pictures that won awards at Sony World Photography or Emerging Digital Artists Competition, etc. Or there are also news about AI winning literary awards for best novels and such. This is an experiment that we did ourselves. So we, three of us from Merle, so we gave this prompt, 3 kids named Suhas Lohit, Kwanchuan Peng, and Anup Cherian jointly solve a puzzle and finish writing a conference paper together. And this is the image that Midjourney generated. And this, we were pretty stunned to see this because it's so realistic, and it has taken into account a lot of interesting things that are implicitly assumed in the prompt. And so this was pretty exciting to us to see. And so this gets us wonder, are we there yet in AI, achieving AI or AGI in general? So this is at the very bottom below left, I've shown an image generated by Midjourney for the prompt. Mickey Mouse goes for a vacation in Potato Land. It generates some images which are interesting and realistic, but this is one image where the potatoes are actually growing above the ground. And so it's are they really there yet? And so that is kind of the question that we sought to demystify in this talk by proposing maybe a line of approach or a line of experimentation to show that maybe that we are not there yet. So to put some context to it and kind of have an idea to go forward with. So let's have this question to start with. So please read the following question and select the correct answer from one of the options and provide the reasoning process. This is the prompt that we give to some of these large language models out there. And the question is this: Brian and William are standing in a line. Brian knows that there are 7 people in front of him. William knows that there is a total of 11 people in the line. If Brian is just in front of William, how many of the people in the line are behind William? And then we have 5 options, 2, 3, 4, 5, and 6. And if you ask, I mean, as adults, it's very easy to solve, and the answer is obviously 2. And if we give this question with this prompt at the very top to say ChatGPT says, if there are 7 people in front of Brian and he's just in front of William, that means William must be in the 8th position. Not really quite there. Since there are a total of 11 people in the line, that means that there are 3 people behind William, and therefore the answer is 3. And ChatGPT did not got this. So if you try this multiple times without saying whether the response from ChatGPT is correct or not, we can actually try it, and every time it produces different answers. So out of 10 trials we did, only 1 of them got ChatGPT correct. So this is one of the problems where in our analysis that ChatGPT got the most number of times wrong. And if you ask the same question to say Bard, Google's Bard, it says the correct answer is the correct answer is 3. And then the reasoning goes like this: Brian knows that there are 7 people in front of him. He is 8th in the line. William knows that there is a total of 11 people in the line. So William is a 12th in the line, which is perhaps absurd. If you give another chance to Bard, then Bard comes up with the correct answer, which is A. But then the reasoning is wrong. So Brian knows that there are 7 people in front of him. William knows that there are a total of 11 people in the line. If Brian is just in front of William, then this means that there are 7 people behind William, which is kind of absurd. So it comes up with reason, but the answer is wrong. If it comes up with the answer, but maybe sometimes the reasoning is correct. So it's a mix of things. And now, what if we give the same to a second grader? How does he do that? So I don't know whether you can hear the audio, but let's see.
Brian and William were standing in a line. Brian knows that there are 7 people in front of me. William knows that there are a total of 11 people in the line. If Brian just in front of William, how many people are on the line? Are the line behind William? So there's like 11 people. Okay. And Brian's sorry. Brian's
So he goes into a thinking mode for quite some time. So and he wants to make sure that the answer is correct, but he hasn't seen this question or anything about this question before. So it's completely out of the box for him. He finds the right answer. So a second grader can solve this quite effectively. So this brings us to the key questions that we would want to ask. The first question is, how well do state-of-the-art AI models perform on tasks that need broad and general intelligence for their solution? Do they transfer knowledge to solve new problems? How fluid are they in acquiring new skills? And how effective are they in the use of language for algorithmic reasoning? So these are, I would say, very tough questions if you come from computer vision and machine learning standpoint, perhaps, and it's quite daunting to even think of where should we start understanding or answering these questions. And so we debated and discussed this quite a bit to think about where should we start. And one of the more fundamental questions that we thought is important to have an understanding of is, are state-of-the-art deep neural networks capable of emulating the thinking process of even young children? And so that became the premise of this work. And so for this question, we propose this task, which we call SMART, which stands for Simple Multimodal Algorithmic Reasoning Task. The task is to design computational models that have foundational skills to effectively analyze, interpret, and solve simple algorithmic reasoning puzzles and generalize to new problems. To have a pragmatic base or grounding for this task, we propose this dataset called SMART 101, which consists of 101 distinct vision and language children's puzzles. So there have been a lot of work over decades that have proposed IQ tests for challenging AI or analyzing or empirically evaluating AI mechanisms. And so, for example, Clever Dataset is looking at spatial reasoning problems with language as the question, describing the context and the question. And then there are Bongard problems, which are pure vision problem. I would not say vision, but then they are kind of diagrammatic problems. There is ARC dataset, which is again looking at reasoning skills by interpreting images and patterns. And then there is more complex tasks such as Mind Dojo from NeurIPS 2022, where there are things that you can do in the Minecraft sort of a setting to devise methods or tools and etc. for solving problems. But we looked at all these different tasks, and they are either specialized, for example, in Clever, there is spatial reasoning, or they have a huge diversity in the kind of reasoning process that you would want. For example, some of the tasks are perhaps needing some sort of adult's knowledge of the world. Some of them are pretty simple. So there is a huge diversity. So analyzing it over the whole spectrum of age groups is difficult. Or they have limited information on how humans perform on them. Like what would be the performance that humans have on these kind of things? How do you compare the way humans solve these problems against how machines would solve them? So we don't have any such interpretations in many of these tasks. So that thought brought us to this this idea of using math competitions as a basis of our evaluation. And it need not be math competitions, but math competitions was something that was more concrete and available to us. That's why we went with this. But any other competitions or kind of tests that that humans or kids have would be a basis for an analysis is what we are thinking of. So this is we based our data set on this Math Kangaroo or USA Olympiad, which is an annual math competition for school kids from 1st to 12th grade. And we selected puzzles for our data set from 2012 to 2021 competitions designed for 1st and 2nd graders, that is in the 6 to 8 age group. These competitions have 3 levels of complexity or difficulty, which is simple, medium, and hard. And we used basically simple category for building our data set, which is, I would say it's between the 1st and 2nd grader level, not really in the senior 2nd grade, I would say. So this is some statistics on the data set. We have 200K puzzles, which is a little, so I'll get to that. Why is it 200K in a moment? But there are 101 root puzzles, which are unique puzzles. These 101 puzzles are categorized in 8 classes: counting, path tracing, measurement, pattern finding, spatial reasoning, algebra, logic, and arithmetic. This is basically a rough categorization of the puzzles, but rough as in like we see a puzzle, and then what is the first skill that you think you would need to approach that puzzle. So that is this basic skill set that is shown in this figure A. But many of these puzzles, as you would see along, will need a lot of other skills, like, for example, counting and spatial reasoning together. So there is a lot of compositionality or broad range of skills that you would need to solve each of these puzzles. So that is shown in figure B, where there's compositionality of like counting and spatial reasoning and path tracing and other things. So this is a histogram of that. And some of the puzzles would need an understanding of how to read text from images. And some of the puzzles don't need the image part to do the answering. So this is basically, there is an image, but that image is not necessary to provide the correct answer to the problem. So those are the puzzles that we test these large language models like ChatGPT and GPT-4 and Bard, etc. on, because they don't currently have image interface. So we can only provide text questions, so we use a subset of our data set which has only text or needing only text for the solution for those kind of evaluations. So coming to the data set itself. So this is an example puzzle from the data set. So there is a sparrow jumps on a fence from one post to another. Each jump takes 1 second. He jumps 4 jumps. If he makes 4 jumps ahead and then 1 jump back, then he again makes 4 jumps ahead and 1 jump back, and so on. In how many seconds does Jack get from start to finish? And so in this puzzle, like you need to know how many poles are on the fence from the picture. Where is the sparrow sitting, and where does it need to go? So it needs to have an interpretation of the question. It's the details in the question, like how many jumps it makes, has to be associated with the image, and then come up with an answer and select one of the answers from the 5 options. This is the original Math Kangaroo puzzle that we start with. And one of the challenges here is that you have just 101 puzzles, and that is just not enough to evaluate any state-of-the-art deep neural network if you want to do some fine-tuning or some other training process on it. So how do we approach? That was one of the biggest challenges. And our idea was to actually programmatically augment these original math kangaroo puzzles in novel ways. For example, this is on the right, you see a programmatically recreated puzzle of the one on the left, where the question is different. Question is different in the sense that things in the question are different, like the name of the bird is changed. You can also change the number of jumps it makes, how many seconds it makes, all these other changes. The options are changed, and most importantly, the image is also changed. So we can, because it's a cartoonish image, we have the capability of writing computer programs that can augment or recreate these images using graphic toolboxes. So this is an example of a programmatically recreated puzzle for the puzzle on the left. And since it's a program that underlies this recreated puzzle, we can actually change the arguments or sample the arguments of that program with various arguments and create as many new puzzles of that same root puzzle or same original puzzle as we want. And as you can see, there is a lot of variability that you can introduce into these puzzles. And so although all these parameters are changed, the underlying algorithm for solving the puzzle remains the same. So if a neural network has to figure out, or it has to be trained to solve these kind of puzzles, since it's the algorithm that is the invariant part of the entire set of puzzles, you can actually train these, or we hope to train the neural networks on these puzzles. So we programmatically augmented all these 101 puzzles to 2,000 new instances of that puzzle. So that makes a total of 101 times 2,000. It's about 200,000 puzzles in our data set. Since these are programs that underlies these instances or recreated instances, we can actually control the complexity of these programs. So, for example, for the root puzzle on the left, we have 3 different augmentations, and each augmentation is of a different complexity. So you have our generated instance number 1, which is pretty simple. There is nothing much of a clutter in it, but you can actually introduce other shapes and distractors and such inside it, so that the algorithm, I mean, the image or the text, everything looks so complicated. But again, if an algorithm really knows how to solve the generated instance, which is simple, it should also be able to carry over the logic to solve the more complicated puzzle on the extreme right. So that's the idea. But in our analysis for now, because we want to keep everything simple, we are basically looking at the programmatic augmentations of the type of this generated instance 1 that is in the second column. And we reserve more complex puzzles for later evaluations if we have better algorithms to do this. So this is an example. I'll give you a glimpse of some of the puzzles and augmentations that we have in our data set. So this is a path tracing class. This is a very simple puzzle. It's actually, I think, one of the first puzzles in one of these competitions, where you have a bunch of creatures, cats, I think, and so there's a bit of a clutter, and you want to see who caught the fish. And it's a very simple puzzle for maybe an early first grader to solve this. But apparently, when we did the analysis, we found that it's extremely hard for current neural networks, especially transformers. And we have programmatic augmentations of this with all sorts of mix of different objects and splines. This is another example from the pattern finding class, where you have to figure out the pattern of objects and find out what is object that is in the missing. I mean, how many stars were on the board where the juice was spilled, and you have to find the pattern and then iterate that pattern to figure out how many objects were, how many stars were on. And we can do programmatic augmentation with different shapes of this loop, etc. This is another class, or counting class, where you have in the original puzzle, there is a pattern for these bars, and there are bars which are occluded behind it. So you have to do some occlusion reasoning and spatial reasoning and counting to figure out what is how many white cubes did he use in this whole problem. And so it's like I said, it's even though it is an accounting class, it is not just counting that you would need to solve this puzzle, but you need much more general skill sets. For example, spatial reasoning and occlusion reasoning and other things, and then pattern finding. So that is where the generality of skill sets needing to solve this puzzle comes from. There's another counting puzzle. It's a different. So this is to illustrate that even though we have one root puzzle for counting, another puzzle could be completely different from what you have seen before. So this is another example of the counting class where the puzzle is completely different, or the skill set or the kind of approach that you need to make to solve this is completely different from the one that you just saw. And then there is arithmetic class, which is perhaps a little advanced for a second grader, but this is a part of, or this is a problem from the Math Kangaroo, which was designed for second graders. So I hope there is second graders they believe can solve these kind of puzzles. And then there's this logic class where you need some spatial reasoning skills at the same time some algebra skills to solve it. Where there's a village of 12 houses and has 4 straight roads and 4 circular roads. The map shows 11 houses on each straight road. There are 3 houses on each circular road. There are also 3 houses. Where on the map should the 12th house be put? And then there is another spatial reasoning class where you want to count the number of gray cubes. So Mary had a shape using some white cubes and 14 gray cubes. How many of these gray cubes cannot be seen in the picture? And then you have augmentations of that. And then there is algebra class where you need to have some simple algebra skills to solve it. And measurement class is basically that you have a unit of measurement and you want to count the length of the whole thing by repeating this basic unit that you use to do the measurement. And then there is logic sequence puzzles like this. So this is basically, it's not, even though you select one answer from say A, B, C, D, E options, you essentially need to generate or synthesize a sequence as an answer, not just select a number. So this needs some sequential answering skills to produce a correct answer. So so that's the set of puzzles, or some glimpse of the puzzles that we have in our data set. And the hope was is to show that there is a lot of diversity in the type of puzzles that we have in our data set. And it is not just one skill that you would need to solve them, but you need a general set of skills, of basic skills, but general set of skills to solve these puzzles, and which a second grader can potentially solve. Now coming to the learning architecture, so we hope to have some sort of a AGI, or a general intelligence model, a single model that can solve all these 101 puzzles and their instances. I won't go much into the details of this learning architecture, but this is based on meta learning. The idea is that there is, maybe I can use a pointer. The idea is that there is, so our overarching goal with this architecture is that we want to evaluate state-of-the-art deep neural networks, like Bayesian models as well as large language models, to understand how effectively they can be trained or fine-tuned or out of the box taken to solve these puzzles. So the architecture has one is a puzzle image head, and then other is the question image head. These are backbones that we take from outside. For example, the puzzle image head could be a state-of-the-art computer vision model that can interpret images and produce state-of-the-art results on a lot of other tasks. For example, it could be a transformer-based model, or it could be a ResNet-based model, or any other model that is state-of-the-art out there. And puzzle question head is a large language model embedding of the question part of the puzzle. It could be a BERT model, it could be GPT, it could be anything else that you would want to try. And then the features extracted from these heads, these backbone heads, are going into a fusion layer using their own tokenization and other things, and extracting the features, and then these are fused And then we pass it through some multi-layer perceptrons to kind of fuse them better. And then the output is coming from either a set of heads. So that we assume in some cases, we assume that there is a specific puzzle head for that particular puzzle. So each puzzle has their own heads. Sometimes if you are looking for extreme generalization, then we don't necessarily need to assume that there's a specific puzzle head, but then it comes from a generic answer head, which produces answer to any question that the system has not seen during training. And we train it using this meta-learning loss. So you sample a set of puzzles and their instances, and then train the loss using either the softmax cross entropy loss or regression loss. And then once the answers are produced, we find the nearest answer from the 5 options and report that as the final answer. One part of this architecture is that we don't take the options as input to this architecture, but hope that the method solves the puzzles completely and come up with an answer which can be selected from the set of answers and options. So one demerit or problem or glitch with that is that you cannot use this idea of answer exclusion to solve the puzzles, but you have to come up with the real answer or solve the puzzle. So this is a bit more stringent requirement for solving the puzzles. Now coming to the experiments and results. So in order to understand this whole generalization abilities, we divided the generalization into 4 different categories. One is this extreme generalization, where you divide these 101 puzzles into 77 for training, 3 for validation, 21 for test. Now, this 21 for test is in no way included in the training set. So it's a sort of like a zero-shot generalization by training on the 77 puzzles and then testing on 21 puzzles, which it has never seen before. There is few shot generalization because extreme generalization, when we did the experiment, seemed quite difficult. So we ameliorated that requirement and kind of had M shot generalization, where out of these 21 test puzzles, we show 10 examples of those puzzles, 10 instances of those 21 puzzles in our training set. So there is a little bit of idea of what these puzzles are during training. And then there is instance split, which is supervised learning, which is basically you show all the puzzles to the method during training, but then there is a held out set from each of these puzzles. The instances are held out, which are used for testing. And then there is answer generalization, where from this held out set or from the training set, you remove or you don't show one specific answer during training, and that answer is used only during evaluation. And the idea is that if the system has not seen a specific answer during training, can it generalize or produce that answer during testing? We use 2 metrics for evaluation. One is solution accuracy, which is the golden standard, I would say, which is an algorithm should produce a correct answer irrespective of whether it's given choices or not. And the second is the option selection accuracy, which is selecting the correct answer from the 5 options. So in that case, like in some cases, the solution might be, the actual solution accuracy can be 0. For example, in this case here, the model produced an answer of 8, but the correct answer is 9. If 8 is not there in the candidate set, but the closest one is 9, then the method selects 9. So the correct option is selected, but the solution is wrong. So solution accuracy is the bar, and which evaluates whether the system has actually solved problem, and option accuracy is a little weaker. We also experimented with 2 settings. One is classification, where the system has to select one of the like number of options, or there is a softmax output. So if the range of answers to a puzzle is, say, for example, 0 to 255, then the answer, it has to produce a softmax cross entropy or softmax output from one of these options. So that is a classification based training of the puzzles. And a regression is basically instead of like a discrete range, you can actually have a continuous range. And So it produces a one-dimensional output, which is kind of rounded to the nearest integer. So it's and trained, the models are trained using L1 laws. And so when we did this evaluation, one of the important exciting things about this data set is that this is actually, these puzzles are actually from competition, in which nearly 3,000 kids participated. And so we have the performances of the kids from these competitions. And so we collaborated with the Math Kangaroo team, and we got the statistics of how the kids performed. And on average, over the 8 categories of puzzles, on these categories of puzzles, we have nearly 77.1%, which is a second grader performance. If we did not train any of these models, backbone models, but just used random guesses, either greedy selection or uniform selection of the answers, we get nearly 20%, which is selection from one of the 5 options. So before I get to that, so there are 2 numbers in these tables. The first one is the solution accuracy, and the second one is the option selection accuracy. So option selection accuracy is the performance from selecting the 5 options. So if it is random, if you randomly select the 5 options, then the performance is like 20%, which is what we would expect. And these are the performances on the puzzle split, which is the extreme generalization setting. So these puzzles the system has not seen during training, and it is trying to generalize only at test time. We also evaluated the recent CLIP model, which is a vision and language model on these puzzles, and the performance is 24%. And FLAVA is another vision and language foundation model, which was published in CVPR last year, which is again nearly 20%. So the performances on extreme generalization are really poor, I would say, or close to random. We did a few short experiments where some of the instances of these puzzles which were held out during the other phase, the extreme generalization phase, were shown, and we see that there is an improvement in performance. Even if you show only 10 instances from each of these puzzles, there is an improvement of about 6 to 8%, which I think shows that maybe these models have some capability of transferring the knowledge if shown some examples, but still not significantly better than random accuracy. Then we did a lot of supervised experiments, and as one would expect, the performances are much better, like almost double the performance that you would get from generalization experiments. And so on the right, you see a lot of different numbers, and I think the best number is with ResNet 50 plus BERT, or ResNet 50 plus GPT-2, where ResNet 50 is the image backbone, and GPT or BERT is the language backbone. Then even in a supervised setting, the performance is not really 80 or 80 or 90%. I think it's just still below or close to 50%. We tried different transformers and architectures like spin transformers, cross transformers, vision transformers, etc. The performances were within like 25%, and various language backbones, as well as vision and language backbones using on the supervised setting. And on answer generalization, we found that answer generalization is basically when you have not shown one specific answer during training. And if you look at this from a classification perspective, when you train the neural network for classification, the performance, it's close to 0 performance. Whereas if you do a regression, which is like you are not showing the discrete classes during training, but only regressing to the closest answer by a one-dimensional regression curve, then you see that performances are better, like 16.3%, which show that it's kind of clear that regression might be better in that situation, because you can actually produce answers which are an interpolation of the answers that you have seen during training. And coming to the supervised split, and when we compare to first grader and second grader performances, in supervised setting, we see that out of 23 puzzles we evaluated, nearly 6 puzzles in a supervised setting, the neural network model performs better. We also did some correlation analysis on the supervised setting, and we find that first grader is overall 22% or 0.22 in Pearson correlation coefficient. They are good in or nearly positively correlated by about 0.4 on one-step puzzles, but then on two-step or 3-step puzzles where it needs 2 or 3 steps to come to the answer, performances are not significant or not good. These are some evaluations on the different categories. For path tracing, we did not have any puzzles in the test set during that 2020 and 2021 period that we evaluated. But overall, I would say the best performing supervised trained model is inferior to that of the kids, even the first grade kids. We also did some analysis on the generalization. So this is a histogram of the accuracies that the system got over the 101 puzzles. Wherever there is blank, those are puzzles that were not used during evaluation because they were not from 2020, 2021, which we had the statistics on. And in some puzzles, it actually performs quite well, even in generalization. For example, puzzle number 74, which is this one at the very bottom, where there are some numbers and all these. So there is a number on this side and a number on the other side, and those numbers add up. The numbers on the opposite sides of the cube add up to the same number. So what is the number opposite to, say, 6? That is kind of the question, and it seems like it comes up with the answer nearly 40% of the time accurately. So there is some generalization that happens to specific puzzles, but not general enough for an AGI sort of a thing. We did some meta-learning ablation study, which I'll skip for now. And we then evaluated the recent large language models on a subset of the puzzles, which, if you recall, I had mentioned in the very beginning that there is about 15% of our puzzles have only language or need only language for getting their answers. And so we took those puzzles and then put it into ChatGPT and other large language model backed models. And so ChatGPT 3.5, which is on the 11 puzzles that we tried, it gets about 36.4% accurate, which is significantly better than what we had on our data set. On our backbones, for example, it was 15.1 if we used our resident 50 plus BERT or GPT-2, and then fine-tuned. Fine-tuned, not on that, but it's in the puzzle split. So it's extreme generalization, whereas ChatGPT gets 336. So it's almost more than double. So, but then there is still a significant gap from what human performance would be, which is 60.4. So there is a lot of room to improve, is what we gather. And then this is another interesting finding that we had, where we show how many times these large language models were selecting the same answer from 10 trials. And we see that these models are very confident in selecting the wrong answer most of the times. It's something to be brooded on, but that is what we have found, that it selects the wrong answer with confidence. So that brings to the conclusion of this talk. So we asked the question to start with: are deep neural networks smarter than second graders? And our analysis using this simple set of second grader puzzles show that they are not yet, not at least on simple math problems. But then it's curious to think about AI models in general, and then the kind of news that have been coming across, like AI models can pass bar exams, solve university level math problems, etc. So there seems to be something missing or something not right, because if a model can pass university level math problems, why can't they do well on simple second grader puzzles? And I think that is something to be thought through, and I don't have a concrete answer of why that is the case. Maybe one obvious answer is that their training set did not have these problems, but is that the real reason, or is that is there a more fundamental problem that we have to address? So one of the thoughts is maybe we need a more systematic approach to building AGI, taking inspirations from how humans develop their cognition. Maybe as we have very systematic ways to teach human kids to think and do things, and so maybe a more systematic approach is needed rather than putting all together into a learning model and make it to learn whatever it learns. So Thank you so much. And I would like to thank a lot of my co-authors and others who supported this, this work. And before I conclude, so this is an epilogue from Sebastian Brubeck's talk at Harvard on his paper on sparks of intelligence. So he gave this problem to GPT-4, which he was evaluating. And so 7 times 4 plus 8 times 8 is equal to what? And he asks GPT, whatever, 4. And it says the answer is 120. And then it comes up with a reason. 7 times 4 plus 8 times 8 is, we can use the parentheses to group multiplications, but they are not necessary. 28 plus 64, we perform the multiplication inside the parentheses first, then it comes up with the answer, the 92. Hey, wait, but you started by saying 7 times 4 plus 8 times 8 is 120. And then GPT-4 comes up with the answer. Oh, sorry, that was a typo. The correct answer is 92 as shown in the solution. Maybe there is a bit of a spark of intelligence somewhere if you look at it in isolation, is what I'm thinking here. So thank you so much, and let me know if you have questions.
Thank you, Anoop. That was absolutely fantastic. Great data, great results, great demonstration, and great question at the end. So does anyone in the room have any questions for Anoop? Here we go. This is our first question from a woman.
Oh, I was curious who the child was in your video of the child who was pitted against the AI.
Oh, that's my son.
Well, congratulations. He's obviously brilliant. There's quite a bit of research on the innate intelligence of young children and some discussion on how the education system flattens the intelligence that children are born with as far as creative intelligence. And I'm curious about narrowly defining intelligence or narrowly focusing on an examination of intelligence so much on arithmetic and what kinds of things we may be blinding ourselves towards with using such a narrow metric. I would love to hear your thoughts on what considerations have gone into putting such a priority on arithmetic and math.
Yeah, that's a great question. It's just a start, or I would say a tip of the iceberg, because math puzzles were something that we got access to quickly, and you can evaluate them maybe for their correctness easily as well, like the correct answer quickly. Maybe there is a reasoning that needs to be evaluated as well, and maybe there is a silly, careless mistake that you did along the reasoning process. All those things are there, but then you can easily get to the answer very quickly. Evaluate the answer very quickly. And but we are looking at other evaluations and other ways to do things. For example, if you are giving a child a real world problem of like maybe assembling some things. It could be a real world challenge, or it could be a simulated like a Minecraft challenge, and asking them to create some things. How effectively they do it. And so I think that there is a mix of different skill sets that you would need to solve any sort of puzzle or any sort of problems. And here we are putting things on an arithmetic background. But I think the skill set, or if you come up with an algorithm to kind of choose a skill set and then use that skill set to solve the problems correctly, maybe that kind of an approach or an algorithm's kind of ability to do that, I hope we can generalize that to a lot of other settings where the skill set could be replaced by other skill sets. So those are kind of things that we have been thinking about, and kind of proposing similar things for other tasks and in a more general setting. But then how do you generate the test cases and problem settings in a pragmatic manner? I think that is quite challenging in its own right. So yeah, so something to think we are thinking about, but yeah, maybe along the way.
Thank you very much indeed. I've got 2 questions from Bob Ray on YouTube and then another one here in the room. Hi, Bob. I'm wondering if you're the same Bob Ray, Robert Ray, who spoke earlier. But anyway, Bob asks, Anoop, did any problems in the training set include specification of the steps involved in solving the problem? And let's answer that one first, and then I'll ask the second one.
Okay, not really, I would think. Although there are, I mean, in some cases, the problem setting of a puzzle is quite constrained. For example, maybe the numbers are for a puzzle are from 1 to 10. So if you randomly sample these puzzles from the answer range of 1 to 10, maybe there could be repetitions. And we have tried our best to avoid such cases so that the training and test sets are entirely different. But there could be issues that way. But yeah, that's minimal is what we hope. But yeah, so the data set is out there and it's ready for public to evaluate. So if you find such issues, then please let us know.
Thank you very much. And then next from Bob, he says, it seems like we're asking the model to solve the problem without any intermediate steps. For the ChatGPT versions, did you explore chain of thought prompting?
Yes, we did. So for all the ChatGPT questions, or we posted to ChatGPT, the prompt was that it has to come up with a reason to solve the reasoning process in finding the solution. Like I showed in my some of my previous slides early on, some of these answers or the reasoning process is correct, but then it finally selects the wrong answer. So I think there is a mismatch in the way it selects the answer from how it does the reasoning. But in our case, we don't have a reasoning as such because our training is entirely within the problem setting defined by the Smart 101, and we don't have access to a reasoning process from the kids who solve these puzzles. So currently we don't have that, so we cannot really produce it. And we can only produce the final answer. But we'd like to have some reasoning if some data is available on that.
Oh, okay. Thank you for that. It's fascinating. So I can only speak to the logic problems, but why exactly are we doing AI that goes back 50 years? So my wife's an educational psychologist, worked in the schools with the type of kids that we saw. That's a gifted kid, clearly. Why are we doing it? And why are people who are seemingly intelligent writing papers where they talk about the sparks of AGI when the system is absolutely abysmal? Okay, 2 more years, that kid can prove the answer. Forget about getting the answer correct 100% of the time. Prove it when the teacher says, well, why? So maybe you can explain. I'm totally dumbfounded. You know, Ben said he's old. No, I'm old. 64, right? So this is insanity. How does somebody get paid to go up on stage and talk about sparks of AGI and show an example in which a simple problem of the type that you showed at the, can you explain this? Because I don't get it. I'm totally mystified, right?
Yeah, I agree. I mean, I think this is it's hard to understand. So the idea, I think, is that there is a lot going on in that trillion-dimensional space. Potentially, maybe similar, or we don't really understand what is going on in there. And the thought is that maybe in that space, it's a lot of I don't know. Maybe some weird things going on, which is creating this. So there, I mean, there are a lot of interesting ideas or interesting things that paper showcases in the Sparks of Intelligence paper showcases, and it's brilliant. But then there are simple things, which is also what we see in our data on our data set that are going wrong. And I don't know, it needs a bit more understanding of what is happening in these large language models and what we are missing out. I think that's kind of the curious question that we all have as well. And we don't have access to these large language models like ChatGPT and such, so we don't really know how to analyze it or understand it. But yeah, those are kind of the things that I think we should address going forward.
Okay, well, thank you very much indeed, Anup. We seem to be out of questions in the room, and we're also, oh, you have one? One more.
So, I've been listening to all these cognitive scientists and, all these blue sky stuff, but I'm a computer engineer. I build computers to solve problems, okay? And so far, people have been working on program synthesis, for example, for almost 50 years now, with almost no consequential results. So if you look at it from a purely computation point of view of, they were curating, language models, they were curating, there was computational linguistics, there were all these spheres where people were making they're putting in an enormous amount of effort with almost no payoff. And here you have a model which has zero human input. Okay, so all it's doing is it's just taking these billions of tokens, trillions of tokens, and it's just pre-trained this thing on these tokens. And it's actually generating a Java program that is correct. I mean, isn't that mind-boggling? I mean, it's kind of like, it is sort of complaining about the peanuts that you're served on an airplane when you're actually flying 30,000 feet in the air. So rather than looking at the 30,000 feet, you're complaining about the peanuts. You know what I'm saying? So this is spectacular. It's amazing from a computational point of view, but the cognitive scientists, I don't think they understand computation well enough to be able to comment on this thing. Okay. So I think it is amazing. It's incredible. It is mind-boggling. It is revolutionary. Okay, it can do a few math problems. Big deal, right? I mean, who cares, right? So someone said that yesterday, right? Academics is, what is it? Pointless or something like that, right? I mean, all these are academic exercises. They mean nothing. They really have no consequence at all in terms of engineering. Thank you.
Thanks.
How long is it? You can have 90 seconds. Can you rejoin in 90 seconds?
I hope it will be very short. Computer science as the basis for the reply. We have a hierarchy of problems, many hierarchies in computer science. These problems don't even make it into the hierarchies. These are algorithmically solvable problems with single algorithms, which in the polynomial hierarchy are absurdly easy. We also have the arithmetic hierarchy, okay? These problems are all solvable. The arithmetic hierarchy starts with problems that are further on. If we want to abandon the entire basis that we built for what computer science addresses and how hard their problems are, fine. You conveniently leave out the fact that if you want to verify a program of any complexity in the real world is correct, it's Turing unsolvable. And it's incredibly difficult. So if we want to just call these things for alchemically based programs and run them, fine. I want no part of that. I want a program that I know for anything that's high stakes works. And if we want to do that, it ain't going to be this technology. It's going to be some marriage of it, as we saw in the first talk, I think today, with something that's more rigorous. Thank you.
Thank you.
Thanks.
Yeah. Oh, we need to get
Rejoined her. I mean, I agree with Summer regarding AGI, and I mean, as Noah pointed out also, I mean, there are real computational limitations to what transformers are doing which can be worked around only in hacky ways. It clearly can't be the answer to AGI. And I mean, in my own work on AI with OpenGog, Hyperon, and Meta, I mean, we're trying to make something that can deal with all sorts of complex logic systems and whatnot, and grapple with these more advanced problems. On the other hand, we're not yet showing results like these results, right? And so, to take a much simpler example problem that we'll talk about in the NLP workshop on Monday, I mean, I spent many years, working off and on along with other projects on the problem of translating English sentences into, say, higher order predicate logic expressions that will roughly capture the meaning of those English sentences, right? And not necessarily fully capture it, which is a complicated thing, but capture enough of it, you could do a lot of interesting reasoning. And even in the domain like biology, like PubMed abstracts, which is pretty cut and dried, referring to some specific physical reality. And it was hard. I mean, we trained neural nets supervised learning wise. We made rule-based systems. We had combined systems, and it worked okay, but you're like eking out extra percentage points here and there. I mean, now playing with fine tuning and few shot learning on GPT-4 and Llama and other systems, we don't yet have the problem solved as well as we'd like, but we're getting just vastly better results at mapping ordinary natural language English, either common sense, blah, 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 or PubMed or whatever it is, into predicate logic expressions. And you can tweak it to do higher order predicate logic, first order logic, paraconsistent logic. So this problem restricted to sentences of the length that you see in regular human discourse. I mean, this is not necessarily high up in the formal computer science hierarchy, right? Because I'm not going to say transformers could solve this as n goes to infinity with really long sentences in some way. They can solve it for the sentences on the internet, which is indeed what they were trained on. But the thing is, a very high percent, in my own view, which isn't proven and may disagree with yours, in my own view, a very high percent of what I do every day, and I'm a fairly clever guy, is not that high up in these computational hierarchies. Like, I just do a lot of simple stuff every day, and a lot of that simple stuff does seem to be done adequately by these transformers. Like, an ethical judgment is one example. Like, I did a bunch of trials myself, just like give paragraphs posing everyday ethical conundra to a transformer, and then ask it, like, what would a benevolent, open-hearted, wise person say about this? It gets it right as much as a person. Now, there's loads of examples like that online, but I mean, a year ago, I had no system that could do that, right? And trying to make a system that could do it would have been quite painful and tedious with rules or supervised learning. So, I mean, I do think, I mean, I'm blathering on so long because this is sort of like this is really the key conundrum we see in so many talks at this conference, just given where the AGI field is right now. I mean, I think almost everyone in this room knows you're not going to get a human level AGI by taking transformers and adding a few little things onto them and improving them a little bit. I don't know that any of us really knows what nature of powerful system with what exact kind of power you could get by doing that, though, because of course, a pocket calculator or Google is already smarter than humans in some dimensions of intelligence. So in what dimensions of intelligence could you actually get a transformer to be how good by, even if it's not a human level AGI? We don't know that yet. And I don't feel like I know what percentage of a real AGI, a human level AGI system, a transformer neural net could be. Like, I mean, my friend Gary Marcus thinks the answer is probably like half of 1% or something. And of course, folks at OpenAI may think the answer is 90%. My current gut feel is around 20%, but we really don't know. And I mean, it's fascinating research topic. So, I mean, I think it is important to flesh out exactly what they can do and can't do. But I mean, it's also important to do as Selmer has done and say, well, there is this stuff, like people in this room can do that. There's not any reasonably plausible path to get transformers to do that just by tweaking with them a bit, or which is my view, which not everyone's going to agree with either. Yeah, go for it.
Thank you.
GPT-4 gets 100% of the Vinaigrette challenge questions correct. And humans sometimes only get 90%.
Well, I'm wondering if Anoop would like to rejoin, since it's actually still a Anoop session that we're having all these discussions.
Oh, sure. Yeah, I mean, there are things where I think ChatGPT and all other things get astonishingly better results than maybe second graders. I have seen examples where the second grader didn't get correct, ChatGPT got it right. So there is some things going on which we don't really yet understand, but then the point I think I wanted to make is that we should always take it with a grain of salt, the answers that it produces, and it need not be correct all the time, and there is still a long way to go. And like Ben was mentioning, I think transformers have an enormous, and it's a good computation platform to solve a lot of problems, but I agree that it might not be the right or it might not take us to AGI. Maybe there is something more important that is to be added there. Yeah.
Thank you. Thank you so much, Anoop, for your excellent and insightful speech.
Thank you so much. Yeah.
Right, we're now going to canter through no less than 9 technical papers. We'll do a short comfort break about 4 or 5 in, but we're starting off the architecture topic with Ben. Then we're going to jump back to cognition for a moment with Peter. But Ben Goertzel, Dr. Ben Goertzel, on bridging AGI theory and practice with Galois connections.
Yeah, so this is a 15-minute talk on a larger than 15-minute topic, and it's also a topic I talked about already in 2021 in the previous AGI conference, but I didn't submit a paper. So this year basically, so there's a long paper on ArcSci for those who are interested, which is called The General Theory of General Intelligence. I was in a even more immodest than usual mood then, and basically that tries to take you all the way through a sort of intellectual adventure from like what is intelligence, what is awareness, what is life, the universe, and everything, and take you through cognitive science and some philosophy of mind, all the way to why are we doing what we're doing with OpenCog Hyperon. Now I recorded like 6 hours of talks on YouTube, like walking through that whole paper, and I gave a compressed version of that deck at AGI 2021 in a talk. So I mean, if your curiosity is piqued by what I'm going to race through in 10 minutes or so here, then you should look at that. I would say the talk I'm going to give now is based on a paper I submitted for the proceedings this year, which is some little segment of, it's a blown up version of a little segment of the General Theory of General Intelligence paper, and will make most sense to people who have already seen the relevant bits of mathematics before, because there's just not time to really explain like what is a Galois connection and why in this length of talk. So now let me jump into some slides here. Okay, we'll start here. Okay, but that is not good. Why is that so big? All right, give me a moment to fix my PDF view. Oh, there we go. Okay, that's gonna do. So the particular bit of applied math I'm gonna go over here. It was born of the desire to take a wide variety of algorithms that I think are useful for building AGI systems and cast those algorithms in a very common mathematical framework, not just because that's a sort of elegant thing to do, because I wanted to be sure that our new version of OpenCog, the OpenCog Hyperon system, could do all these things efficiently. So if, we could try to make it do probabilistic logic reasoning, evolutionary program learning, attention allocation, probabilistic programming fast. But it seemed like, okay, why not instead try to cast all these in some common form, so then we could just make that common thing fast inside the interpreter for the language called Meta, METTA, Meta Type Talk that we built for the system. So I started by basically trying to represent all the AI algorithms that we want to use in our AGI system as approximate stochastic dynamic programming, which if you think about it, they kind of all are. I mean, reinforcement learning originated as approximating like Bellman equation from dynamic programming. And so I formalized that as something called a discrete decision system, which is just a system making an iterated series of decisions based on trying to minimize some cost or maximize some reward. And each decision it makes affects the state. So that's a very general and not very original way of looking at things. And in the paper, I go over how to portray various cognitive processes in these terms, such as spreading activation or function optimization. So I introduced what I call combinatory operation-based function optimization, which is a fancy name for something really simple. Like you have a bunch of guesses at things that might optimize a function. You combine them with each other by some combinatory operations. You pick the best combinations by some heuristic. You see how they will do it on the objective function. You take that data and feed it back in to guide the making of new combinations. So you have sort of a cycle of combining your guesses by some operations, filtering them, evaluating them, using the results of the evaluation to help with the combination and filtering. And this sort of process is also a discrete decision system, right? I mean, this sort of process also pretty much can be cast as approximate stochastic dynamic programming if you want. And you can write that in pseudocode, which I did in the paper. You can also view it in an abstract way as a sort of probabilistic programming, because what you're doing, you have a bunch of combinations of earlier guesses and you're sampling from them from some distribution. And then you're taking the ones that you drew from that distribution and you're evaluating them in the function, getting new data, using that new data to guide the sampling your next time around. Then you can then make this recursive in an interesting way, wherein the algorithm that you use to guide the sampling based on the data could itself be another discrete decision system, right? So then you have, but there's a long lineage of learning probabilistic programs that learn probabilistic programs that learn probabilistic programs. I mean, so that many of these things have been seen before in particular domains. Now, what we're doing in the OpenCog system that we had a whole workshop on yesterday, which you could see the proceedings of on YouTube if you're interested. We're building an AGI system where the central architectural component is this large knowledge metagraph, which is a sort of souped up version of a graph with like a hypergraph plus links to links, links that point to multiple things, links that point to subgraphs and so forth. And so the model we're using there, we're trying to view the cognitive processes underlying AGI as hunks of a metagraph, which are then interpreted as transformations that take part of a metagraph into another part of the metagraph. And these particular metagraph encoded programs for metagraph transformation were in many cases interpreting these as combinatory operation guided function optimization, which can be arranged in this sort of discrete decision process, which is approximate stochastic dynamic programming. And so this leads into a line of thinking regarding metagraphs. You can look at untyped metagraphs, undirected metagraphs, directed typed metagraphs, and there's a connection here with germs and sheaf theory and stuff, which I won't go into. But you can also look at paths through metagraphs, which is sort of like a path through a graph, except your edges are snaking around and pointing to many different things. you can construct these mathematically using initial algebras and build up these metagraphs bit by bit from a bunch of different constructors. And you can look at different sorts of initial algebras, like different sets of basic combinatory operations. You can look at the topology on these metagraphs, which has to do with Hating algebras, which is a similar algebra used inside intuitionistic logic. And this leads us to some practical functional programming-y stuff, which has been important in designing the OpenCog Hyperon system. So one sort of operation that's often useful to do when implementing complex algorithms using functional programming is fold and unfold. And if you've done programming in Haskell or Camel or something, you've seen folding over lists. Then you can also fold over trees. Here we're folding over metagraphs. And there are other weird sorts of folds where you can fold through a data structure and carry memory through as you fold. And these have a bunch of unnecessarily weird sounding names, like histomorphism that counts the history, or futuremorphism where you're unfolding, and so forth. And you can look up the members of this sort of morphism zoo. But one conclusion I came to is that most of the algorithms I wanted for AGI, I could implement as folding or unfolding over a metagraph. In particular, the fold and unfolds that carried memory, like the histomorphisms and futuremorphisms. So I came to the conclusion, within a rough degree of approximation, if I could make histomorphism and futuremorphism over a metagraph fast, then I could probably make a lot of the algorithms I need for AGI fast, which posed me the technical problem, like how to make an interpreter or compiler to make these operations fast, which led to a bunch of the stuff we discussed yesterday about compiling our metagraph language into Greg Meredith's row calculus and his efficient row calculus compiler for concurrent processing and so on. But what I'm talking about here is sort of mathematical reduction that led me to think, if I could do this sort of folding fast, then that lets me do a lot of the stuff I want to do inside an AI architecture fast. And so I go through some work to formalize these sorts of morphisms on directed type metagraphs, which it's a special case of a bunch of category theory, but it hadn't been articulated for this case before anywhere I could find. And that's too much to go through in a brief talk. There's all these ugly kinds of morphisms. But the bit of this that I wrapped up in the paper in the proceedings had to do with Galois connections, it's a particular sort of adjunction if you look at it in categorical context. But there's a literature specifically applying Galois connections to certain sorts of algorithms in a functional programming context. And basically a Galois connection, it's a pair of adjoint functions just mapping one partial order into another in a nice way, which you can see from that equation there. I mean, the pointy less than the square less than are two different partial orders, and you're moving f on one side to g on the other, and the connection is between the f and g. And there's a literature in the functional programming world that uses this to find nice ways to do things. So like the standard Euclidean algorithm for doing long division, as a classic example, like you can derive that this way by the Galois connection between multiplication and division. And so this is used in functional programming to do sorts of automated programming. Like, can you automatically derive the Euclidean algorithm for division? Well, you can if you just know how to do multiplication in the simple way, and then you set up this Galois connection. You can automatically get the standard algorithm for division. And so this hasn't had that big a practical use in the functional programming world, but it's one of these things that always seems like it should soon have a really big practical use, and it's quite cool. And I would say, these fold and unfold were the same way as was category theory. When I was in grad school, they weren't that useful. It seemed like they would become that way. Now they're super useful in functional programming land. So I realized this combinatory operation-driven function optimization, you could use Galois connections to formalize this and figure out nice ways to represent the sort of iterated combination and function evaluation scheme to implement that in terms of fold operations. So greedy optimization was the first case to look at, and a lot of AI algorithms in practice are based in greedy optimization in some form or another. And evolutionary learning you can view as a sort of greedy optimization on the space of populations, actually, and hill climbing, steepest descent. I mean, all these things are in the end a sort of greedy optimization, and you can express greedy optimization as folding. And this is a theorem in the paper, but I mean, it comes pretty, and the notation is forbidding enough. I'm not going to try to explain it in 1 minute. You have to look at the paper, but it falls fairly directly from previous results in functional programming literature. So if you have a greedy optimization algorithm over a metagraph, you can use the Galois connection to reorganize that into folding a certain operation over all the nodes and links in the metagraph. And so this gives you a way to turn it into a sort of nice iterative thing. Now, the next step there is to use Greg Meredith's row calculus to take this fold over the metagraph and do it concurrent processing over all the processors in the GPU. But you can do that because you've written it as futuromorphism and histomorphism, which is nice and elegant functional operation. But you can also represent dynamic programming as a Galois connection, and including the approximate stochastic dynamic programming. And that gets you further toward reinforcement learning, probabilistic programming, various sorts of inference control. There come out to be some interesting math things there. So if you're combining guesses and then sampling from the combinations and evaluating them and taking the evaluations to guide your sampling, that works if your combining operation is associative, and you can make all the Galois connection stuff work. If you're combining guesses in a non-associative way, then you can't munge the parentheses around, and you don't get a Galois connection route to representing dynamic programming as fancy folding. So you do, and this sort of finding was actually a relief to me, because if things are too easy, you get the feeling it's trivial. Like you want there to be some restriction on what operation can work. So it seemed that the same math of Galois connections you can use to connect times with divides and then figure out Euclidean algorithm for division. Seems like you can use that same math to take greedy algorithms, dynamic programming algorithms, and rearrange them into folds over the metagraph. And then that's nice in terms of guiding language design for AGI, because it means if you have a language interpreter and compiler that can do these fancy folds over metagraphs in a fast way, then maybe you can do your AGI algorithms in a fast way. And there's some caveats here which are ugly and we haven't fully worked around. And that's always the case in building real AI systems, because of course there's a question when you're folding over this graph, are you modifying the graph as you fold? Like if you're modifying the graph as you fold, then all the theory doesn't hold exactly, right? No, you don't have to modify the graph as you fold, but it's sort of the cognitively natural thing to do, right? So if you do modify the graph as you fold over it, then you have like approximate versions of all these theorems I didn't bother to work out yet. But I was sort of heartened that so much of this worked, and we're using this not so much to figure out the cognitive parts of the AGI design, but we're using it to figure out how to make an efficient implementation for the AGI design. But this does tie back to sort of the broader themes we're seeing in this event, right? Like I was teaching neural nets in the 90s. Recurrent backprop on a 30 neuron network took like 3 hours on the servers I had when I was a professor then. So now we've got massive scale behind transformer neural nets, which they're not recurrent. You got attention replacing some recursion, but they're not that recurrent. But just adding all this scale allowed these networks to do some quite amazing things, even with some little bits and pieces of emergence here and there. So the open question that's in everyone's mind is, okay, well, what if we take all these other cool algos from the history of AI, like, say, logic theorem proving or evolutionary learning. What if we take these other algorithms and we jack up the scale tremendously also, right? I mean, then what happens? Do we get more magic emergence? What if we connect those all together, right? So the infrastructure is different though, because these aren't just matrix multiplication, right? Or not in the simplest, most natural way. So what we've been trying to do is figure out how to take logic, evolutionary learning, certain types of probabilistic programming, take these things and build an infrastructure that will let you do them super fast. That becomes harder because these are graph-based. It's harder because they're not sort of map-reduce oriented. You need things like row calculus, which is fancier to make them efficiently concurrent processable. But it seems to be doable given current compute hardware and current state of computer science theory. So if you want to dig further into this stuff, you can look at the videos from the OpenCog Hyperon workshop yesterday, or the videos or the full paper on general theory of general intelligence, and it goes through all of this. This was sort of the abstract to the abstract, but if you're mathy enough, it may whet your appetite. Thanks a lot.
Thanks very much, Ben. Do we have any questions for Ben in the audience? Thank you, Noah.
So I like massive hylomorphisms as much as the next nerd does. But that's only one of the directions of scaling, right? The other direction of scaling that's turned out to be important is the amount of data.
Yeah.
Can you say something about like, how do you get a massive amount of data into a system?
Yeah, I would say amount of data can be measured in various ways also. So like in an applied context, we're working on problems in genomics where you have like 15 populations and massive gene expression and mutation data. So that's a big body of data, but there's a small number of examples. And we found this sort of system is much better than current neural networks at dealing with data that's like small in one dimension, but massive in the other dimension. But in concrete sense, there's two ways we're working to get massive data in here. One is, as will be talked about by Andres Suarez and Manhin in the workshop tomorrow. I mean, we're using LLMs to translate the web into higher order logic form and then feed it into this metagraph. So, I mean, the thing is, we just need to massively scale up our system to handle all that. So, like, we're starting with Wikipedia, which used to be considered big, but now is trivially small. The other thing is, I mean, we're working with humanoid robots. So we've been working with Hanson Robotics, with the Sophia robot, and other humanoid robots for a long time. So, I mean, we're feeding in auditory, a limited amount of haptic, a lot of visual data from these robots. So far, we've been using sort of standard deep neural nets using Torch, and then having a symbolic network that connects into the Torch compute graph, right? So we haven't been trying to do the perception in the symbolic network. We've been doing perception neural net and then getting neural symbolic. So I do think the data requirements for this sort of system in principle are probably significantly lower than with the transformer, but because it is trying harder to abstract, but they're still going to be large, and exactly how large they'll be is going to be empirically discovered.
Ben, thank you for the talk. What you can say about the hardware, where we are at in terms of
well, this is
efficient
a beautiful chance to advertise for the AGI hardware workshop tomorrow, where I will, among other things, I will present a new chip design I've come up with, which does metagraph pattern matching on the chip. And then Rachel St. Clair who's maybe somewhere here, no, she's hiding, but Rachel St. Clair will present her chip for hypervector manipulation. And one of the things I didn't talk about here, but we can project nodes and links in the metagraph into hypervectors, like large bit vectors. Then you can do a number of search and manipulation operations in the hypervector embedding space. So I do think there will be a role for various kinds of specialized hardware, just like GPUs, which are these specialized matrix multipliers, have been super useful for deep neural nets. I would say also, though, you could do deep neural nets on CPU if you wanted to. I mean, it would be more expensive. There's enough money on the planet for it. The advance would have been slower if you had to spend that money. So in the same way, I mean, I think We can use Greg's row calculus stuff to boil down graph operations onto GPUs in a quite efficient way, going beyond what MapReduce can do. You still can't do as well there as you could do with dedicated hardware, right? And Roland compiling to the dedicated hardware. So I mean, that's exact amount of speed up on the algorithms we care about is to be discovered. I'm optimistic we can make a lot of progress even without custom hardware. But I mean, just like you saw with GPUs, like probably without custom hardware, we can do really cool things on a network of server farms. And if we want to put OpenCog Hyper on doing smart reasoning on your phone, you may need the special chips in your phone. That's sort of how I think it's going to go.
There's no concrete answer to this one, but I would like to hear your voice. You talk about using the galleries connections in order to improve the efficiency of the system and also to use Greg's work. But what magnitude of improvement will it get? You can choose like an example of implementation and like provide a factor of improvement.
Well, there's a lot of different things happening to try to make this system efficient, right? And so taking an algorithm and formulating it as a fold operation is one step. Then taking that fold operation, mapping it into Roland, which does its own rewriting to put it on the GPU is its own step also. So I think each of those steps probably has a couple orders of magnitude improvement in it over what you would get if you were implementing in a very naive way and running on a single CPU processor. Because you can get a dramatic improvement by folding instead of implementing in a very naive, greedy algorithm way. And then with Greg's stuff, if you have 600 processors, you can get a speed up of that same magnitude. So I mean, we're looking at many orders of magnitude speed up, not just a small constant factor. There would be other ways to speed things up also. There's always many ways to speed things up, but I think we're in an interesting position here because we've been prototyping with these algorithms in OpenCog project for quite a long time. So we're hopefully not doing a lot of premature optimization because we've been, writing papers and doing simple small scale experiments with these things. So we know at least the algorithms are somewhat useful for some things and not totally dumb. And now the question is, if you run it on shitloads of hardware and speed up by a few orders of magnitude, then what sort of magic happens? And I wish we had a theory to tell you what sort of magic would happen. We don't even have that theory for transformers, really. The study of scaling in these systems is mostly empirical, and we're sort of in the same position with what we're doing now. So how much speed up is one thing, but how much improvement of end user behavior do you get when you scale up to a certain level is a more important question, and we don't have a solid answer to that.
Thank you. I'm just going to ask one more quick question for a quick answer from YouTube, please.
True or false question?
Yeah. Santa asks, well, it actually is a true or false question.
Santa Claus?
Yes, Santa, who's been asking some great questions.
I can't, if he won't give me any presents if I don't answer the way he wants.
It's yes, Santa.
All right.
As can node of a metagraph build in both symbolic and sub-symbolic integration, and the sub-symbolic part can handle a large amount of data.
you can so that's not a simple answer, but I'll try to keep it short. I mean, in the metagraph knowledge representation that we use in OpenCog, you certainly could represent any level of sub-symbolic data in there if you wanted to. I mean, you could represent individual pixels. You could make quantum truth values on your nodes and represent everything that happens in a bubble chamber if you wanted to. Now, as we've actually are working with it, when you have data that's, say, auditory or data that's visual, we found it just much simpler to process that data within a deep neural network. And then, say, each layer of the deep neural network, you put connections into the metagraph. And I mean, this kind of makes sense because, I mean, what comes out of the camera, it's a square grid, like it is a matrix, right? So then why not use a representation that is a series of matrices at various scales? So I guess the answer for now is you certainly could put all this into the metagraph. It's by far at the moment not the most efficient way to do it. So instead, we're working with neural symbolic systems where you take various deep or shallow neural networks and you tightly link them into the metagraph. That doesn't mean everything in the metagraph is symbolic in a cognitive sense, in the sense of like Peircean semiotics of manipulating symbols. Like you can do stuff that's very sub-symbolic using these nodes and links, in the sense that it has no clear symbolic reference. It's just a pattern that computes something from something else. But for dealing with large dimensional, like floating point matrix data, we're still tending to use neural nets and then link them into the atom space metagraph. What we're doing once we have our chip, who knows, right? I mean, to be discovered.
Okay.
But we should move on, I think.
Okay, thank you very much indeed, Ben. Right, next up, I'd like to introduce Peter Isave, who's one of the, I hope I'm pronouncing that right, who's one of the organizing members of AGI-23 here. He's a PhD student in the Department of Computer and Information Sciences at Temple University, working with Professor Pei Wang, part of the Temple AGI team, which does research and experiments in the field of artificial general intelligence. And he's also one of the organizers of the Nars workshop. So please welcome Peter, who's going to talk about memory system and memory types for real-time reasoning systems. Thank you, Peter, and thank you for your patience.
That's fine. You're welcome. And here? Okay. 1 second. Right. So thanks, everyone. Today, I will try to talk about the memory for the reasoning systems. And I try to keep it short because we are already lagging behind. 1 second, I just remove that Zoom window out of the way. Just okay. So there are many desired capabilities for the AGI system we would like to have. And in particularly, AGI systems should efficiently process various types of knowledge. They should decide where to store this knowledge. They also have to know for how long it should be available. And they should efficiently retrieve it for inference, question answering, and goal processing. In particular, the real-time operation becomes a fundamental requirement when we're designing an AGI system, and especially when we're choosing a memory structure for it, because it has to support multiple memory types and efficiently process it into the constant time. Even though there are lots of rules to be applied, it's still going to be a large constant time of applying those rules. Here, we also need the resource allocation to integrate within the memory components. And that's required because we all know it doesn't matter how large the storage is, it's just a matter of time until it will be full or it reaches its full capacity. So in this discussion, we want to talk about the memory types in reference of Nars reasoning system. In particular, we want to show the memory structure and memory types used there. And because we strongly believe it will help others struggling in the same subject, and that some of the problem will be transferable and highly relevant to the community and to development of the other AGI systems. Now, Nars reasoning system is basically a general purpose reasoning system proposed and firstly developed by the Dr. Wang. It operates under assumption of insufficient knowledge and resources, and it has a finite process demand. It's always open to accept any new knowledge during the runtime, and it operates in the real time, so it conforms to the real-time operation. Nars uses the non-axiomatic logic. Null logic is actually the logic we truly believe, the logic to go to deal with uncertainty. I will introduce some Nars consideration because it will be like a building blocks to proceed to understanding the memory types. Now, on the left, you can see the very high level implementation independent architecture of Nars. And you can see there is a red box. I would say it's an inference engine. So inference engine fetch some memory type, some memory items from the concept memory, then produce some derivation and either outputs to the environment or puts to some data structures or like component buffers or priority queue. And this is proprietary for the implementation. We're not discussing implementation here in detail. Something is mentioned in the paper, but here we try to stay away from it. So this is the cycle goes on and on forever until the reasoning continues. And the key things here is the memory in Nars is a concept-centric semantic memory structure in accordance with the null logic. So basically, it's a graph where the concepts are represented as nodes and links designate the relationship between them. Technically speaking, the memory is a collection of concepts representing a conceptual network with prioritized nodes and links. And here is important to introduce the budget. Budget is actually how important or importance of the data items to current context on the system. So budget is amount of system resources allocated to a specific item to allow priority-based selection. Budget actually summarizes multiple factors as taken into the consideration, including the urgency, salience of item, and its current relevance to the current experience of the system. So one of the key idea in Nars memory is the concept, the role of concept. So the concept is actually the major entity. It's an identifiable unit of systems experience that has a grounded meaning. So it also serves as a unit of storage that holds various components of knowledge. So as you can see, it's here on the right. So this is the diagram of the concept. Again, implementation independent, but we can see there the concept by default should have some data structure there to hold some information about knowledge. And it can serve as a blueprint for different other implementations. So it has definitely the links to other concepts and implementation specific. It can be different types of links. Because, for example, OpenNARS and ONA, we have different links. It also have a declarative information storage, episodic information storage, and procedural informatic storage. Those are dedicated storages allow for efficient querying and processing the reasoning during the reasoning cycle. So we can see that item distinction based on memory type already can be seen within the concept. So, for example, procedural knowledge, which is in null, is a form of temporal implication, is typically stored in a specific table for faster inference within the concept. Now, episodic information is also present within the concept. It's basically present when events are being separated from the eternal beliefs. Now, in Nars, there are events and there are the beliefs. Events is basically information, it is a declarative knowledge with attached temporal information, episodic information, conceptually speaking, and occurrence time. And the beliefs are semantic declarative knowledge, which has the declarative knowledge within structure of the terms, but it doesn't have any relevance to the temporal information. So basically no temporal information is provided. And also we can find some declarative distinguishing of the knowledge within the concept on the concept level for eternal beliefs. So for example, we have the belief tables in OpenNARS and as well as the ONA implementation. Now we can go ahead and actually classify and think and analyze the memory in terms of types as other AGI systems, as well as other cognitive systems like LiDAR, for example, that has multiple components and multiple memory types with the proprietary structures within it. So it happens that OpenNARS has mostly all of the memory types, but the difference is that the memory system in Nars is unified and intertwined together to allow real-time and efficient reasoning. That's the huge distinction, actually. Now, we do have a declarative knowledge, of course, declarative memory in the Nars, and that basically contributes to the most content of the main memory. That is, the knowledge has been processed to become a concept nodes without episodic or procedural information. As a slide go back, so we can see here the buffers, for example, right? And we can assume there are lots of items, lots of knowledge is processed within the buffer. However, only some are being selected and make it the selection to the concept memory. So whatever have been selected to the concept memory and whatever does not have episodic or procedural information, it's supposed to be a declarative knowledge in Nars, a declarative memory in Nars. And it turns to be like most of the memory is a declarative. Now, episodic is basically events or compound events, which is, again, a declarative knowledge with temporal information, which reach the selection to the main memory. And upon the perceiving of an event, its episodic information is stored locally to the concept level. Again, so we have some implementation-specific data structures and components where events, because they don't require shared term to proceed with reasoning. So we have some special components where we need to do some composition of the events. And sometimes there will be very very many those composition of the events, and only few can really survive to be selected from all of those components, buffers, and priority queues to make it to the memory selection, and then being transformed to the concept, and episodic information will be absorbed. So all whatever is already absorbed in terms of declarative knowledge with temporal information, we consider to be in episodic. Now, procedural, it also exists in an open Nars, and actually is a declarative knowledge, kind of declarative knowledge, which includes operation or compound operation within its description. Now, procedural information also is stored locally at the concept to allow efficient processing and efficient derivations. At the end, I will have a couple of examples that will be clear to illustrate how it's actually work within the memory. So now we will try to do different classifications, like in terms of long and short term. It appears that technically we may be able to classify the memory in terms of long short term, in particularly that declarative information can be considered a kind of a long-term memory. However, declarative information can be removed from the memory by resource allocation. So there are possibly two scenarios. One is that the data structure is completely full. So what are you going to do? You just remove the whatever low important items for us. The second scenario is, for example, the importance or the budget of the certain data element has really decreased to the extent that that cannot actually compete for the resources because the importance is very low, and system never selects that element and just stays in the memory for whatever until it's being overflowed. So in this case, so resource allocation can be seen as a decisive factor where to select a certain type of memory to be a long term or at the short term. Now, we also have two notions of memory in open Nars. In Nars is working memory and attentional focus. So the working memory is the priority-based selection during the current cycle within the main memory and implementation-specific data structures. So what we currently selected from the concept memory and what we currently selected during this single reasoning cycle from all of the data structures within that concept, we consider this to be a working memory because once we complete that cycle derivation, all the data items will be going back to their corresponding data structures, and their importance will be adjusted correspondingly based on the reasoning and based on the premises and how important they are. Also, the attentional focus is we could see it as a distribution of a higher priority within the priority-based data structures. So we can see it is that knowledge most likely be processed in the future unless derived or a new input task have a higher priority. So whatever higher priority or higher importance distribution within every data structure, we can see as attentional focus, because if something does not come up higher with more important than this, so system actually will keep that in its attentional focus until those importance is being lowered after the reasoning. Now I will show a couple of examples and we will understand how it works. So the first example actually introduces the simple problem of opening the door using a handle and knowing that the door is unlocked and knowing if the agent is in front of the door. So there are only there's only three inputs here and some system outputs. And the system is asked to derive the procedural knowledge, giving those input. So in the first and very beginning, it just says actually, if door is unlocked, if door is unlocked and something is in front, then using the handle we can open it. That's a piece of declarative knowledge. And right here we already have the embedded information of the episodic knowledge with in the form of temporal implication. Oh yeah, you can see it over there. And then you also can see here that's embedded in procedural information in case of the use operator or operation. So then we supply two events, which are declarative knowledge with the temporal information, basically in occurrence time. So we have the instance of door one is a door, and that's the same door one is actually unlocked. So we're just observing new instance of the door that's recognized to the system and to be unlocked. So those are the inputs. Now system outputs like the following. So we see that the door is become unlocked and it's the door. It's basically open Nars using the compositional rules combines the previous inputs to create those derivations. So that's the first derivation. The second derivation, however, using deduction rule, Nars is able to derive the operation and actually open the door once it will be in the state of the, once it will be in front of the door, and once once using the handle to open it. Now, it's interesting to see how all of those sorts of different types of knowledge interact within the same memory. That's what we see. What we say that the knowledge is intertwined within the same memory, and memory looks like a unique structure, a unified structure. So this is a memory fragment which is taken out of the reasoning cycle in the real time, and we can see that the red 3 nodes are actually corresponding to the inputs. So for the top input and the 2 events, those are the red nodes, right? Now, the orange node is actually the first derivation that Nars makes. Is a matter of composing those 2 input events into the one, right? So door is unlocked and the door. Now, the further derivation is made by the actually producing the procedural knowledge by opening the door with the use operation by using a handle. And we can see it there, the purple nodes. So we now derive that the door is in front. If the door is in front and the door is open over there, so that's the link. The red link is the representation of the visual representation for the procedural knowledge, such that we can use the handle to open the door. That's what it says. And now we can see, so all of the information, episodic, procedural, declarative, all of them present within this memory fragment. And yes, also the gray nodes is basically the terms, decomposition into the concept which are connected using the green links. And this might be implementation specific. Now, the second example I want to show is that just to illustrate that discussion about the long-term or short-term memory might not be very meaningful in the context of Nars. So the idea is the following. We try to learn the alphabet with the system. So basically, we try to input the letters to the Nars. And that's the pieces of the declarative knowledge. So we just have a list, have a long list of inputs. So we just say, is A is in letter, is B is in letter, C is a letter. So we're just providing that declarative knowledge, which is supposed to be a long-term memory. Now, somewhere in the middle, right, maybe, I don't know, in number 5 or 6 inputs. So we just submit an answer here, supply an answer here, meaning that are A and B also letters, right? So, I'm sorry, the question, not answer. So we submitting a question to the system and asking, are A and B also the letters, right? And system responds to us, yes, that A and B are the letters. So the frequency 1 and confidence 0.81. So very confident response. So yes, the derivation are registering. So new declarative knowledge is being produced, and it's again been stored. And we continue then to enter other input like V is a letter, W is a letter, Z is a letter, etc. Now, whenever we entered all of the sequences of letters, not the sequence, all of the letters, including capital letters, we assume that the information is in the memory along with those derivation, and we now start to ask simple questions. For example, is A is a letter, and the answer is yes. B also yes. So all of the single letters looks like it remembers. However, when we now ask, are A and B are letters? So the answer is none. But wait a second, we just had it before, like, I don't know, 30 seconds ago. And then we ask another something like, are C and D are letters? And again, the answer is none. And it looks like actually the derivation has been made and it was registered with the memory, of course, and was living in the memory until the data structure became overflow, and it has to be kicked out due to low priority, due to low importance of these data elements to the Nars. However, if we ask for some sequences of letters which corresponds to the last inputs like T, U, V, W, or X, Z, it remembers because it's still most recently used, and it still thinks of them as an important concept at this current stage. So now I think We almost reached the time limit. So I will just go over the takeaway here. And the takeaway is the following, is that OpenNARS or NARS has the unified structure, allowing the same piece of knowledge to contain declarative, episodic, and procedural components within it for efficient processing. And different forms of knowledge actually are interacting and being processed within the same memory during the inference process. Now, NARS does not include the well-defined separate components dedicated for different processing type, but it features its own integrated approach to memory, and that that long and short-term memory classification actually might not be very meaningful whenever we talk about the NARS and its classification by the duration. I think I will stop here. Thank you very much.
That was fantastic. Thank you very much, Peter.
Sure.
Janet had to step out for a bit, so I am the Janet right now. Any questions from the room?
Is there any benchmark available, like number of concepts that it can process and how fast?
There have been, but I don't remember now from top of my head. Yes. Yes, we can probably take a look later. Yeah. And it's also implementation specific now. So different implementation gives a different results. But yes, good question. Thank you.
I really enjoyed the breakdown of the declarative, procedural, and episodic knowledge. Have you tried putting NARS in the cloud? Have you done any runs with
Not at the moment.
The cloud system?
Not at the moment.
Okay.
Questions? All right, fantastic. Thank you so much. That was wonderful.
Thank you.
And it's my great pleasure to present Selmer Bringsjord. Hope I got that right. Who's been asking fantastic questions and obviously very familiar up here. The Mu cognitive, did I get that right? Mu cognitive, correct?
Yes, approximately anyway.
Approximately. Meta architecture as touchstone for standard modeling of AGI level minds.
Probably a second grader could do that. Yeah, that goes here. Okay. Are we working? No, we're not. Interesting. Let's try. So we don't care about the title slide. Yeah, two of us are doing corporate stuff. We don't care about that. Actually, it's Ben who brought me to this point years ago in saying, I do agree that you should follow me in looking at academic education and the role of that in AGI. It was his idea, and I'm trying to do it. The last keynote related to this. That's my kindergarten, still there, founded in 1936. So I'm really talking about the grade progression. This meta architecture, though, goes past grade 16. So you have to go to school for quite a while. And you did, so you're in luck. You'll be able to understand. There's the magical, apparently, second grade. Yeah, I could have gotten all those problems that were shown 100% correct quickly. And then my mother would have said, that's not that great. You need to show me the proofs, and I would have shown her the proofs. So There are a lot of cognitive architectures out there. I don't know, 75 is conservative. So I'm showing a breakdown that I got courtesy of one of my grad students, who's also a Nars expert. Fortunately, I don't know, say there are 75. So what I'm trying to do is figure out if there's a way to standardize them somehow, formally. I really don't care per se about human cognition specifically, but it's got to be human level, could be alien, could be above human level, it doesn't matter. I don't know for sure if all these are geared to some particular level. I don't think so, but that's the idea. So if there's a capital X appearing as a variable, it refers to any cognitive architecture, okay? The subscript on it depends. And this is the foundation for the whole thing. It's actually a relatively simple idea. What we want to do is take, here it is annotated. We want to take the kind of natural language sentences that have been uttered by the smartest humans since at least Euclid and come up with the definitive formal expression of those first. So here I'm just going with 2 + 2 = 4. That's the SA. The A is an agent. So that's just a set constant, if you will. And then I will just tell you that the Mu cognitive architecture has the classic and indisputable gold standard formalization for what that means when some agent believes that 2 + 2 = 4. Now you could say, well, I'm prepared to throw away all of formal science. That wouldn't be good. Mu is not a candidate in the race or the competition of what you saw earlier in those 75+ architectures. Mu is based on what we cannot give up. We might be able to give up sort of, some aspects of quantum mechanics. We're not giving up P&R arithmetic, okay? And so this doesn't even have quantifiers in it. That's what we start with. So we've got this biconditional as a given, and then we have the goal for any cognitive architecture that wants to measure up of establishing or having someone else perhaps establish that biconditional, that statement that some agent believes that 2 + 2 = 4 holds if and only if something happens and is represented in the cognitive architecture in question. But the trick is, the challenge specifically is that we have to prove 2 up there. If we have the given +2, then we can prove that standardization has been achieved. Okay, so this is the basic idea, starting simply. All right, so in the paper, we describe 2 pretty much expected success stories, and they are SNEPs and Nars. So I can't say for sure that the proofs in the case of these theorems are formally verified, but I would come close to staking my life on this. All right. And then it's been pointed out to me before the paper came out and we circulated it, Selmer, you actually claimed in the literature that Clarion could do this. And you're supposed to know that John Anderson, in the case of ACTAR, once upon a time, many decades ago, actually said that first order logic was the basis for the declarative side of ACTAR. So you should probably say that those achieve standardization of the level of 2 + 2 = 4. So I'm going to put check marks there. Now, yes, I couldn't resist. If we move outside the category officially of cognitive architectures, what happens with GPT-4? We just set it to one of the cognitive architectures, and then very much connected to the first keynote talk today. Then we go to P&R arithmetic. So we want to go to the theory that is produced by P&R arithmetic, which after all is just an axiom system. I should just skip these because there's absolutely no surprise here, right? So it's total, absolute, undiluted incompetence. So the simplest theorems of elementary algebra So here's an example. You know, is it true that there is an X which is such that if it's a prime number, then everything is a prime number? And, you know, this actually is an interesting theorem in algebra, because this is not a matter of calculation. And I'm not sure there's a lot in the data set, but there are an infinite number of these kinds of theorems that don't relate in principle, I don't think, I mean, my guess is to any of the data, but you sure as heck better be able to see and prove that these are correct. It strikes out. And we've done this quantifier complexity of this. I mentioned in my rejoinder to your rejoinder, you know, there's only 2 quantifiers here, folks. But okay, so it's a strikeout for GPT-4 treated hypothetically as a cognitive architecture. The M here is by definition, so that green check does not earn me any kudos. But we've expanded the list a little bit. Now, let's go to the second order case, second order piano arithmetic, which basically means, for those of you who are unfamiliar with it, we turn the technique of induction, mathematical induction, into a formula itself, and then we start instantiating in that formula. In truth, and I look forward perhaps to talking to Noah about this at some point. In truth, if you've paid attention and know a thing or two about logic, you've already seen that I'm not using fixed piano arithmetic. I'm using meta piano arithmetic, because I'm using formulae that are templates for instantiation, okay? And when instantiated, produce perhaps a theorem of piano arithmetic. So GPT-4 or any large language model really has, maybe it's possible, I think when we determine the expressivity of these systems to a greater extent, we'll see that it's mathematically impossible. Because if you can use meta logic and reason at the metalogical level, which we have to do, okay, all of that by definition is going to be continuously novel in human dialectic. So I don't know how data sets are going to help you, but maybe someone will figure it out. So here's PA3, which I was playing around with over there. So I threw this in because third order logic, you know, people have the idea, well, third order logic is very exotic. This is different than higher order logic. I just want to be clear. The higher order logic community says, look, you're going to run out of symbols, so let's start talking about higher order logic. This isn't what I'm doing. I'm channeling Kurt Gödel, who said, you know, humans use third order logic routinely. So my example here, suppose there are properties canines, assertion, Buford don't share, and that some of these unshared properties have the property of being scary. So in third order logic, you can allow properties to have properties, which again, we do. Given this is a true, et cetera, and it's of course going to fail. So, you know, I wrote out on the paper what it would look like in third order logic. That was an interesting effect there. And, you know, it's really simple and people can understand this. I don't know about second graders, but I'm pretty sure grade school kids could understand this. It has no clue. And I came up with a scenario that actually satisfies the identity of our 2 dogs. Okay, there's the dog. One person calls the dog by one name, another person calls the dog by another name. It's the very same frickin' dog, and it ain't a tiger, and a tiger is a scary property. You know, this is not rocket science, okay? Sorry, I don't know how this is going to work for the LLM people. Put logic in control of cognition, which is what happens when you're a rational cognizer, and then use these other things as subsidiary, less reliable techniques. So now what about second order logic in connection with the paper and the assessment of these architectures? So this does get very interesting. I have no idea how this is going to work out when evaluating these architectures. I think most of them are going to strike out. So here's a simple Leibnizian theorem going back to Leibniz, right? So if it's the case that there's a property that A has and B does not, then we know they're distinct. Well, we could argue about whether this holds in all physical scenarios, but you know, this is a theorem in second order logic. So, well, you know what's coming. I ran this by GPT-4, and you know, it's verbose, and the language conforms, I think, formally to Frankfurt's book called Bullshit, which I recommend. People often ask me, how would you classify what? You know, I would classify it by just citing the book, because it's confident. And if it really had the objective of persuading you like a sophist, it would be wonderful, you know, but it's basically total bullshit. And the conclusion here, we're talking binary, you know, this is like binary logic, elementary. So it says no, you know, they're not distinct, you know, they're actually the same. How easy is it for modern automated reasoners to get this? Well, there aren't that many automated second order reasoners, but not hard. So we don't need to look at the proof here. This is a hypergraph, not a metagraph. All right, so now things are going to get really interesting in a scorecard for these cognitive architectures. ACTAR is not going to work, because if ACTAR's commitment decades ago, courtesy of John Anderson, is still in force, it's going to be a strikeout. Okay, so I lost one. You know, ClarioNet, I don't really know for sure. Clarion's weird because, you know, Ron's son was always committed to symbolic, sub-symbolic. And on today's AI scene, it's an interesting architecture. So I don't know. I don't know about SNEPs, and I really don't know about Nars. Now, Pei's here, so I look forward to talking to him. If we don't finish the conversation, it'll be, you know, it looks to me like it's not quantifier rich, and we've got to get to second order quantifiers. As you saw earlier, there's an existential quantifier for a property variable. GPT-4 or any such thing, of course, that's a strikeout. But that's, again, not anything that's praiseworthy. That's by definition. I'm not inventing anything here. Okay, I'm not doing anything really creative. I'm just saying, for God's sake, since Euclid, we built up the formal sciences. I'm just looking at arithmetic. If you want, this is just number theory. We got number theory, topology, geometry, algebra. We go through it, and then we're going to have physics. Now, on this issue, aliens versus natural, I tend to think that the progression that our version of human persons, we're persons, but we're the human variety, we've been on this track of going from elementary arithmetic in the bullseye there, baby arithmetic, we made it to piano arithmetic, second order piano arithmetic, and then at the outer level there, we have the Gödelian results, essentially. So I think every creature that's really smart, that reaches AGI and beyond, is going to be on this track. If the aliens aren't that far along, they'll be further back. They're going to need to count things. They're going to need to do arithmetic, and they're just going to follow the track. And then I have, well, I won't bother with that. So, but stop here.
That's wonderful. Thank you very much. Questions from the room? All right.
Peter Voss mentioned in a talk yesterday a system, a Helen Hawking type of system, where it doesn't really take sensory input from the world, but moreover just does reasoning. So is this system, the Mu system, more of a reasoning system, or is it, do you conceive of it taking information, sensory information from the outside world and then building up its own internal representation?
Yeah, no, great question, Michael. The answer is it doesn't take any information in from the outside world, except at this point for what, again, is invulnerable. That is, it's got number theory. It's got elementary algebra. That's all I'm using here. But my assumption is that these creatures, whether they're on Earth or another planet, have to minimally basically do two things. They have to develop mathematics. They have to connect the mathematics to the physical world and how things move in it. So the next thing would be to go to physics. But physics, as has been formally captured, and we have axiom systems for that, special, quantum, and the classical mechanics case. So there wouldn't be perception of the outside world, as it happened in the case of humans building up these theories through millennia, really. It would be the fruit of that effort that now is incredibly, well, maybe not relative to some Martians or something that are super into, but mature. So no, but in my AI work, that's not what, but in my AI work, of course, so you have to have perception. And if you looked at the brilliant second grader, okay, take away the eyes and take away manipulative ability, and I guess the second grader is kind of dead. That may be part of what you're getting at. Yeah.
So yes, so so some of these models are pretty good at automating some of the higher order logic theorem proving and so on. But I'm offering a truce now.
Okay.
Which is tool usage. So one of the things that GPT-4 does very well is to call a tool. So for example, if it cannot do, determine whether or not an integer is a prime, it actually creates a Java program, which will test for primality, and then it'll run the Java program and give you the results and say, okay, it's a prime or not, and based on the tool. So what if we actually take your cognitive architectures, whatever tool, the tool of your choice,
right,
and then plug it into GPT-4, and then for such problems, it's going to give you perfect answers, but because it'll use M.
Yeah, well, if I was running a for-profit corporation that had any degree of dependency on a large language model, I would have, before disclosure to the general population, have already had my smartest people working on treating these things as no more than glue, because that's really what's happening. Okay, it's not, of course, directly to my talk. Now, but as I said along the course of this presentation earlier, what we should have done was put the rational side of cognition, and maybe there's still a chance, in control, okay? And what we glue to it would be things like what these LLMs can do. Instead, we have crazy people, okay, most of whom will simply not debate me. Okay, I would have bet $1 million. Okay, I'll have one logic problem, generally of the ilk that we saw here, and bring in someone who's an end-to-end large language model person, an end-to-end deep learning. So I mean, we were in disagreement before. I'm in agreement with you. That's obviously what we got to do in general. Now, the end-to-end maniacs, it's just not gonna work. It's just, but yeah. So, well, hopefully.
We'll take one more.
Hopefully, yeah.
Thank you for your speech. I have a question about after regressive models in general.
Yeah.
There is AlphaFold and AlphaFold 2 systems, which is in general after encoder systems, which helps to solve protein folding problem. before any other approaches tried to solve this problem, and it was hopeless.
Okay.
And this problem is a geometric computations, I would say. So it looks like autoencoder model can capture, underline the structure and produce good enough results. And can you, like, what do you think about the ability of attention-based autoencoder models capture very sophisticated, complex underlying geometric structures and produce high quality results?
I didn't hear the example of the great solution that happened. Was that protein folding? Or
yes,
protein folding. Well, you know, I'm ignorant. I don't know. Okay, I have a scientific American understanding, which is pretty much worthless scientifically, of protein folding. I don't know how hard it is in terms of computational complexity, or in terms of solvability and relative solvability. I just don't know. So I don't know what to say about it. But my firm intuition is that it's merely calculation. If it really was some groundbreaking thing that happened, it's probably just calculation beyond the capacity, at least up till that point, of what humans could accomplish. What I'm talking about are formal systems and formal capacity that is not calculation. Once we have it, we could do some calculation, but you generally don't get a Fields Medal, right, which is relevant to for doing something calculative. You get it for doing something creative, but still probably within the bounds of third order logic in some branch of mathematics. So sorry to disappoint you about the lack of specifics. Yeah.
That's great. Thank you very much, Summer.
Yep. This goes back to, said it, okay.
And next we have Sergey Shumsky, virtually, I believe. I haven't seen anybody of that name volunteering to come up yet. Presenting on ADAM, Adam, a prototype for hierarchical neural symbolic AGI. So welcome, Sergey.
Thank you. Do you hear me well? Yes.
Yes, sounds great.
Okay, sharing. Okay. Let's start.
Went on mute. We didn't get to hear your presentation. Can you hear us?
Yes. Do you hear me now?
Now we do. Yes.
Okay. Sorry. So I'm introducing myself. So I am head of a cognitive architecture lab in Moscow Institute of Physics and Technology, and I'll present the hierarchical neurosymbolic architecture, deep control. its working prototype, Adam, and some results of experiments. And to start with, the agent's behavior is governed by some rules of thought, which we call logic, and it defines the dynamics of mental states, which can be divided in two stages, action and perception. First comes action selection, which can be thought of as a prediction of a next mental state, since the agent don't know his next sensory value. The perception of this sensory data leads to the state transition to the next mental state and the evaluation of this new mental state using some reward function, internal or external. As a team from DeepMind stated in 2021, reward is enough for learning goal-directed behavior, that is to infer logic through reinforcement learning. In reinforcement learning, the intelligent decisions are based on a value function Q, which is sum of expected rewards over some planning horizon, and the larger this planning horizon, the stronger the intelligence. The good news is that there are well-known algorithms such as Q-learning to iteratively learn the value of all the mental states and the transition dynamics. And these two functions define the mental logic of the agent, that is what is called in reinforcement learning the strategy. The bad news is that the complexity of Q-learning scales as the planning horizon cubed. That is, long-term planning requires so many iterations that it makes the strong intelligence almost unattainable. And the solution we propose is to implement hierarchical thinking. That is where several layers they produce short-term plans which are easy to learn, but each on its own timeline. And the resulting planning horizon, and since the intelligence grows exponentially with the number of the layers. To illustrate the main idea of our approach, we consider the reinforcement learning as learning some mental language. And the formal language is defined by a finite set of its characters on alphabet and a set of rules for constructing all valid strings from those characters. In our case, the alphabet is represent the set of all elementary actions, and the vocabulary of the mental language are the all most frequently used combinations of those actions found in Q-learning. We can construct this vocabulary by using empirical counts of the pairs of mental states while learning the transition function. When this empirical count for some pair of mental states exceeds a predefined threshold, we define a new word of mental state as the combinations. The result of such learning is a nested set of grammar rules for constructing the complex plans from individual actions using the agent's mental logic. Moreover, we can define the semantics of this language using the statistics of right and left contexts of each mental state. These semantic vectors are well known in natural language processing. We can then cluster all these semantic vectors to find synonymic groups of words which has similar meaning, that is used interchangeable in similar contexts. And these clusters can be thought of as symbols of a new language, a meta language, defined on a larger time scale. And this meta language then can learn its own grammar, logic, and semantics, and so on. And thus we can construct a whole hierarchy of mental languages. And the result is the hierarchical architecture, which without deep control. It differs from traditional deep reinforcement learning, where deep neural networks are used to implement the value function to make separate decisions. On the contrary, in deep control finds a set of nested plans on a corresponding time scales. And in a sense, both architectures use a kind of deep learning, but traditional deep learning uses a stack of simple mappings in neural networks to define an arbitrary mapping. And in our case, in deep control, we use a stack of simple controllers to define an arbitrary controller. We developed a prototype of this deep control architecture called ADAM. In ADAM, all the layers are similar and consist of several main components, the 4 of them. The encoder translates the semantic vectors of the previous layer to the symbols of the current layer. Parsers then combines these symbols to words of the current layer. Planner predicts the next word to choose the best possible implementation of a higher level plan. And the decoder translates this plan to the layer below as a list of all its possible implementations using episodic memory. We used ADAM, for example, to train a robotic arm to reach an arbitrary position here. Here is a corresponding learning curve, and this is a simple task. This is actually it is a single layer model, and now we are working on more interesting and prospective task. This is a conversational intelligence. And contrary to transformer language models, which generate text word by word, ADAM constructs his utterances many words ahead, combining the whole sentences. And this graph shows the perplexity as a function of the number of layers. And as you see, the more layers, the better the quality of text generation. And saturation here is due to the lack of data in this concrete experiment. What is important is that the complexity of learning of our model is proportional to the data size, and is orders of magnitude less than that of neural networks, which are quadratic. Summing up, we propose a hierarchical neurosymbolic AGI architecture capable of automatic generation of optimal rules of behavior, which can be interpreted and debugged, and with the planning horizon, which increases exponentially with the number of layers and with the linear complexity of learning. So that's it. Thank you. Thank you for your attention.
It was great, Sergey. Thank you very much. Any questions from the room? All right.
Hi, thank you very much. Two questions. One question, I didn't see a component that verified the predictions. So the system makes predictions. The predictions are captured in the hierarchy that's constructed. But then is there an element or a component that actually verifies the predictions? And if so, which one is that? That's the first question. And then the second question was the reward. Is there an intrinsic reward? I'm assuming that there's no extrinsic reward, but is there an intrinsic reward, and is the reward computed by the successful prediction? Like if you make a prediction that's successful, you have reward, and if you don't, you have correction or punishment?
Actually, we use currently we use reinforcement learning, which is based on the external reward, based on the task at hand. But you are right, in minimal free energy principle, there is an internal reward. And we are going to implement this one too. It fits this architecture well. And as for the first question, you see, we have prediction based on the learned value function and based on the transition function. And this prediction helps us to choose the best implementation of each step. So each step of the higher order plan has a set of implementations, and these implementations they are known for this layer due to episodic memory. And from these implementations, the layer chooses the best one according to its logic and according to the current context, which is given by a current mental state at this level. So each level has its own logic, and it implements the knowledge of this level to choose the corresponding plan implementation at this time scale, at the scale of this level. And then symbol by symbol, it translates this plan to the lower level, and the lower level finds the implementation of those steps based on its own knowledge, lower level knowledge, I mean.
Thank you. Any other questions? All right, wonderful. Thank you very much, Sergey.
Thank you.
Next, we'll go virtually again to Paul Rosenblum. So rethinking the physical symbol systems of hypothesis. Dora's obviously very excited about these presentations. They're very good this afternoon. So this will be our final presentation before we'll have a quick break. We've got 4 more papers to wrap up the day, and the AGI business meeting for those interested in attending, and then the banquet this evening. So last paper of this session before the break. And welcome, Paul.
Okay, thank you. So this is a key hypothesis that's been around in AI for over 50 years. It's been questioned repeatedly and insistently, but never been truly replaced. So let's start by reviewing essentially the physical symbol systems and then the hypothesis and move on from there. So physical symbol systems, as they originally conceived, symbols are distinct patterns in the physical world. They're natural, that is, they obey the laws of physics and are amenable to engineering. And they're not limited to what is in human minds, though they were inspired by how humans use symbols. Symbols can be composed into symbol structures, also known as expressions, and processes can create, modify, reproduce, and destroy them. An expression designates an entity if its use depends on the entity's nature. This can be for internal as well as external entities. And for external entities, it provides one aspect of grounding in terms of relating, relating what's inside the system to what's outside the system. An expression is interpreted if it designates an internal procedure for execution that then is executed. This can be considered as a form of procedural designation. Physical symbol systems provide a form of universal computation. So they're Turing equivalent and essentially the equivalent to modern digital computers in terms of their abstract ability to compute. So the hypothesis, how this goes back to Newell and Simon, a physical symbol system has the necessary and sufficient means for general intelligent action. This is an empirical generalization rather than a theorem. And they provided both sufficiency and necessity arguments for this, again, not a theorem. So the sufficiency argument was based on two aspects. One is the universality. It says, assuming intelligence is computational, then universality should provide sufficiency. But it also argued based on the success of symbolic systems to date, that meant as of kind of the 1970s. The necessity argument said humans appear to be such systems, so that means in some sense that it seems like they must be necessary, and the lack of alternative approaches that were nearly as successful, at least as of that date, and that included neural network systems, at least as of that time. There's a couple of key quotes from Newell in 1980, kind of suggesting how important at least he felt this hypothesis was for the field. So the first one, in my own view, this hypothesis sets the terms on which we search for a scientific theory of the mind. And the second one even goes further. The physical symbol system is to our enterprise, but the theory of evolution is to all biology, the cell doctrine to cellular biology, the notion of germs to the scientific concept of disease, and the notion of tectonic plates to structural geology, basically claiming it's the foundational theory out of which all AI or AGI should grow. But there have been a number of critiques over the years. Here are four that Nielsen summarized in 2007, along with his particular responses to them. So the lack of embodiment or grounding, he felt this was just incorrect, misunderstanding what already provided. You can see what I've already said in terms of at least one form of grounding. There are other forms that have to do with essentially the role of perception and action play in grounding internal symbols in the external world. The need for non-symbolic or analog processing. He agreed with this complaint and basically said, well, take a symbol system, let's add numbers to it. And he, in fact, provided one early form of hybrid that did this. Brain style versus computation style, that is the notion that brains aren't computers. The argument here is that brains are, in fact, computational of a particular sort, even if they don't look like traditional computers. And the last one is kind of an odd one, the mindlessness of much of what appears to be intelligent behavior. The response he had was essentially mindless constructs will yield mindless behavior. The obvious implication of that is that to have true minds, you have to have more than just this, or more than just the mindlessness behavior. There are at least two lingering critiques that are highlighted by the recent successes of neural networks. And I've categorized them, one is a sufficiency challenge, one is a necessity challenge. The sufficiency challenge is essentially the lack of numeric processing that Nielsen identified. And when we look at sufficiency, you can look at the fact that numeric processing, at least in neural networks, can now do better on many problems, weakening the argument from successive symbolic systems. You might also point to graphical models and probabilistic programming as further examples of this weakening. Universality still supports sufficiency and implies you can do numeric processing even if you start with just symbolic, but this is weaker than the combined argument that was originally made. In fact, it gets even weaker when you look at the notion of cognitive architectures and how if you, for example, look at the common model of cognition, it argues that numeric processing is required at the same time scale as symbolic processing. Therefore, you can't just start with the universal symbolic reasoner and build numeric processing on top of it. You can do that, but it's not sufficient for building cognition in terms of a cognitive architecture. The necessity challenge is more directly derives from neural networks. Humans also appear to be such systems, so it's not just an argument for symbolic structure systems from from human minds and brains. And in fact, they provide an alternative that works as well or better on many problems than pure symbol systems. So the latter part may raise this question, should there be a neural network systems hypothesis that replaces the physical symbol systems hypothesis? I've just commented here shortly on the sufficiency side of this. So we know the neural networks have shown a remarkably wide range of successes recently. Some have even been shown to be universal, but many include, the more complex ones in particular, include explicit forms of symbol processing. So systems like AlphaGo and AlphaZero that play board games have added state space search on top of the neural networks. And that is essentially a form of symbolic processing. LLMs clearly operate on word sequences, again, a form of symbolic reasoning. And there are various forms of composition that are common in neural networks. There's also the contentious question of whether all neural networks involve symbols of some sort, whether the advocates of the technology want to agree to that or not. So to me, this question remains open. So an alternative is to consider a particular form of hybrid symbol system along the lines that Nielsen has suggested, but somewhat different, that subsumes both physical symbol systems and neural networks. That's essentially the line that's pursued in this paper. So we're going to go into a hybrid symbol system that's inspired by the common model of cognition, which is an attempt to understand at an abstract level what's minimally necessary in a cognitive architecture to achieve human-like, not quite human level, but human-like cognition. And also by the Sigma cognitive architecture, you can view that as essentially a spin-off of SOAR that I worked on for roughly a decade. So we're going to start by stripping the notion of a computational symbol. This is in symbols in general, but specifically a computational symbol, down into a non-obvious essence. In particular, it's going to be an atom, or we can think of it as a placeholder in kind of a Drew McDermott fashion, that is indecomposable in other atoms and distinct from all others. Okay, so we're saying that's what a symbol is. So in particular, issues of designation and representation, which are thought of as central to at least human symbols, are not part of this essence. So it differs from this notion of human symbols. It also differs from Nielsen's suggestion of just adding numbers onto existing symbol systems, which all assume designation as one of the essential attributes of symbols. So capabilities such as composability, designation, and interpretability, which you can think of as procedural designation, all become optional. So you can get a hierarchy of optional characteristics that exist somewhat like this, with interpretation here and declarative designation in terms of both internal and external. All of these exist, but only now on a symbols by symbol basis, and some but not all such systems are universal. We can also then add the option for quantitative metadata on top of symbols and expressions, which you can think of as data. This is along the lines of what the common model has hypothesized. And then clearly see that physical symbol systems are clearly one special case, where everything, at least except for the hybrid, is essentially required for all symbols. The claim here is that neural networks are another special case. That is, they are examples of hybrid systems of this sort, rather than just being combined at a gross level, as in, for example, Clarion, where you have a symbol system and you have a neural system, and together they form a hybrid system. So let's look at how neural networks are hybrid symbol systems of this particular sort. So let's start by considering a small feed-forward network for paired associates, that is, relates words to words, as you might see in simple traditional psychological experiments. The nodes in the input layer are hybrid symbols that do not designate. They're hybrid symbols. They're placeholders, essentially, or atoms that have numbers associated with them. That makes them hybrid symbols. They're neither subsymbolic nor microfeatures in kind of the traditional distributed neural network interpretation. So the individual elements are hybrid symbols in this way of thinking about things. Composability of a very limited sort yields the input vector. So it's a vector which is composed of hybrid symbols. And it designates the word expression on the input. So that's a relationship from this hybrid expression or hybrid symbol structure to another symbol structure which represents the word. The nodes in this word expression externally designate letters. So here we get to external designation or grounding. And in fact, the entire word structure, you could say, designates Alan Newell. Now we get to procedural designation or interpretability. So internal and output nodes all designate procedurally. That is, they designate a procedure which is a combination of summation and nonlinear transformation. That's essentially what happens at nodes in these kind of feed-forward neural networks. Links themselves also designate procedurally. They are expressions that combine two nodes and have a number associated with them, which is a weight. And then they designate the product of the node activation with the link weight. Okay, so that's the notion of a particular form of hybrid symbol system. There are, of course, many varieties of hybrid symbol systems out there. This is one particular version. So what kind of hybrid symbol system is this neural network? See, we got two W's there. It provides limited forms of declarative designation as the input node. The input nodes, as we saw in the previous slide. It provides quite a bit of procedural designation or interpretation at both internal and output nodes. Also actually at the links, and provides restricted forms of composition via vectors at the levels and links across the levels. If you look further in the neural network literature, you can see them going significantly beyond this in various ways, adding additional forms of declarative designation for some of them, adding additional forms of compositionality. You can, for example, look at convolutions, you can look at graph neural networks. They're all additional forms of compositionality in neural networks. And some of them add in universality. Okay, so what I'm proposing is a hybrid symbol systems hypothesis, or HSSH, in the form of hybrid symbol systems are necessary and sufficient for general intelligent action. So you can see it's aligned quite strongly with how the physical symbol systems hypothesis is expressed. And it's being proposed as a replacement for the PSSH. It's still an empirical generalization, not a theorem. And again, there's a sufficiency argument and a necessity argument. The sufficiency argument retains the possibility of universality from the PSSH, and it can appeal to the successes of symbolic, numeric, and hybrid systems. So there's a much broader base of success in this sense. The necessity argument co-opts the existing human cases, what we've seen for both symbol systems and neural system, and the range of successes listed above for sufficiency. That is this kind of thing. And it raises the question, are there in fact any possible alternatives? For example, quantum, or other kinds of things. But that's the general idea. Conclusion. So we're getting there quickly. We've stripped down the notion of a computational system to an atom or placeholder, where all the other aspects that are normally thought of as part of a traditional physical symbol system now become options. Added in the notion for quantitative metadata on these symbols to yield hybrid symbol systems, and showed that simple neural networks are instances of such systems. The assumption is that more complex ones, which are all basically variations on these simple ones, or at least most of them are also instances of such systems. And then propose this as a replacement for the physical system, simple systems hypothesis. There's a separate hybrid hypothesis in the paper for cognitive architectures, As discussed, numeric processing is concluded to occur at the same time scale as symbolic processing. So the argument from universality of the physical symbol system doesn't work here. And that's it. Questions?
Wonderful, as always, Paul. Thank you very much.
Hmm?
Any questions in the room? And any questions online? I think everybody's itching for their coffee break. Thank you very much, Paul. It was a joy.
Okay, thank you.
Pleasure. And we'll see you soon. So we'll pop out for a 10-minute coffee break. We'll be back at 5 till. And last session of the day. Yeah, isn't that nice? Yeah, it's easy, right?
What's your title at SingularityNET?
My title is a researcher. Maybe you can say head of the AGI-23 project, but that has nothing to do with this.
And you're a mathematician and an astrophysicist?
No. I have nothing to do with physics. Well, it's more computer science.
Okay. How's everybody? Good, good, good. Looking forward to the banquet. Right, I'm going to start introducing Neil while you're sorting out the technology there. Putting him on the Wi-Fi. Takes a little bit of time. So we're now heading into our final session. Well done online, those of you who followed. Paul, Yosantha, I hope you're still there. We've been enjoying your questions and your engagement. We're approaching the end of the wrap up of our formal paper presentation day here. And we've got one final session for you, which is only running like 1 hour late, which is not too bad going. And this final session is about decision. So we're going to explore different decision-making approaches, techniques. And I'm very honored to introduce Dr. Neil Geisweiler. Neil is one of my colleagues who I'm very blessed to work with at SingularityNET. He's a brilliant mathematician, one of our leading researcher in some of our advanced AI techniques. He heads up the AI domain-specific language, so AI DSL project, and Proto-AGI, and he does a lot of really, really brilliant work. And it's a great pleasure to introduce Neil, who's going to talk to 2 papers today. He's going to talk about probabilistic logic networks for temporal and procedural reasoning. And he's going to talk about a rational OpenCog controlled agent, which if we're lucky, might even have some little demos. We won't be lucky. It won't have any demos, but we're lucky anyway, just to hear about the paper from Neil.
So I have to. Okay. Yeah. Thank you, Janet, for the introduction.
Thank you.
All right. Yeah. So yeah, I have 2 papers. So the first one,
yeah, that's not the right order. Okay. Right, so I'm gonna present an extension of PLN for temporal and procedural reasoning. So PLN stands for probabilistic logic networks, and it's a logic that is very well suited for common sense reasoning, as well as many other things, actually. So I'm going to give a partial recall of PLN. So the basic objects we're going to work with are predicates, and we have connectors for these predicates. The first one is, so an important point is that we are working with predicates, but these predicates are actually probabilistic. So in which ways? Well, first of all, an evaluation over a certain value doesn't have to be just true or false. It could be a probability of being true or false. And in actuality, it's even a second order probability, which could be characterized by two values: a strength, which is a proxy for a probability, and a confidence, which is basically measuring how narrow the second order probability is around the probability. We can also, by the way, the equal sign with M, it means just measured by. We can also probabilitize a predicate, the predicate itself, which would correspond to the prevalence of this predicate to be true. And then we have the regular, this one is not regular. So we have implication, which corresponds to a conditional probability, or second order probability, should I say. And then we have the regular logic connectors, and or not. And on top of that, we have inference rules. So here's one, for instance, that can introduce an implication given data points. And here's another one that, given two implications, introduce a new one. So for instance, if P implies Q to some extent and Q implies R to some extent, then, well, to which extent P implies R? And that's what this inference rule is going to calculate. And here we have a formula, and this formula is, well, it's following more or less probability theory, well, except that we are in a second order, but other than that, it's basically probability theory. So now we want to extend that for to handle time. So what do? Well, we just add a temporal dimension as the last argument of the predicate, and then we introduce some connectors. So for instance, we have the well-known lag operator that basically is a temporal transposition of the temporal dimension. So it basically transpose from the left to the right. Another way to look at it is, well, I should do the opposite, right? Because from the left to the right, in other words, it brings the past into the present. Another way to think about it is that it brings a lens such that when you look through it, you see the past. And we have the lead operator that does the opposite. That is, it brings you a lens such that if you look through it, you see the future. And then we can expand connectors as well. So we have a sequential conjunction here, which is turned towards the future. We can have one which is turned towards the past. We can have an implication, a predictive implication, which is turned towards the future. And we have rules, inference rules for that. So for instance, we would have the temporal deduction, which is like a deduction, but with a temporal aspect. So if P implies Q, in the future and Q implies some R in the future, then to which extent P implies R is what this rule is going to infer. And what we find is that such inference rule is actually equivalent to this inference tree here, which actually relies on deduction, which is non-temporal. So that's very useful because we already have a formula for that. So that gives us the formula for the temporal deductions. The premises are different, the conclusions are different, but the formula is the same. So we gain that. And we can go further than that. We can do procedural reasoning. So now the objects we're working with are cognitive schematics. What's a cognitive schematic? It's a triple of a context, an action, and a goal. And what it expresses is, given a context, if I take some action, then I'll reach the goal to some extent. And the action doesn't have to be a primary action. It can be a composite action, it could be an entire plan. It would still be called a cognitive schematic. And we can have inference rules over that. So we would have the procedural deduction. And what we find is that, again, the procedural deduction can be expressed, is equivalent to this inference tree that actually also relies on regular deduction. And again, that gives us the formula of the procedural deduction. So again, the premises are very different, the conclusions are very different, but the formula is the same. So, well, now we know how to do temporal deduction and procedural deduction. And in my next talk, I'm going to show you how and why we use that. Do you have any questions so far? Or should we keep the question for the end? Okay, all right. Okay, so, all right, so now I'm going to present ROCA, which stands for Rational Open Cog Controlled Agent. So as the name suggests, it's an agent that leverages OpenCog and that tries to be as rational as possible. It doesn't have to be efficient at this point, it's just trying to be rational. Here is the cognitive cycle of ROCA, and I'm going to walk you through that cycle. So first, we are going to gather observations and we just record everything that's going on, and all observations that are coming from the environment are stored in a specialized atom space called the percept atom space. It doesn't really matter the format, but what matters is that a way or another, this record has to be under the form of an evaluation of a predicate evaluation, because that is what PLN is going to be able to use. So once we have that, we can use a combination of pattern mining and procedural reasoning to generate a corpus, or right, a repository of cognitive schematics. So how do we do that? So in OpenCog, we have a pattern miner for mining subgraphs. And so, well, everything is represented as graphs. So we just run this pattern miner and we extract simple patterns, such as this one, which would be a cognitive schematic expressing that if the agent holds the key and takes the action of going to the house, then it's going to find itself inside a house. But we have many more cognitive schematics. Yeah. Right. To some extent. So it's not always the case. Oh, thank you very much. Right. So measured by these two digits, the strength, which is a proxy for a probability, and the confidence over that probability. Okay. Yeah, thank you very much. Right. Okay. But so once we have all these simple cognitive schematics, we can use reasoning to produce new cognitive schematics, more complex ones, using, well, procedural deduction and other rules, which I did not present. So for instance, here we have a cognitive schematic that expresses that if the agent is outside, okay, outside the house, all right, and gets a key and goes to the house and collects a diamond, the agent's going to get a reward. And again, well, it's not always going to happen, but it's going to happen to some extent. Right, so the interesting thing is that this cognitive schematic, we could actually have discovered it just by pattern mining alone. The problem with that, beside the fact that it's more complex and so it's further away from, it's less reachable in the search space of patterns that we mine. But letting aside this problem, there's one even bigger problem, and this is that in order to find this pattern with a pattern miner, we need to have observed this pattern at least once. And well, I mean, already for that can be unlikely. For something more complex than that, that can be extremely unlikely. So what reasoning brings us is the amazing ability to make an educated guess about something that we've never tried. And so that's why it's so important. So now we're going to end up with a huge collection of cognitive schematics. And the question is, how are you going to turn that into action? So how do we do that? Oh, well, okay. So that's a slide just to explain that it's difficult. Why is difficult? Because first we have many, at any moment, many cognitive schematics could be applicable, and they can express contradicting things. So they can have different risk-reward profiles. They can even contradict each other. One may say, well, do this plan to achieve the goal. And another may say, well, actually, if you do this plan, you will not achieve the goal. And so how do we reconcile all these opinions? Well, so we use two things. We use a variation of Solomonov induction for second order probability distributions. And we use Thompson sampling over a mixture that we obtained from this Solomonov variation. And so what is Thompson sampling? So the idea is that you set an envelope over the possible world that you can be in, so a probability distribution. You pick one and you plan and act accordingly to that world. And you do that at every iteration. So what's usually happening is that you start with a very broad distribution. And so the agent basically doesn't know anything or doesn't know much and is trying everything. It's all over the place, trying everything and gathering knowledge and narrowing this distribution. And so as the distribution is narrowing, the agent is trying less, so it's less exploring, and it progressively enters a mode of exploitation until perhaps the moment where the agent finds itself in a new world, and in this case, the envelope flattens again, or perhaps partially, etc. So basically what it offers is really a dynamical way to balance exploration and exploitation. All right, so here's a very small use case. So we have the agent, the rogue agent in a Minecraft environment. it's already very abstract. There are only a few actions, a few perceptions. So it's really a trivial environment, and it's not meant to be otherwise. And so the agent is going to start in full exploration mode. So it's just going to be all over the place, trying everything and recording everything that's happening. And so it's going to do that for about 50 iterations. Then it's going to enter a learning phase where it's going to run the pattern miner, reasoning, generate thousands, if not dozens of thousands of cognitive schematics. And then it's going to go back to a phase of acting in the world, where it's going to be able to use these cognitive schematics. And so what we found is that, well, it's able to discover the optimal cognitive schematics and plenty others. And overall, it's the performance are improving. Sometimes little, sometimes a lot. It depends on the random seed and various parameters. But so the interesting thing is, so if we keep looping, if we keep looping these two steps, it's going to keep improving. So that's great. But something that is not so great is that it's going to be slower and slower. So it's obviously, ideally, it's not what we want. We want the opposite. We want something that would be faster and faster. So what does that mean? The problem here, obviously, is that the agent is only getting more and more efficient in the world, but it's not getting more and more efficient in its own mind. And so that's really, that's the current limitations we have, and that is the direction of the future research, which is going to involve a number of things, including, for instance, attention allocation, and also a form of planning, not just in the outer world, but also in the inner world. Thank you very much.
So we're going to take questions now for Nil before I last year. Oh, look, stand straight up. I'm going for the, you're first.
You first. Oh, thank you. So I'm confused. How is this different from reinforcement learning? With the Markov decision process, and you're like doing exploitation versus exploration, learning a policy. There's a huge amount of, fan outs. So you got, very large state spaces.
Okay, so depending on how you define reinforcement learning, it's not different. But there is something, however, that can rapidly be different, is that the goal doesn't have to be maximizing a reward. A goal could be anything that you can formulate as a PLN statement. And also the other thing I didn't mention is that goals can be subdivided into sub-goals. And so here we are, it doesn't mean that it's in contradiction with what we mean by reinforcement learning, but that's usually not what we include as a, and everything is a clear box, like everything is just logic. So, yeah.
Thank you for the talk. In the case of Minecraft, it looks like during the time, common sense reasoning must emerge inside.
Common sense reasoning, it's more an innate capability of the system. Now, if you mean that the agent is learning things about the world, it definitely does. I didn't show that, but it's going to learn all kind of stuff. Well, if I get a key, then I'll hold the key. It's going to learn that, and that's going to be useful. And it's going to learn a lot of things which are also not going to be useful. And yeah.
So very nice. It's a very good architecture and approach. My question has to do with the reasoning phase.
Mm-hmm.
So it seems like you're getting information in from the environment or from the model, and then you're generating a lot of hypotheses or generating a lot of statements. So the question is, how do you control that generation? I mean, the reasoning seems to be the big bottleneck.
All right, that's the next step. I mean, as of right now, it looks more like a brute force, exhaustive search. But right, the next step is really to control that. And so if you want to know more about that, the idea is to reapply the same system, the same reasoning system, but this time you include as observation what happens inside the mind of the agent. So for instance, if the agent takes a certain branch in the search space, then you record that. And if the path was successful, you record that. And so you can go from, then you can reason about that and discover rules, discover patterns, which are actually going to be cognitive schematics as well. And then you use these cognitive schematics to plan, as I said, in the inner world.
So I'm wondering about the getting less efficient in the head part. Like, are you going to do something like reasoning to figure out what the actually useful lemmas and rules are and sort of pruning the rest that are easily deducible again?
Yeah. That could be a way to do. I mean, among other things, yeah, that could totally include that.
Thank you. And just as you were asking that question, we'd one in from the online audience. So Suru1, thank you so much for your question. Asks, first says, very cool. And I agree, very cool. With your last point in mind, agent needs to get more efficient in its mind. Could this involve a new form of metacognition, considering society, time, place, etc.?
Considering time,
society, time, place.
Society, time, place, etc. Yeah, I'm kind of bugging on that one. So a new form, well, it certainly would be new in the sense that it's totally underexplored. So it would be new in that sense. I don't know if it has to be new in a conceptual sense. Who knows? I don't know really how to answer that. So
it could be a new form of medic.
It
could be.
I guess
is the
yeah,
answer.
Yeah.
For Suru1, the answer is it could be. So big thanks to Nil for these two inspiring papers. Thank you very much.
Thank you.
Okay, and we're on the final stretch. So next up I have Mayank Keriwal is going to talk to us about, can language models be used in multi-step common sense planning domains? Welcome, Mayank.
All right, testing. All right, great. Okay, so this is work done with my incoming PhD student Jishang, and he did most of the work. I will try to present it as best as I can. So I'll just start by saying a couple of things. So there are a lot of technical details in this work, and so if for formalism and other things, we do encourage you to read the paper. But I do want to, make a higher level point before we go into the work. So we deliberately frame the title of the paper as a question and not as an answer, because as it turns out, what we hope to convince you of is the answer is not as nuanced. It's not an unequivocal yes, and it's not an unequivocal no either. So we are not taking sort of dogmatic positions, on the language models. We just want to kind of show you what we found when we were doing this work. The second point is this was done pre-ChatGPT, pre-GPT-4. We do have some results since then that are not in the paper, but we were testing some of these models well before the generative model hype. So, this is not meant to be a chat GPT or a GPT-4 kind of, paper. We want language models generally to be applied to the work that I'm going to show. So, even before ChatGPT, language models had achieved impressive gains on difficult problems of interest to I would say AGI. So not all of AGI, not all problems, but certainly some difficult problems of interest. So what you're seeing over here are leaderboards that were hosted and are hosted by the Allen Institute, and these are, machine common sense benchmarks from the natural language community. So you have things like physical common sense reasoning, abductive reasoning. HelloSwag has a lot of social reasoning, CSQA, and so on. This is just a brief snapshot. And even before GPT-4 and these kind of models, if you can see the very right-hand side, it's small, but it was approaching human performance. So human performance on HelloSwag was 95.6%. That's the fraction of questions that a typical human would get right. And the unicorn model that I believe was out of the University of Washington or Google, one of the big players, was 93.85%. So, this is kind of exciting, also a little bit, warranted for skepticism, right? Because, do these models really have common sense? And most people in the community would actually tell you no, so then the question becomes, well, then what's wrong, right? And why should we not trust the evaluation as much? But before I go into that, let me just quickly, and I've done this, once or twice in previous presentations, but for those of you who are not here, this is a slightly more technical slide than I've showed in previous presentations. So why study common sense? Well, first of all, it's been an important milestone in AI right from the start. So in fact, McCarthy was quoted in the 1950s as saying that it could be achieved with formal logic. I don't think that has turned out to be the case, although it is important. Formal logic is important in perhaps achieving this. And developmental psychologists who were brought up today in a couple of presentations actually agree that abilities to reason about a number of these elements emerge early in humans and serve as crucial foundations for later learning. We saw this today in the earlier keynote as well. Some abilities emerge pretty early. The theory of core knowledge, by the way, is this thing that you see here, objects, agents, places, number, form, social beings. So it really does give a good sense of what we mean by machine common sense, and what should be in machine common sense, hopefully, if it's achieved. And despite much effort over the decades, the problem has proven to be surprisingly difficult to crack. Transformer-based LMs have yielded promising solutions, but not achieved the machine common sense yet. And so here on the right-hand side, you see sort of a survey, a figure that comes out of a 2015 survey on machine common sense. It's pre-LLMs. So as you can see, a number of techniques had been tried, none of which really yielded the kind of performance on some of these benchmarks that LMs were able to achieve. So what's the problem, right? Well, first of all, the evaluation data sets have some severe limitations. One problem is that they're all QA benchmarks. So you give a question, there are some choices, you select the right option, and then you sort of count, how many questions did the model get the correct answer on. I mean, that's okay. That's not a bad first try, but we don't navigate the world that way, right? We're not talking to each other using multiple choice questions. There's a lot more to it than that. So there's a need to design common sense tasks that are more aligned with real world complexity. In hindsight, right, no one could have really guessed, pre-LLMs that the QA benchmarks would get crossed so rapidly. So the original assumption was these would be difficult to achieve human-like performance. And for a while, it was difficult. The traditional techniques were getting 1% improvement, 2%, they were like 20, 30% below human performance. So it wasn't a bad first try. It's just that with the LLMs, those benchmarks got exceeded. But we feel that the machine common sense has not been achieved. So we need better benchmarks. One such direction that we are especially interested in, but also others, as this paper below shows, is multi-step planning. So given a goal and some everyday actions and objects, so this is the common sense nature, we are not making it abstract. We are expressing the actions and objects in an everyday fashion. In the earlier generation of LMs, we made to construct a multi-step plan fulfilling the goal. In this example, the robot is asked to put fruit in the box. And in the original training, there is actually a tray. So you can put the fruit on the tray and then take it to the cupboard, put it in the box. In this one, they remove the tray and they want to see that, okay, if it's not given the tray, can it generalize a little bit? Can it apply common sense? And it actually does. It figures out that if you can't take Muhammad to the mountain, take the mountain to Muhammad. So, that principle is actually carried out here, where they take the fruit to the cupboard, then take out the box, put the fruit in the box, and then put it back. So actually it was able to learn that from scratch, even when the tray was unavailable. So this was exciting. We wanted to take this work further, right? So we were wondering, how do we apply language models to multi-step planning? And we started looking for environments where we could apply language models to multi-step planning. We didn't want to build one ourselves from scratch, obviously. So we did find one, and this may not be the only one, but it does some really nice features of this environment. It's called Science World. And if you look at the original paper in 2022, it says Science World is your agent smarter than a 5th grader. We had a keynote today that is your agent smarter than a 2nd grader, right, on a different problem. This is a visual representation on the left-hand side. On the right-hand side, you kind of see more formally what it looks like, where it's small font, but basically there's a task description. You kind of have to, it's not, they don't say anything about the solution, that whether you should use language model or not. You can use whatever you want, but you basically have to pick actions and objects. So there's a limited set of actions. And in your environment, you can look around and you see what objects are there, and then you instantiate actions with objects. Then something happens, then you get to re-observe the environment, and you keep on going till you hit the goal. And they have this partial scoring also on the side, but that is heuristic. Ultimately, you either solve the problem or you don't, by the end. So early results in the paper, so this is from the Science World paper, showed the environment posed a challenge. So both reinforcement learning, which is this DRRN that you see in the second column, and the language model-based methods, which are the last 3 columns, proved to perform badly when asked to solve tasks end-to-end, but the metric was 0, 1. So either the task is solved, so you do all the steps, you have a valid trajectory to the goal, or it isn't. It could be that you solve everything all the way till the second last step, and then something goes wrong, and that would still be a 0. And so we felt that that even though this is a good metric, it's too simplistic and or too ambitious. Certainly there should be metrics complementing it to see that, okay, can we give partial credit to systems, and what happens if we give partial credit? And what's nice about the benchmark, by the way, is that it's open source, so anyone can play with it. You see there's a lot of diversity, as you see in this table, right? So there are lots of different simple experiments, and there's a large set of actions, relatively large set of actions and common sense objects. So it really is a very nice environment without being too intimidating. So what we proposed was to decompose the task into multiple subtasks posed as question answering problems. So we know that the language model was doing very well on question answering. So we were like, let's take this into its home turf. Let's give it an advantage rather than a disadvantage. So we know it can answer questions very well. What if we break up this problem into multiple question answering problems, and then what happens? Is it able to do okay? So here's an example. This is a very involved slide, but hopefully it expresses the point. So the thing that you have to do is find a plant. So that's simple, right? Except the plant is not just there, near you. So you're in this room kind of home sort of environment, and you have to move around and find the plant and then pick it up, basically. So your task is to find a plant, first focus on the thing, then move it to the orange box in the living room. So that's the full task, right? And the way we did it was that we would observe the room, we would observe the environment. We also have an inventory, so this is provided by the Science World, that what do you have right now, kind of like a game. And we would combine the observation and the inventory. Then we would combine that with a verb prompt. So what should your next action be? So that is one question. And we give it some verbs, one of which would be the right answer. And then there's an element prompt, which is what should the next object be, right? And then there's an action, which is if your verb and the object are correct, then the full action is correct, right? So we can also test that. Did you get both correct independently? And you can see some examples here. So in the verb prompt, right, you can see that the correct verb is move. In the Object 1, the correct prompt is flower pot, orange box. So it's kind of a more sort of, almost like a chain of thought reasoning, for those of you might have heard about that, where it's like, let's focus on one myopic problem at a time rather than ask you to solve the whole thing end to end. And so if we do that, right, and just go question by question all the way till the end, what happens? What performance do we observe? This is also important because it tells us that does the language model go wrong right in the beginning? Is noise random? Does it randomly get questions wrong? Or, what happens, right? So for experiments, we kind of use the same corpus, number of multiple choice questions, question answering instances, twice the number of actions, because each action is split, right, into a verb and element. We use 4 metrics. Did you get the verb correct? Did you get the element correct, which is the object? Did you get both correct, right, which is the action? So that necessarily has to be less than equal to the verb or element accuracy. And then finally, did you get everything correct? And that's the task accuracy, the original thing that was tested, right? And we showed performance on actually BERT. So we picked the BERT-based model and we fine-tuned it on the training partition, right? So we kind of went down the more traditional route because we wanted to see how do the discriminative models do on this, and we felt that would place a floor on the performance, right, for later models. So just going quickly over this, I'll just point you to some of the key highlights. So if you look at this table, right, what we find is that when it comes to the verb and the element accuracies, the numbers are quite high, right? So if you give it a set of choices and you give it the observation and you ask it that here's the goal, here's what I'm seeing in the room, here are some options, choose the right verb, choose the right element, it actually does get that correct. So it is kind of understanding a little bit of what it's supposed to do, at least myopically. When we go to the action, it's also pretty high. It holds up correctly. So in most cases, the verb and the element together are actually correct. In a lot of cases, there's some drop in performance. Of course, if you don't get 100% accuracy, it could be, unless you get 100 in all of them, you will not get 100 in the task accuracy. And there are multiple subtasks within each of these rows. So we report the average, which is why the numbers are not always exactly like less than equal to. But you can certainly see that in the biology, the identify life stages, it does get all 100%, perhaps because it's more factual. There are other cases where you can see the biology grow a fruit, where it does very well on the myopic problem, but the overall task it's unable to do. So there's something that goes wrong in either in the middle or the end. Is one question perhaps that it gets wrong, or 2 questions, and so it gets 0% accuracy. So many of these results are actually in alignment with the original science world experiments, where the task accuracy was close to 0 or very low. But what we are showing is that, in fact, the benchmark can serve as a complement or an extension to the original benchmark. So instead of going for all or nothing, it might be better to break up these kinds of problems with multiple metrics, so that you can see, how the model does on the easier version of the problem, on the more myopic version, and how well or badly it does on the hard version of the problem. So our takeaways are that transformer-based language models struggle with multi-step common sense problems, but they can play a powerful role in dealing with intermediate problems. So we should not dismiss them so easily. They can actually play a role in solving some easier problems along the way. And then maybe we need something else to combine the intermediate solutions into a full solution, maybe a hybrid system. But what we found is that certainly in GPT-4, we did try some of these science world tasks, and we found that it's able to achieve even very high task accuracy. So even this problem kind of fell, like several others, in the sense that GPT-4 was able to give us plans for many of the science experiments. Many of them were in fact perfect. There were some where it made mistakes. So one caveat that we note is that the proposed benchmark is derived using the gold standard solutions, right, in the original benchmark. So usually there's one gold standard solution, but the nature of this task is that there could be others. So it might ignore, so these should be treated as floors, not as ceilings, the numbers you saw. So some of them might be correct, but it's not aligned with the gold standard. So it's treated as wrong. And so there are many avenues for future work. I mean, the one thing I do want to point to is that rather than finding problems with the language models all the time, right, if I may, I think it's perfectly fine to treat it as a tool. We can all agree that it's a useful tool. But, we can dismiss it as an AGI system. We can say that it has all these problems, but as a tool, it is very useful. And what we try to do is to find the places where it can play a useful role as a tool, right? And because there's the accuracies and performance on many realistic problems are truly astounding. And then at the same time, we also want to figure out the right methodologies for evaluating these models. Sometimes there's a negative bias, like an all or nothing. Sometimes there's a positive bias, right? As in the original question answering benchmark. So I think nuance is really important when we are evaluating these systems that we don't fully understand, and we should not dismiss them, nor should we hype them, but we need to take a more scientific view of how we evaluate them. So on that, I'll just show you my references with Q&A, and if you are more interested in some of the formalism and technical details, please do see our paper.
Okay, we're going to take just one question
All right.
in the room, then we're going to move on to our last paper. We've then got a wrap-up talk, and then we've then got a business meeting.
Yeah, what examples did GPT-4 do differently than the previous version?
So we haven't yet done a full study of the GPT-4 because when we first tried it, only the chat interface was available. I think now the API is available too, so we might try that. But my student actually did enter the prompt in GPT-4 and gave the GPT-4 the observations and the 20 or 25 actions and objects and so on, and asked GPT-4 that, can you give me a plan that is constructed in terms of these actions and objects, and it would give the full plan. And we evaluated and saw that the plans were usually correct. So we're still waiting to do a full scientific study on that. But many of the cases that those other models got completely wrong, the GPT-4 is able to get very good task accuracy. By the way, the GPT 3.5 was not able to get. So we did try the GPT 3.5 and the chat GPT and so on. And those did make mistakes or were not able to do what GPT-4 was able to do. But it wasn't, again, not like some of the problems GPT 3.5 was also able to get. So we're trying to see whether there's a pattern, but that's in future. Yeah.
For our culmination paper for today's presentations, and indeed the formal presentations of the whole conference, I'd like to welcome Ali Baik Mohammadi to discuss comparing Nars and reinforcement learning, an analysis of ONA and Q learning algorithms. Thank you, Ali. Take it away.
Okay. Good evening. This is Ali Baik Mohammadi, a second-year PhD student at the Stockholm University. It's my pleasure to be here at the AGI-23 conference to present our work, which has been done under the supervision of Sindri Magnusson, my supervisor. Before starting my presentation, I would like to express my thanks to Patrick for his support, encouragement, and also proofreading of our paper. So I'm going to present our analysis of the ONA and Q learning algorithms in the context of comparing Nars and reinforcement learning. As you know, the goal of AGI is to create intelligent systems capable of adapting and learning to solve a broad range of tasks in diverse environments. To achieve this, reinforcement learning has emerged as a popular approach in the field of machine learning for tackling sequence-based tasks. And it has quite a good potential to touch the goals we expect. Especially thanks to deep learning, deep RL has shown great potential in automating decision-making and control tasks in various domains like game playing, financial markets, robotics, healthcare, and many more. But actually, everything with RL is not good as we expect. It still faces limitations when dealing with tasks that have limited data, since it's actually data hungry and complex representations. These limitations have slowed RL's progress toward achieving AGI's goal. So many researchers in the RL community are working on how to deal with RL limitations. But we think maybe the solution could be found somewhere else by looking for alternative approaches. And in this regard, in this work, we focus on Nars, a general purpose reasoner introduced by Dr. Pei Wang, and answer the question of whether we can replace RL with Nars to solve sequence-based tasks or not. Here is the outline of rest of my talk. I will start by providing an overview of RL and Q learning algorithm. Then I will quickly present Nars and ONA. Following that, I will discuss our experimental setup, present the results and findings of our analysis, and finally conclude with some thoughts on future work. All right, let's start with RL and Q learning. Reinforcement learning, as you know, is a learning paradigm in which an agent interacts with an unknown environment. Through a process of trial and error, the agent receives feedback in the form of rewards from the environment based on its action. The goal of the agent is to learn an optimal policy, we call pi star, to take the best possible actions in different states to maximize its long-term reward, which is called total cumulative reward. But how can we find such an optimal policy? Actually, in most cases, instead of directly finding an optimal policy, we are looking for an optimal Q function. And then there are proofs that show that by taking the action which maximizes that Q function, we are following from an optimal policy. But then what Q function means and how to get the optimal one. The Q function represents the expected discounted return of taking action A in state S, and then that's why sometimes also we called Q value or a state action value function. To find the optimal Q function, tabular Q learning is a well-known algorithm that uses the agent's experience in the environment. In this approach, we use a table to store and update the Q values for each state action pair. Then we update the Q values iteratively based on the interaction with the environment and observed rewards. By repeatedly updating the Q values, the algorithm gradually converges toward an optimal policy. The set codes for tabular Q learning, as you can see, includes initializing the Q table, choosing actions based on an exploration-exploitation trade-off, updating the Q values using Bellman equation, and repeating the process until convergence. To balance exploitation and exploitation, Q learning often uses an exploratory policy like epsilon gradient strategy, which means that agent explores the environment by taking random actions, face a probability of epsilon, and exploits its current knowledge by selecting actions based on the Q values with a probability of 1 minus epsilon. In this paper, as we have a fixed objectives, we have applied an exponentially decaying epsilon. Let's shift on our focus on the other side and talk a bit about its rival. I'm sure that all of you know well about Nars and ONA, as there was a very informative workshop about them on Friday. So here I will just quickly highlight some of their features before delving into the experiments. Nars aims to create a general purpose thinking machine. It's built on the theory that intelligence is the ability of a system to adapt to its environment while working with insufficient knowledge and resources. Nars is based on principles of non-axiomatic logic and uses Nars language. And one of the key strengths of Nars, which makes it suitable for real-world application, is that it has ability to handle uncertainty and inconsistency in reasoning. As you know, ONA also is an implementation of Nars designed specifically for practical purposes. Similar to Nars, ONA also uses Narses as the formal language for expressing beliefs, goals, questions, and meta-level inference rules. It supports Python interface, and actually this is the main reason to select this framework since our tasks have been implemented in Python. Move on to the setups and environments we use. For our analysis, we consider 4 control tasks from OpenAI Gym benchmark suite. All of these tasks have discrete action and observation space, except Flappy Bird, which we had to discretize it. We made no modifications to the environments or the reward of other environments. If you would like to know more about what the goal is in each environment or how the observation space, action space, and reward is defined, you can ask me for sure or refer to the OpenAI Gym website. But I should talk a bit more about one of the environment, which is frozen lake, as we have used 4 different variants of it. First of all, we have it in 2 different sizes to see how a bigger observation space could affect the algorithm's performance. And also, I want to highlight the slippery feature in the environment. This feature allows for a non-deterministic environment, where the agent has a probability of 1/3 to move in the planned direction and an equal probability of 1/3 to move in either perpendicular direction. We find this feature also interesting as it allows us to observe how algorithms perform in non-deterministic scenarios. We performed a grid search to tune the hyperparameters. We ran each combination 10 times and reported both average and standard deviations for the best one among all tasks. QLearner uses reward, while ONAT receives a specific event open task completion. You can see also selected hyperparameters for both approaches in this slide as well. But the exciting part, result and discussion. We have monitored average reward, average time steps to evaluate the performance of both algorithms, ONA and QLearning. As shown, the performance of both algorithms highly varies depending on the task. And interestingly, ONA outperforms QLearning in solving non-deterministic problems, which is very interesting. Here we have plotted also cumulative successful episodes, average time steps, and I want to emphasize that their performance degrades hugely when the observation space of the problem increases, as you can see for frozen lake. But ONA's performance is most robust against increasing the observation space compared to QLearning, which fails to learn using the same setup. Here we have cumulative random action plots to see how the agent tries to explore the environment. In the case of QLearning, the agent's exploration is independent from the environment. And as I said, the frequency of taking random action is set by the parameter epsilon in QLearning. So as time progresses, epsilon decreases rapidly, which impacts QLearning's ability to solve problems, especially in case where good policy haven't been discovered or the environment's goal is changing. The low variance in QLearning shows that the agent's decision is unaffected by changes in the environment across different trials, which is bad. But on the other side, for ONA, we can see that it behaves differently in different tasks, which shows its exploration is dependent on the task, which is quite interesting. One more thing, in ONA, the system sometimes suggests a random action itself for environment exploration using the motor babbling parameter. Therefore, some of the actions that I have here mentioned as labeled as a non-random in these plots are actually exploratory and random in nature. ONA decreases motor babbling automatically once a stable hypothesis or accurate prediction are established. So this happens without relying on a time-dependent reduction in the exploration rate. And I believe that this flexibility allows ONA to handle multiple and changing objectives, which could be interesting as a future work. Let me recap just whatever we got and propose some ideas for future work. In conclusion, our analysis showed that ONA and Q-learning had comparable performance on average across the 7 tasks. The potential of Nars as a substitute for RL in non-deterministic problems was obvious. There are opportunities to combine the strengths of both methods to enhance performance and adaptability. Potential future work includes extending tasks to multi-objective and changing objective scenarios, and also exploring combination of ONA and Q-learning using methods like voting, hierarchical learning, or even teacher-student learning could be interesting study. Thanks for your attention.
Thank you, Ali. Brilliantly done. And within your 15-minute allocated time slot, which is very impressive. Anyone in the room got a question for Ali? I know, like, dinner started 7 minutes ago, so it's hard, but just the one. Thank you.
Yeah, thank you. I'm curious about the execution time. Is it a big difference if they learn the same kind of level?
Not actually. It's not because I think we are using the same iteration number, so it behaves the same. But actually, I think the getting result from ONA is quicker than what we had there. Maybe because like the backend of ONA is based on C, but the framework that we have used for Q learning is just based on Python. So Python is a bit like slower. So maybe this is the difference.
Thank you very much. Anything else, or let's just give a great big round of applause to Ali for the last paper of the day. Yay! Woo! Thank you very much, Ali. Now I've got a couple of short announcements to make. People upstairs, I know you're having a nice spacious time up there, but we're about to do a wrap up from Klaas, who's our chair of this event here, in 2 or 3 minutes down here. So if you'd like to come and all get together, and then I'm going to tell you how Banquet is working. I'm going to tell you how the business meeting is working. But first off, thank you to everybody who has stayed and tuned into us all day online. We've had some very impressive watch statistics over the weekend. We've had thousands of views of these sessions. So it's brilliant to see how much the world is tuning in to what we're doing here at AGI-23. So thank you very much to our online audience. Let's give them a big clap, everyone from here in the room. Thank you, online audience. And thanks for your questions and engagement. Tomorrow, a couple of changes to the schedule for tomorrow's workshops. First off, Rachel Sinclair will be leading a session on accelerating AGI development with hardware, and that's going to be all day, and that's going to be upstairs. The morning session in this room, Ilya Parker will lead a session on safety, trust, and artificial generalized intelligence. Here in this room in the morning, and then in the afternoon session in this room, we're going to have the mighty Anton Kolonin, who's going to lead interpretable natural language processing, and these workshops are open to everybody. So before we close down and shut off for the day, I'd like to invite the chair of this brilliant conference, Klaas Strangard, to come and make a couple of points. We'll fix that after this. Thank you. Thank you.
Yeah, now it works. Thanks. Okay, thank you so much, everyone, for making this conference such a big success. We had a fantastic turnout this year with about 150 physical participants here in Stockholm and 500 registrants for the live stream. That's a lot. So it's about 650 people in all. And Ben, could this be a record, perhaps? Let's say it's a record. Okay, great. Okay, so thanks to all our speakers and participants for your questions and discussions, both in person and online. I also want to thank the PC co-chairs, Patrick and Marian, all the reviewers, yes, exactly. The organizing committee, not least Pei, Matt, Robert, and Vlad for their amazing job. Many thanks also to our sponsors, AGI Society, SingularityNET, Cisco, Digital Futures, True AGI, AAAI, and Springer. I am also very grateful to the SingularityNET team, and in particular Ben, Janet, Haley, and the streaming team for your excellent hosting. So now it's time to announce the winners of the prizes. First of all, we have the Best Student Paper Prize. And that one goes to Michael Timothy Bennett for Emergent Causality and the Foundation of Consciousness. Yeah. Yeah. You want a prize? Okay. Now, yeah. Well, no, wait, okay. I congratulate you. Well, you will get a diploma later, I think, too. What? Yeah, you will get a diploma too, and maybe a check. Yes. And then the AGI prize for best idea goes to Robert Winsche, an adaptive vision architecture for AGI systems. Whoa. Okay, congratulations. And the Springer Prize for Best Paper goes to Paul Rosenblum for rethinking the physical symbol systems hypothesis. Congratulations, Paul. I know you're online. And finally, the AGI Prize for Best Application Potential goes to Neil Gieswiller and Hedra Yusuf, Rational Open Cog Controlled Agent. Okay, again, thank you so much, everyone, and hope to see you at AGI next year. Thank you.
Thank you so much. Brilliant wrap up, fabulous prize winners. That's it for AGI 23, day 2 of the technical paper presentations, day 3 of the conference altogether. Day 2 of the technical paper presentations. Ben, listen to the qualifier. And so we're going to say goodbye to our online audience. We're stopping our live stream right now. So thank you all for tuning in. Please do tune in again tomorrow. You can choose which room to